Check. Hello. One, two, three. Check. Hello. 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 Check. Hello. One, two, three. Check. Hello. 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 Check. Hello. One, two, three. Check. Hello. Hello. Hello.
Is this audible? And not too bad or loud or anything. I apologize in advance if you hear me coughing. Oh man, okay, can we stop this? Yeah, no, but my accent is a mix of lots of things. I think it'll just mess it up. Captions. Version captions for fun. Uh, okay. Testing. Very good. Look, it's audible, right? Okay, I apologize in advance if you hear me coughing. I'm sorry about that. Um, Right. So thanks for the introduction and thanks for inviting me. It's good to be here. And thank you for rounding down on the decades. So my brief was to give talk about sum of squares methods and coding theory, and I'll talk about some recent developments which kind of give new decoding algorithms for codes using optimization methods. This is a tutorial. I'm not assuming much in terms of background beyond what would be typical maybe in an advanced undergraduate or a first-year graduate class. Please do stop me if something is unclear. There's some concept which I kind of included which is not defined. Please do stop me and ask. All right. And I should say this is joint work with a lot of fantastic co-authors, Vedat Levielev, Fernando Granaja Geronimo, Dylan Quintana, Tushant Mittal, and Shashank Srivastav. Shashank is right here. And Tushant and Shashank are on the postdoc job market. Vedat is on the faculty market. Do look them up. They're all great. Okay. And with that, let's start. There's some feedback. Will it help if I move it further?
Maybe if I move it further.
That better?
Too soft. Okay, move it up. Better now? Okay. All right. So let's talk about codes and then decoding, and then we'll talk about what we mean by proofs. And just to introduce what error correcting codes are, we're going to think of sending a message, let's say a sequence of bits, fixed length sequence of bits. And hopefully this picture reminds you of an adversary. So there's some adversary who will kind of corrupt the sequence of bits, and our goal is to recover the original one. Okay? And these are called error correcting codes. There are also other kinds of codes for compression, etc. I'll not talk about them. I'll only restrict myself to error correcting codes. And in particular, where the bits are corrupted by an adversary, we'll just have some restriction how many bits the adversary can corrupt, nothing else. Okay. So for example, if we want to communicate this message and if the adversary is limited to corrupting 1 bit, we can repeat everything 3 times. And then for every position, we can just take the majority of the 3 copies. If the adversary corrupted at most 1 bit, we'll be fine. Okay. And this is, of course, not the best way to do this. And in general, the theory of error correcting codes is about what is the minimum amount of redundancy you can introduce to correct maybe 1 adversarial error or 2 or 3 and so on. Okay. And this is captured in some properties of the code. We'll talk about that in a minute, but let's define codes formally. Okay. So we'll think of a code as, formally it's just a subset of, let's say, f2 to the n. Of course, there's nothing special about, there is something special about 2 in the sense it's most commonly used, but we'll restrict ourselves to thinking of codes as a sequence of bits, but whatever I say can be applied to codes where you're thinking of symbols from some other alphabet of size q. And I'd like to think of linear codes in the talk, which means that this subset is actually a subspace when I think of f2 to the n as a vector space. Okay. And so if you think of q as a prime or a prime power, you can still do this. So, but let's say we just restrict ourselves to 2 during the talk. Everybody okay with the definition of a code? And in particular, I'll always mean linear codes when I say codes. So it's always a subspace. Okay. Okay. Now let's see what we mean by decoding, which is this task of correcting a certain number of errors. And this can be measured by a parameter which is called the distance of a code. So if you think of these code words as these red dots sitting in all of f2 to the n, which is this ellipse somehow, then we'll ask what is the distance between any pair of points in this picture. And in particular, we'll look at the worst case, so the minimum over all pairs of points which are unequal of the distance between those pair of points. And when I say distance, I'll actually use fractional Hamming distance, which is nothing, just the fraction of positions in which they differ. Okay? That way I won't have to write an n all the time. I won't have to remember what is the number of bits in a code. This is just a fraction between 0 and 1. Okay? And now it should be easy to see from this diagram that if an adversary corrupts delta over 2 fraction of bits, then we will land up somewhere in this ball, which will be disjoint from the ball around any other code word of radius delta over 2 in this notion of distance. And so, at least in principle, we can always sort of, these balls are disjoint, we can always figure out the center, and so we can always decode in that sense. Right? This is what is called unique decoding, and it's always doable if you have at most delta over 2 fraction of errors. So at least determining how many errors you can fix in theory is just a question of finding the distance of the code. The algorithmic problem, which is not trivial, is we'll find the center efficiently. And that's what we'll call unique decoding. Okay, any questions? There is a slightly more interesting kind of decoding, which is called list decoding. So as we saw, if you have delta over 2 fraction of errors, then these balls are disjoint and you can always find the center of the ball. Maybe the adversary made more than delta over 2 fraction of errors, and let's call it rho, the fraction or the error radius. And maybe it's true that, okay, now there is not just a unique code word in this ball. So now I've switched the diagram a little bit. I'm drawing the ball not around code words, but around the kind of erroneous point that we received, because that's all we actually see. And I mean, you can flip the previous picture to say that up to delta over 2, there'll be a unique code word in this ball around the center that we received. Maybe up to some radius rho, there are some 10 points, so not many more. And list decoding is actually the problem of finding all the points in this ball. And again, we can define a combinatorial problem. Okay, just kind of when are the number of points in this ball bounded by some nice function, and the algorithmic problem, which is give me an efficient algorithm to find. Okay, right. And there's actually a nice function of the distance, just like for unique decoding, we just said that up to delta over 2 fraction of errors, you can always unique decode. For any code, there's a function j of delta, which is somewhere between delta over 2 and delta, which is called the Johnson bound, and I'll write it more precisely later. But up to this radius, for any code, you can list decode in the sense that you can say that the number of code words in this list or this blue colored ball is small, and we'll kind of make precise what we mean by small, but something which we can hope to at least write down in polynomial time. Of course, finding them in polynomial time is a whole other story, and that's a challenging problem, and we'll talk about that throughout the talk. Any questions? Okay, so that's list decoding. This is the kind of problem we'll actually be concerned with in most of the talk. So let's get to this Johnson bound. And this is, remember, for any code, we claim that up to the Johnson bound, which is some function, you can you can prove that the size of the list is small. Okay, so let me kind of parse this function a little bit. So j of delta is some weird looking function. I like to think of it this way. So if you have a code word, and let's say we are looking at distance from 0. So let's think of 2 code words. One of them is 0, the other is non-zero. Our codes are subspaces, 0 is always available. Okay. Then the number of ones minus the number of zeros is 1 minus 2 delta. Okay, in absolute value at least, maybe. And this is what is called the bias of the code, just kind of the unbalance between zeros and ones. And j of delta is a function such that if you had j of delta once, then the unbalanced, or like the bias squared, is equal to the bias of the original. Okay. And there are generalizations when you're not working with code on alphabet 2, where the bias is just kind of 1 minus 2 delta, and so on. I'll not get into that too much. And the Johnson bound, one version of it says that for any code, if you look at the list of radius j of delta from some received x, then the size of the list is small. Small as in n plus 1 here, which is where n is the number of bits in the code. So in principle, you could write down that entire list. If you are actually willing to go a little bit below this j of delta minus epsilon, then you can write this as a function just of epsilon rather than even involving n, but let's not worry about that. Yeah. In general, it can be super polynomial. And I mean, there are codes for which you can go much farther beyond Johnson bound. But this is just, if you're working with an arbitrary code, then yeah, there are codes where after Johnson bound j of delta plus epsilon, the list size is super polynomial. Any other questions? And just to illustrate this, j of delta is kind of something better than delta over 2. I just kind of computed it for some code where delta is close to half, which is roughly what the best you can hope for in a binary code. And j of delta is much bigger than delta over 2. So if you are willing to go do list decoding, you can tolerate more errors. Yeah. Yes, of course. 1 minus 2 delta is, so if you think of, let's say, the distance from 0, so we are just looking at the number of ones in a given code word, right? So let's say the code word has a bunch of ones. Now let's count the number of ones in this. It's at least delta. Let's say it's exactly delta for a moment. So the fraction of ones is delta. The fraction of zeros is, 1 minus delta times n. And the unbalance is this, which is, okay, so that's what's called the bias of a code, which is just kind of the imbalance between zeros and ones. And j of delta is a number such that the bias squared at j of delta is equal to the bias of the original code. That's how I usually think of this bound, and we'll use this property. Okay. But yeah, I mean, it's an explicit function. You can write it down this. Other questions? And we'll use this sort of variation in like this definition in the proof. We'll prove it. Yeah. Other questions? Yeah. Okay. So what do we know so far? List decoding, we kind of defined it. There's actually a very rich theory of list decoding. Venkat is an expert, and this is kind of a nice survey by Venkat, which I find quite nice. Maybe there are kind of more recent ones. And the algorithmic problem of finding the list is often a very non-trivial problem. And in most known algorithms, it requires some sort of algebraic structure, or it relies on some algebraic properties. Not necessarily always, but we have many more techniques available using algebraic structure. And in today's talk, I want to talk about a slightly kind of different way of doing list decoding using optimization algorithms, which works for codes where previously list decoding algorithms were not available because we didn't have these kind of algebraic structures which were used in the previous algorithms. And in particular, what we'll do is actually just prove the Johnson bound. We'll give a slightly different proof via a statement I'll call a covering lemma. And then we'll see how to implement every step in this proof of the Johnson bound algorithmically. So we'll give an algorithm which kind of does whatever the Johnson bound proof is doing. And at the end, when Johnson bound says there is a bounded size list, this algorithm will find that list. Okay. Everybody okay so far? So I'll kind of do it in a way that I'll actually give you the proof of Johnson bound and this some algorithmic relaxation without talking about what code we are working with. Okay. And the technique will work for a bunch of codes. So it's kind of easier to do it this way, write down some property of the code that we will actually need, and then just go and check that this property is available for many codes of interest. Okay. Any questions? Okay, so let's talk about the statement which I called the covering lemma. And yeah, if you Don't take anything else from the talk. If you remember the statement of the covering lemma, I'm happy. It's a really nice, clean geometric statement with a one-line proof, and it's actually very useful. So, okay. And the statement is purely geometric. I mean, I'm not going to use anything about codes in this statement. So let's switch to vectors in real space for a moment. Let's not talk of finite fields for this statement. Okay. So let's think of unit vectors in Rn in dimensional space. And let's think of a collection script f of unit vectors and a single unit vector g. Okay. And as you'll see, this script f is supposed to be a stand-in for your list. This g is supposed to be the stand-in for the center, but let's worry about that later. We have the property that the inner product of g and f is somewhat large, is larger than epsilon, for every f in this set. Okay. This need not be finite. It can be an infinite set even. Okay. Then the same property or a similar property holds for an h, which is not just the sort of, instead of this arbitrary g, which could be anywhere, there is an h which is actually in the convex hull of these points or these vectors. And because it's in the convex hull of unit vector, it need not be a unit vector itself. Its length will be smaller. Okay. And it has the property that h has inner product at least epsilon square with every f in this family. Everybody okay with the statement? I mean, this is true for any notion of inner product, any family of vectors, and so on. So, okay. And we'll just say h covers f. So that's why the name of the covering lemma. Okay. So this h is just a point which in the convex hull, which covers this entire set f. That's how I'm thinking of it. And you see that there's already some sort of square thing showing up here, which we'll use in Johnson bound. Sorry? I think so. Yeah. Okay. So is the statement okay? Nothing to do with codes, just a statement about a collection of unit vectors. The proof is actually shorter than the statement. So, I mean, the first thing we would do, maybe you have a convex combination. Let's say we take a uniform, like we take a convex combination of everything and see what happens. Okay. And the problem with taking a uniform combination or combination of everything is that there can be points which in this set script f, which are like really one point, but they're all very, very close together. And so if I take a convex combination of everything in f, then these points get a lot of weight. Okay. And that's not what we want. We want something which is kind of really well in the middle of it. And so we'll do the next best thing. We'll actually look at the point which minimizes the L2 norm, where L2 norm square is the inner product of a vector with itself. Again, whatever notion of inner product you choose to work with. So we'll look at the minimizer of the L2 norm in the convex hull. And you can check that, okay, if there is a point on the boundary of this, if there is an f which has small inner product with h, then you can change h to h prime by moving a little bit in the direction of that point. It should reduce the norm because you're moving in a direction where the inner product is smaller. So you're moving in an orthogonal direction, almost orthogonal. And again, it's a two-line calculation. You can figure out what is the optimal amount of move just by setting the derivative to 0 for the norm. It's a quadratic inequality. Okay, that's the proof. Nothing more than that. Everyone okay with the statement? Hopefully okay with the proof? Yeah. Sorry? Yeah, so in this, actually, it doesn't need to appear here because h is in the convex hull. Every f has large inner product with g. So every point in the convex hull also has large inner product with g. Okay. So I don't need to worry about g in this. I mean, I'll use this property, but this is actually implied by h being in the convex hull. And it's just, yeah. I'll need to know that this was true to kind of actually get a lower bound on the norm. I can't just get the 0 vector in this minimization problem. Okay. And that's just by Cauchy-Schwarz, right? Because this must be true. So H can't be the zero vector. And you can prove that its norm is at least epsilon. Okay. Okay. Any questions? Yeah, exactly. Then yeah, G is kind of giving you the center of the cap, or it's telling you that they're in a cap. Right. Exactly. Yeah. Yeah, I mean, I also like to think of it as just you pick a sort of combination of coordinate vectors. So you just think of like coordinate vectors in like directions 1, 2, 3, and then which is like a 1 over root 3 times a combination of those. You take a convex combination, which is 1 over 3, which will be your H. So, I mean, which is a special kind of cap because sphere is rotationally invariant. Okay. More questions? Right. So that's the covering lemma. All it says is that if we have G, which has large inner product with everything in F, then there is a H inside the convex hull, which covers them. Good. Let's prove the Johnson bound. And we'll see that we can convert actually every step of this proof into an algorithm. So let's start with what we have. We are given some X. We want to find the list around this X. Okay. Let's transform it into the setup that we were working with. Let's make this X into a G. Let's make this code word Z into these functions F, which where I kind of map a 0 to a 1 in the real space and a 1 to a -1 in the real space. So, and the inner product here, I'm thinking of the expectation inner product, because then I get numbers between -1 and 1, which kind of work well with my fractional Hamming distance kind of. Okay. And you can think of this F as a function or a coordinate vector, whichever you like. Okay. So we have obtained a setup which is at the start of the covering lemma. The conclusion tells me there is an H, which is inside the convex combination of all these Fs which correspond to code words. Okay. And it's in the convex hull. And now let's look at what is our epsilon, or how much correlation or how much inner product we have. So we are looking at a list of radius j of delta. So when I look at x minus z, the number of ones is at least, or sorry, at most j of delta, right? So the inner product, which actually just calculates this bias that I was writing earlier, you can check. If I sort of replace zeros by ones and ones by -1s, the inner product will be just the bias of x minus z. Then, because the number of -1s in this is small, the number of ones is large, the inner product is at least 1 minus 2 times j of delta, whichever whatever was the radius. And so my covering lemma will tell me that this H, which is the point in the convex hull, has inner product at least 1 minus 2 of j of delta square, which conveniently is 1 minus 2 of delta. That's how we define j of delta. Okay. Everyone okay with this so far? Okay. All we did was just kind of took this picture, embedded everything in the real space, and then applied the covering lemma. Okay. And now we're almost done. So first, note that we can assume that the support of this H is of size at most n plus 1, because it's a point in n dimensions. And Cathode theorem tells us that if you have a point in n dimensions, which is a convex combination of a bunch of things, then you can write it as a convex combination of n plus 1 things. Okay. And I'll also say that anything which is not in the support can't be in the list. So the support is small. Anything in the list has to be in the support, so the list is small. Let's check why. So let's say this f sub z is not in the support of H. Let's calculate its inner product. H is a convex combination of a bunch of fi's. Let me write it as summation ci times fi. Inner product is linear. And F sub z is not in the support, so it's a code word which is different from fi. And two code words which are different from each other have small inner product, at most 1 minus 2 delta, because the distance is at least delta. And these CIs sum up to 1, so the whole thing is at most 1 minus 2 delta. But this contradicts what we knew about H from the covering lemma, that the inner product with any F sub z in our list was at least 1 minus 2 delta. So anything which is not in the support is not in the list. Support is small, so list is small. Okay, everybody okay? That's the Johnson bound. All right, and now we'll see that actually this can be made into an algorithm. So yeah.
Any different n plus 1 because of n might have different so everything that is essentially
no, I mean fix one representation. Okay, now you have n plus 1 things there. If you potentially had something else which could have been in a support and in the list, take its inner product, you will get that it's actually not in the list, because the inner product of H is large with everything in the list, not just things in its support. Right? So fix any representation, and anything outside this representation is just not there in the list. Yes, yeah. Okay, more questions? Yeah, it's a convex combination of the list. Yeah, but it's a good point. So if you maybe, notice I actually cheated here. So I actually relaxed this condition to saying that H is not in the convex combination of the list, but in the convex combination of all code words. And even that is fine, because all I needed was this property, that the inner product is small. Okay, so even if instead of finding H in the convex combination of the list elements, where we don't know the list, so it's kind of hard to optimize over the convex combination of the list. If you find an H in the convex combination of all code words, this is still okay. Okay, and yeah, so then we will need to kind of apply this sort of argument that you have, that maybe you have multiple representations. In fact, we can't even optimize or kind of search over the convex combination of all code words. In general, codes are kind of complicated objects. So we'll work with some convex relaxation of the convex hull of all code words. Okay. And we'll solve the same minimum L2 norm kind of optimization problem over this convex hull after embedding in the real space. Thank you. So yeah, I'll actually use these F sub z's interchangeably, as sometimes I'll just say F is in the code because it's just an embedding of a code word. Okay, so yeah, I think after a while it might get a little hairy to keep writing F sub z where z is in the code. So I might say F in the code. Okay, and we will work with the convex, sort of a relaxation of this convex hull, something which we can hope to optimize over. And all we need is to be able to capture this kind of statement that for some code word, either it's in the support or its inner product with H, or this whatever is this relaxed object H tilde is small. Okay, that's all we used in the proof of the Johnson bound. So, and now we'll try to figure out how to find a good convex relaxation. Everyone okay so far? Yeah. No, please. Yeah. Exactly. It's just approximate Cartho-Theoretum. Thank you. Yeah. So if you are slightly below, yeah, you can afford to lose a little bit in this inner product, and approximate Cartho-Theoretum theorem will then give you a support size which is, I guess, 1 over epsilon square or 1 over epsilon, depending on how I'm defining things. Yeah. Okay. More questions? Okay. All I've done so far is prove a very standard bound, which all of you probably know, but it's a slightly different proof. Okay. So now let's get to figuring out this relaxation. And we'll use a set of relaxations, which are called sum of squares hierarchies, or sum of square relaxations, or sum of square semi-definite programs, etc. And we'll get to this in a couple of steps. So let's think what we are trying to find. We're trying to find an H, which is in the convex hull of all the code words. Okay. What is a convex hull? It's or what is a point in the convex hull? It's a distribution over code words, because, well, we just have coefficients which add up to 1. So you can think of these coefficients as probabilities. So So instead of convex hull, we can think of the set of distributions over all code words. You can specify a distribution by writing down all its moments. So you can think of a random variable z, which takes a value as the real embedding of a code word. So it's a vector valued random variable. Okay. And instead of saying, find me a distribution, I can say, find me a random variable. I mean, you can specify the random variable by writing down the distribution. So find me a random variable. And instead of saying, find me the random variable, I can say, write down all the moments of this random variable. All the moments of this random variable are 2 to the n numbers because this is a vector valued random variable. Coordinates are supposed to be 1 or -1. So we are really working modulo the ring like zi square is equal to 1. So, but there are 2 to the n moments corresponding to which subset of coordinates I'm multiplying. And once you write down kind of, there is an obvious kind of relaxation to consider, which is don't write down all the moments. Just give me, let's say, moments of degree up to at most t. Okay? And this is what is called the tth level. I mean, we'll need additional properties. I'll get to them. But this defines the tth level of the SOS hierarchy. Okay? So we'll define this in a little more, I mean, I won't define it very formally, but in a little more detail. Okay. Everything okay so far? Just the fact that we are working with distributions and moments. All right. So let's write a little more. So we'll think of this h tilde as a list of numbers which corresponds to these moments. Okay. And if we have moments for z1 and z2, we can write down a moment for 1/3 times z1 plus √3 times z2 or whatever. So you can write down the expectation of any polynomial if you have the expectations of all the monomials. And if these were actually moments, then if you were to write down expectation of a polynomial square, this must be non-negative. And so this is the condition we'll require. Okay. So formally, the solutions are, I mean, it will be a bit of a mouthful to say all the time list of numbers corresponding to low degree moments linearly extended to polynomials satisfying non-negative expectations for square. So I'll not say this all the time. This has a name. It's called a pseudo expectation. Okay. So a solution to this relaxation will be a pseudo expectation. Why pseudo? Because, well, we think these are moments according to some distribution. All we are given are numbers. We don't know if there is an actual underlying distribution. In fact, we'll try to see, and it satisfies some properties. So it kind of smells a little bit like a distribution, but we don't know for sure. And the question is, what can we do with these limited properties that we have available? Any questions? So then we can do a little bit of a switch, and instead of thinking of this as a list of numbers, because we are going to also write down expectations or moments of polynomials by just kind of linearly extending this and taking linear combinations, we can think of a linear operator. We can think of e tilde, which takes a polynomial, gives me a real number, which is supposed to be the moment of the polynomial, at least for degree t polynomials. And this is called the pseudo expectation operator, which is the solution to a level t relaxation. We require linearity. We require non-negativity of squares, at least when p square has degree at most t, where this is well defined. Okay. And there's some normalization condition that e tilde of 1 is 1. So if it's scaled correctly. Okay. That's what we will think of as a solution to an SOS relaxation. These can be found modulo some sort of bit complexity checks. These can be found in time n to the order t. We'll not need to worry about how to find them in this talk. Let's assume that what our semi-definite program or some sort of relaxation, when we solve it, what it gives us is this. We'll actually also require, or we can require, additional conditions that e tilde of q is equal to 0, which is a linear condition on the collection of moments. Remember, we are not trying to solve for q. We are trying to solve for e tilde. Right? So e tilde is just a list of numbers corresponding to moments. E tilde of q is just a linear combination of those things. And we are saying some linear combination of this list of numbers is 0. Okay? So, q is some other polynomial we might choose, which is problem dependent. So the thing is, everything I wrote here as a condition on e tilde is independent of what problem we are solving. We'll need to introduce something about the problem. So I'll not get into this too much, but yeah, we can add additional conditions of this form. Okay, which is like, so P and Q are some polynomials in this. Yes, so we will optimize the norm. Well, okay, so I kind of said H tilde is this entire list of numbers. If we were looking at the norm of H, it was actually, because I defined things in terms of expectation, it was expectation over I. So we will analogously optimize the norm, which is which will correspond to just the first moment. So we'll not square the second and third degree moments, and we'll need them for reasoning about the solution. But what we'll optimize is this. Okay. Okay. Yeah, I'm kind of cheating a little bit. I said this relaxation can be solved in n to the order t. Actually, I can also optimize this norm in n to the order t, and it also still has the covering properties. I'll not prove them. The proof is the same. You just kind of move in the direction where you don't have correlation. But let's see what we can do with this, or let's see how we can reason about these solutions. Okay. Everyone okay with thinking of a solution as this operator E tilde, which takes polynomials, gives me real numbers, has these properties? Yeah. Okay. So how do we reason with these sort of solutions? Remember, these are the only properties we have. I mean, I talked about adding another property, but let's not worry about them. These are the only things we have. So we are given E tilde, and we want to prove something about the solution we got. That's how we'll say that, okay, we solved this relaxation, the solution is kind of nice, it solves my problem, it gives me something nice, etc. And when I say prove a property, let's say I want to prove an inequality of this form, where E tilde of Q of Z, where Q is some polynomial I choose, is greater than or equal to 0. These are the only things I have. So I can prove it if I can write this Q of Z as a sum of squares of some PIs. Okay. Because for each of them, E tilde will be non-negative, and by linearity, E tilde of Q of Z will be non-negative. And so that's basically how we reason about E tilde. Whatever property we want to prove, we think of it as E tilde of Q. We try to express this as a sum of squares of polynomials, and then we use these properties. Okay. And the key is to find the right Q of Z, which helps you reason about whatever problem you have at hand and kind of talk about the algorithm. Okay. And this is a whole theory. It's called so-called proofs to algorithms paradigms, that when you can prove properties this way, you can get algorithms. So you can reduce the task of designing an algorithm to just kind of expressing some Q as sums of squares. And that's why it's called the sum of squares hierarchy, sum of square proof system, which is actually a dual to the convex relaxation. And there's a nice book by, not sure you can read the names, but Noah Fleming, Pravesh Kothari, and Tony Patasi, which gives lots of applications to this to statistical problems. I don't know kind of previous works on coding theory, but yeah, this is some extension to coding theory. This talk is really not sponsored by now publishers. I just kind of like these books. Okay. Right. So now, what are the kind of inequalities we want to prove? Let's see. We said we wanted something about the distance of a code, like two code words. Something is not in the support, then it's far, and we wanted to prove this for H. Okay. What is the distance of a code? And now I've kind of switched to thinking of F and H in the code rather than F and H as real embeddings of some code words. I'm kind of overloading this notation, something in C. It's really it's in the real embedding of the code. Okay. Now, when you have two code words, either they are equal, which means their distance is 0, or they are far, which means the distance is at least delta. Little delta is what I'll use for the distance of the code throughout the term. Okay. Okay. What this means, when they're equal, the inner product is 1. They are plus minus 1 vectors. We're looking at the expectation and product. So it can be at most 1, and it attains that value. Or the inner product is less than 1 minus 2 delta because they are far from each other. And that's a quadratic inequality in F inner product H. Okay. F inner product H itself is linear in the entries of H. Okay. So we have this inequality, which is the product of these two forms is greater than or equal to 0. Okay? That's the quadratic inequality which expresses the distance of a chord. Okay? Either this inner product is greater than 1, but where is it going to go? It's 1. Okay? Or it's less than 1 minus 2 delta. Okay. Everyone okay with this inequality? So we'll basically prove this one inequality. And as we said, all we need to do is to kind of write our inequality as sum of squares. So our job will be to say that we can express the distance of a chord as a sum of squares inequality. And actually, I'm cheating a little bit. I'll need some problem-specific things. I'll mention that in a minute. But we would like to show that our convex relaxation satisfies this inequality, which is what I'll think of as the notion of distance for solutions to this relaxation. Any questions? So we want one inequality. Actually, it's a family of inequalities. We want this for every f in the code. Because remember, we don't know what are the f's in the list that we are reasoning about. This was true for every f in the code. We've replaced this h by this formal variable z. So yeah, should emphasize this again. I mean, there is no z. The z is really just a formal variable which is kind of used to write down the moments and so on. So I say expectation or the pseudo expectation of z1, z2. But what we get is the pseudo expectation of z1, z2. We don't get z. Okay. Any questions? So this is the inequality we want to talk about. Okay. And let me say a little bit about how to use this inequality and actually get a decoding algorithm out of it. So remember, what covering gives us is this, and if you believe me that the kind of covering argument can be extended to this convex relaxation, it gives us this inner product of h tilde with f, which is this. Again, I only look at the linear moments. I don't care about the others for writing inner products. It's at least 1 minus 2 delta. And suppose we also have we have this product, or we have this quadratic inequality. And moreover, let's say instead of the expectation of a product, we have a product of expectations or pseudo expectations. Okay. And let's say these are equal for now, or roughly equal. Okay. Then this one says that E tilde of f in our product z is either greater than 1 or less than 1 minus 2 delta, but we know that it's more than 1 minus 2 delta, so it must be greater than 1. Yes. Yeah, so suppose we do that. I mean, that's what I'll do in the second half of the talk. I mean, this is code specific, so I'll actually use properties of the code to do that. But suppose we could show this. Okay. And moreover, suppose that actually we could split this as a product of expectations. Okay. Then we have these two things. We have from covering that the E tilde of f in our product z is large. And this inequality which says that either it's smaller than 1 minus 2 delta or it's larger than 1. Then the only choice is that it must be larger than 1. But it has to be equal to 1 then. And so I find f. This the reasoning I applied to things in the code, so I can just read off code words from this E tilde. You might notice there is a problem. I mean, okay, there is one E tilde. How many code words can I read out of it? So here I'm just kind of saying f is equal to this. So yeah, I mean, the problem is in some of this squiggly equal to, and I'll mention that in a minute. Okay. But at least if we were in this dream scenario, this sort of decoding would work. We just get these numbers E tilde of z, which because they have inner product 1 with a plus minus 1 vector, they should be plus or minus 1. So I can just use them to read f. And that's my decoding algorithm. Okay. This f was something supposedly in the list so that it satisfied this inequality. Yeah. Well, okay. Yeah, so this squiggly is problematic. We'll get to that. Okay. But yeah, at least if I had this very hypothetical scenario, then we are done. Is that okay? Okay. It's actually not so bad. So first, I mean, even in this squiggly, I'll have to preserve this squiggly equal to. So I'll not get equal to 1, but almost equal to 1. That's good enough because I can write down this vector of real numbers E tilde of z1 to E tilde of zn. They're very, very close to a plus minus 1 vector. So I can randomly round them. I can just kind of choose a value for each of them based on some threshold, and I'll get a plus minus 1 vector, which is still very, very close to f. And then I can apply unique decoding. Because this, whatever vector I get by rounding these, I can think of as a 1 minus 1 or a 0, 1 vector, and then I apply unique decoding. Okay. It's still, I mean, whatever is the error in this quickly, let's call it, and I can make it arbitrarily small, suppose, then I can get unique, I can reduce this problem to unique decoding from whatever very, very small error I want. So if you have unique decoding for your code, this will give us list decoding. Okay. There's still a problem. So this squiggly is still an issue. Sorry? Sorry? No, I mean, we need to do a little. So as you said, these random variables could be correlated. I mean, again, in this pseudo expectation sense. But there is actually a generic argument which is used for CSPs in Barak Raghvendra Stoyer and Gurswami Sinop, which says that roughly conditioning on a few randomly chosen coordinates of z, and I'll have to define what conditioning means, but it's sort of what you think it means, which is you write down e tilde of some polynomial product with the stuff you are conditioning on and divide by e tilde of the stuff you conditioned on. So there is kind of a notion of conditioning each e tilde, and if you condition it randomly on a few of these z1 to zr, it breaks correlations and you get this inequality. And the way the algorithm will actually work is, so this conditioning might also affect this property. No. So this, you need expansion properties when you're trying to say that there is some local correlation and then you want to transfer it to some global correlation. This is already global. I'm just looking at, think of this f as all one. So it's just the sum of z's and the sum of z's here, right? So it's just, you get every pair zi, zj when you kind of expand out this inner product. So in this conditioning argument, this is only talking about global correlation. You can use it directly. Don't need expansion for this. Okay. Okay. And I mean, the argument is that, okay, sort of, you can see how much does the variance of this expression reduce when you condition a randomly chosen coordinate. And that's something times the covariance of these two expressions. Okay. And so if the covariance is large, the variance will go down when you condition. It can't keep going down forever. It's non-negative, so it will stop. Conditioning will also change this property because, well, there is no reason it should preserve this. But then we can say that, okay, this will happen with high probability. With some probability over conditioning, this will be at least somewhat large. We can use some very weak Markov. And so what will happen is that for every element of the list, there will be some probability that a conditioning will preserve this correlation and will break, it will preserve this inner product and break these correlations. And so all we do is condition on some stuff. With some probability, this is preserved for a particular f in the list, and we are in this dream scenario. And we find that f using unique decoding. We repeat this process. This happens for some other f. Okay. And you can show that, yeah, this way you can just kind of go over all sorts of conditionings. The time for going over all conditionings is no more than time for solving this relaxation. So you can just go over all of them. And so that will be the algorithm. That's the generic algorithm. Not all the code words. We like the size of the code is exponential, so that we can't afford. Okay. We solve this relaxation, e tilde. Then we condition on few randomly chosen positions. So I1 to IR, okay, which are just bits. Okay. So we condition on this pseudo expectation by some notion of conditioning of the bit I1 is 1 or the bit I2 is -1. There are only two choices. So there are n to the R possibilities for this choosing these positions. There are 2 to the R possibilities for choosing the values. This will be, the whole thing will be time n to the order R. And actually conditioning requires that this R is at most the degree T of the pseudo expectation. So we'll spend time n to the R, which is less than n to the T, which took us in the first place to solve the whole thing. Okay. So this whole thing can be made deterministic. I mean, there's nothing random about this algorithm. This also, this threshold and all can be made deterministic. So, okay. So this I'm kind of hiding a little bit just because the calculations of this conditioning somewhat standard by now, and also it doesn't really kind of add to the conceptual argument. So this is our framework. All we need to do is to have an SOS proof of this inequality, or sort of make sure our our relaxation satisfies this inequality. And then the rest of the scheme can be made to work. Okay? And what we do is we reduce it to unique decoding to whatever arbitrary precision we want. Any questions? Once. So we apply it once to solve this convex relaxation with some minimum norm condition on E tilde, this condition actually. Okay. And then we just go over all conditionings. That's all. So we don't apply it iteratively. But that's a good point. This is a difference from some of the previous algorithms. I think Prahlad, Irit, Inbal, Yuval, and Amnon had a paper where they were using semi-definite programs to list decode some codes, and there you solve a semi-definite program, then kind of change the instance a little bit, then solve another semi-definite program. It's iterative. Here we don't do that. We just solve it once, and then we just go over all conditions. Thanks. Yeah. Good. That's something I don't like to talk about in polite society, but it's a it will be actually something that will dominate the running time. And so we'll talk about it in terms of codes. But if we want to reduce this conditioning, this sort of correlation or this quickly to some error eta, then the number of coordinates will be 1 over eta square, which will mean the running time will be this, or maybe eta to the 4, but it's sort of some polynomial. But this is pretty bad in terms of running time. It's not a great running time. Actually, the numerator will also be a problem, and that we'll see kind of. I'll need to specify a particular code to say what the numerator is. But yeah, the number of coordinates I need to condition will dominate, will kind of give me the running time cost, and then we'll talk about it later when we specify codes. More questions? Okay, all we need is distance. Right? So then we just need to prove this one inequality. And we have one rule to prove inequalities, right? Stuff as sum of squares. So that's all we need to do. And actually, I cheated a little bit. So remember I said with this sort of star, like specifying the side effects of a drug, that we can maybe write down some additional conditions which are problem specific. So we can add constraints which are, let's say, E tilde of Q is equal to 0, where Q is something coming from the problem. Because whatever conditions we wrote on E tilde actually had nothing to do with our problem. We'll need to encode some stuff about the problem. So it suffices to actually have this polynomial P, let's call this P. It suffices to have this polynomial as a sum of squares plus a sum of the stuff which we know is going to contribute 0 to E tilde anyway, because when I calculate E tilde of the whole thing, this will vanish. This will be non-negative, so this will be non-negative. Okay. So actually, we have this one other rule which sort of encodes problem-specific information. All right. Think we can take maybe a 10-minute break at this point. We're at the 1 hour mark. And then, so this is our framework. All we need to prove is this one inequality. And then in the next half, we'll talk about kind of different families of codes and see how to prove these sort of things. Okay. All right, let's continue. So far, we just said our goal is to prove this one inequality, but we didn't really use any information about the codes we are working with, etc. We just kind of gave this framework, and now we'll see a few applications. So now I'll talk about specific codes, in particular code families based on expanders, and show is maybe too much of a stretch, but kind of give a sketch of why the proof of distance can be written as a sequence of inequalities which are just about sums of squares. Okay. 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 And is everybody still comfortable with the fact that all we need to prove is that this kind of an inequality is a sum of squares inequality? Yeah. Okay. So now that's our task for the rest of the talk. You can forget everything about convex relaxations. You can forget things about some of those squares inequalities, except that just kind of think about writing polynomials as sum of squares of polynomials, but that's all we need. Okay. And everything else will be taken care of by the kind of reasoning we did a few minutes ago. Okay, let's start. So before talking about expander-based codes, let me define expanders. And these are things which Akash defined yesterday, Prahlad did too. Let me just reiterate the definition one more time because it's nice. And we will restrict ourselves to thinking of, let's say, deregular graphs. Okay? And we'll write down a matrix, which is the adjacency matrix of the graph, where an entry is 1 if there is an edge between I and j, 0 otherwise. We'll normalize it by 1 over d. And once you do this, you can prove that its eigenvalues are at most 1 in absolute value, because the sum of entries in a row is at most 1. And then by Gershgorin, the eigenvalues are bounded. And we'll say, and the top eigenvalue you can also prove is actually equal to 1, because if you look at the eigenvector, which is just all ones, and normalize it maybe, then you can check that sort of when you multiply that vector, you'll just get the sum of every row, which will be just 1. So this is an eigenvector with eigenvalue 1. And the second eigenvalue, if it's at most lambda, we'll call this graph a lambda expander. Okay. As Prahlad said yesterday, there are many other definitions for graphs. They are sort of all roughly equivalent. We'll stick to this one. It will work well with our semi-definite program and sum of square kind of ideas. Okay. Any questions about the definition? So this is something we've all seen multiple times, but I just want to point out that the first eigenvalue is 1 and the eigenvector is just the all ones vector. And Prahlad also kind of talked about expander mixing lemma, which is some version of another definition of a possible definition of an expander. And let's just write kind of a one-sided bound of an expander mixing lemma, which is a statement. It says, I mean, it's usually stated in terms of subsets of vertices in a graph, but you can think of a function on the vertices of a graph where the value of the function on the ith vertex is 1 if it's in your subset and 0 otherwise if you want. But you can write it down for functions in general. And expander mixing lemma is a statement which will say, if you look at the f of inner product A with A times G, then it's upper bounded by the inner product with the largest eigenvector, which is the all ones vector, plus some error term, which is roughly lambda times, which is equal to lambda times the norm of f times the norm of G. I'm sorry? No. So I'm actually working with this inner product, which is expectation. So yeah, I'll say, but no, I think it's just this. We'll check it. But yeah, there'll be some 1 over n which will show up when I try to write this matrix as an outer product, but not in this version. Okay, and let's even look at a special case where f is equal to g. And I mean, you can write down that case yourself, so I don't need to spell it out. And the fact that I want to point out is that expander mixing lemma is a sum of squares inequality, or it's some inequality, right? It's an inequality between f and g, and then in fact, let's think of this special case, which is an inequality in this function f. Okay, and I claim that this inequality, which is some degree 2 polynomial in f, can be written as a sort of the difference of the right hand side and the left hand side can be written as a sum of squares of polynomials. Okay, so you can prove expander mixing lemma as a sum of squares inequality. And actually, we'll see in like the proofs of all the codes that we were, just apply the expander mixing lemma. So once we have this, we'll be halfway there. Okay. So let's spell it out in a little more detail. And yeah, I am working with the special case of the expander mixing lemma where f is equal to g. You can get to the general case by one application of Cauchy-Schwarz, and Cauchy-Schwarz you can check is also sum of squares. If you remember your kind of maybe high school proof of Cauchy-Schwarz, where you look at some linear combination of f and g and then say that the norm square is non-negative and then optimize over the coefficients. Okay, so let's stick with this case. And I want to prove that this is a sum of, like the difference of the right hand side and left hand side is sum of squares. Okay. So let's think of this matrix, which is the adjacency matrix minus the all ones vector outer product with itself. So 1 times 1 transpose. Here I will need this normalization of 1 over n. So you can check that when you multiply this matrix with the all ones vector on both sides, you will get 0. Okay. And since this is an eigenvector of both these matrices, and this is rank 1, all the other eigenvectors will just be the eigenvalues of A. And we already assumed that the second eigenvalue is upper bounded by lambda. So, and I mean second in the sorted order. So every other eigenvalue or every remaining eigenvalue of this matrix is upper bounded by lambda. So if I subtract this matrix from lambda times identity, I get some positive semi-definite matrix because all its eigenvalues are non-negative. Right? Okay. And a positive semi-definite matrix can be written again in terms of its eigenvectors, let's say ui and ui transpose, and its eigenvalues which are non-negative. So this is the spectral decomposition of a positive semi-definite matrix. And if we write it down and take an inner product of f with this matrix, we get a sum of squares expression, because at least if we take an inner product on both sides. But this is nothing but the inequality we wanted to talk about. So this f inner product p times f is exactly, sort of this 1 over n goes away because I'm working with this funky inner product, which is in terms of expectations of coordinates. Okay, and then you can check that the normalization is such that this 1 over n will go away. And the f inner product f is exactly just the difference of the right hand side minus the left hand side. And we have proved that that's a sum of squares expression. Okay, so any proof which uses expander mixing lemma is at least safe in that step. Okay? That step is just proving some inequality by writing it as a sum of squares of inequalities, and that is the sort of legit thing that we are allowed to do. Okay. Questions? I mean, really, we should think of positive semi-definite matrices and sum of squares as kind of the same thing. In fact, that's how you actually solve these relaxations, by optimizing over positive semi-definite matrices. Okay. I will actually need bipartite expanders. So let me define that just as a slight extension of the concept of an expander. So we'll think of a graph which is bipartite with two sides, which I'll call L and R. Let's say they're both of equal size, and both have vertices on both sides have degree exactly d. So it's a biregular bipartite graph. And yeah, I'm writing down a matrix which is not quite the adjacency matrix. I'm only writing down the rows corresponding to vertices on the left, columns corresponding to vertices on the right. I learned on Wikipedia that it's called the bi-adjacency matrix. So I'm writing down the bi-adjacency matrix, normalizing by d again. This need not be a symmetric matrix. So we'll talk about singular values, and we'll say this bipartite graph is a lambda expander if the second largest singular value is at most lambda. You can again check that the largest one is 1. Singular values are non-negative, so I'll not need to worry about signs. Okay. Everybody okay with this definition of an expander? Okay. And now we'll finally talk about some kinds of codes. So one code family I want to mention is so-called expander codes, or expander-based Tanner codes. Okay. And these are codes where I think of the bits of the code as sitting on the edges of this bipartite graph. Okay. So each xe, so for every edge e, there is a bit xe. Okay. And then I can collect the d bits sitting on sort of on the neighborhood of a vertex, either on the left or the right. I'm going to call them x sub l or x sub r. These are collections of d bits. Okay? So I can think of them as in this little vector space of d dimensions. D is to be thought of as a constant in this. Okay. Just enough that we can get a expander bipartite graph. And as Prahlad said yesterday, you can get good expanders even with very small values of d, and d equals 3 is some kind of an expander. And if you want more precise expansion, then you can take d to be 1 over lambda square and still get things. Okay. So, and we'll have some little code which is sitting in this d-dimensional space, a constant dimensional space. If you want, you can think of it as a kernel of a matrix in F2 to the d, but it's some subspace of F2 to the d. Okay. And the full Tanner code is defined by all collections of bits that I can write on the edges, such that when I look from the left vertex, what I see in the neighborhood of that vertex, just these d bits, belong to this little code. And because I can write it as a kernel of a matrix, I just mean this. Yeah. Or what I see from a right vertex, this x sub r is just a string of d bits. It belongs to this little code. Okay. And I'll require this for all left vertices and all right vertices. And a set of bits on the edges which satisfy these sort of properties or these sort of checks sitting on the left and right vertices will define a subspace because it's just defined by linear conditions over F2. This is what I'll call my Tanner code. It's not my Tanner code, it's defined by other people. In particular, this construction is due to Zemmour, but okay. And this code also has a nice property that these checks are what are called LDPC. These are low density parity check codes. We just like parity check is just summing a bunch of bits of the code word and seeing that the sum is equal to 0. Each row of this matrix H is of size at most d because it's sitting in d dimensions. So each of these checks is sort of like you sum at most d bits, see if the sum is 0. You have some subsets of d bits corresponding to the rows of this H, which you check. Okay. And we define it by saying another way of saying is that the local views at any vertex belong to this little code C0. Is the definition okay? Yes? No? All right. So the full code is actually on a much larger number of bits, d times n bits, which is the number of edges in this graph. Okay. All these checks happen in this little code, which is in some constant dimensional space. Okay. There's a nice history of these codes. So I'll kind of, because it's a tutorial, I'll also talk a little bit about the history. It's and LDPC codes, at least I think I might have stolen this from a survey by Venkat. So it's but okay, I'll take blame for any errors. So yeah, please, I should do my research. But from what I know, there was kind of introduced LDPC codes were introduced by Gallagher in '62 in sort of random collections, and Tanner defined graph-based codes and which could be corrected from adversarial errors, not just random errors. And the fact that they could correct errors or the distance of the code, the proof was based on the girth of the graph, which is the size of the smallest cycle. Expansion of these graphs and using them for construction of codes was pioneered by Sipser and Spielman, which was a construction which is canonically referred to as expander codes, which were beautiful code constructions which came with linear time encoding and decoding algorithms, so they were super fast. And the proof of distance was based on the expansion of the underlying graph. And the bipartite version with a simpler parallel decoder was given by Zemmour. And yeah, I mean, there are lots and lots of other things in this history I'm skipping, but otherwise we'll be here and I'll go over the times of all the other speakers. Okay. There are also nice generalizations of these. So these constructions are very robust. They kind of lead to all sorts of interesting properties. So you can work with constructions where these edges are labeled by real numbers. You can check some properties of some real subspaces on these left and right vertices, and these give you so-called codes over reals, which have interesting properties in terms of what the L1 and L2 norms of points in this subspace look like. The kind of expander codes on steroids, or sort of the expander codes 2.0, has led to a lot of recent breakthroughs, in particular constructions of locally testable codes and recent constructions of quantum LDPC codes, which require somehow lots of expanders squished together by some stitched together by some high dimensional construction, which is called a square Cayley complex. I'll not get into that, but just to say that this construction is has lots of nice generalizations. Okay. Again, an abbreviated history of decoding expander codes. So I already said Sipser and Spielman gave a linear time unique decoding algorithm. And this was sort of a combinatorial algorithm, and a cleaner version was given by Zemmour, which can be implemented in a parallel fashion. Feldman used convex relaxations to decode these codes, still unique decoding, and it's called LP decoding of LDPC codes. And there are also later papers which kind of give decoders based on message passing algorithms, which can be thought of simulating the LP, etc., etc. Again, this is a very abbreviated history. There are lots of work I'm skipping. To the best of my knowledge, there was no list decoding algorithm for these codes, and there were list decoding algorithms for a different kind of errors, which are called erasures. So the adversary kind of corrupts some bits, but tells you that the first, third, and 15th bit are corrupted. And so you might as well just kind of erase them because they're corrupted. You don't learn anything from them. In that case, the question is not really polynomial time decoding, but really linear time decoding, because I tell you that, okay, here is some point in a subspace. I'm telling you all the other coordinates and not telling you the first, third, and 15th. You can find those by Gaussian elimination because the number of coordinates is large enough that you can actually find any missing ones by Gaussian elimination. So polynomial time decoding in the case of erasures is just Gaussian elimination. The interesting thing is to do it fast, and these papers give linear time decoding from erasures, so list decoding. Okay, and so the Gaussian elimination proof, by the way, also works for list decoding. You just get a subspace as the list, right? Okay, so and what we'll do is apply this kind of framework we developed in the first half of the talk to give a list decoding algorithm for this. And actually, we've already given the algorithm. We'll just sort of verify that we have. This is in joint work with Shashank and Fernando. We give list decoding algorithm using semi-definite programs or these sum of squares relaxations up to the Johnson bound, J of delta. More correctly, up to J of delta minus epsilon for any epsilon. Okay. And I mean, what we need to do is just kind of observe that the proof of distance is actually a set of sum of squares inequalities. And then we've already done the work in the first half, which says that once you have sum of squares proof of distance, you get an algorithm out of it by this kind of conditioning, doing unique decoding, and so on. So we reduce it to unique decoding up to an arbitrary small error radius. But there are unique decoding algorithms. I just mentioned them. So we can then apply one of those at the end. Okay. All right. And the proof of distance is actually essentially just expander mixing lemma. And expander mixing lemma, we already said, is SOS. So it's not going to be something too difficult, but let's just maybe observe what the proof of distance looks like. Okay. Reminder on the code, we have bits on the edges, local views, which are sort of size D on the left and right vertices, which are supposed to belong to this local code C0. Okay. And we want to prove, let's say, for two code words, actual code words, that if you have X and Y, that the distance must be large. X and Y must be far from each other. Okay. And the distance is just this, which is I go over all the edges and see on what edges do they differ from each other. Okay. And the fraction of edges on which they differ from each other is their fractional Hamming distance, which is what I was working with. And it will be convenient to define these two functions where on the left and right vertices. So let's think of f of L as as the indicator whether the local view sitting at the vertex L of the code word X differs from the local view of Y. So there are D positions I see when I sit at a left vertex. If they differ in any position, this indicator is 1, otherwise it's 0. Okay. So it's just seeing if any of these D positions differ in X and Y. Analogously for G, so I'm going to define a local view of the right. And the proof of distance is actually just two inequalities. Let's write one of them. So if I have an edge, which is, let's say, on left endpoint X and right endpoint Y, left endpoint L and right endpoint R, then if X and Y differ on that edge, then either the left view at L is different from a sort of between X and Y, or the right view at G is different, right? Because we know this one point is different. Actually, both are different, right? So, sorry. Yeah, so both F and G will be 1 on sort of when I write down F of L times G of R, because I know that on this edge L comma R, X and Y differ. The local view of L is different, the local view at L is different, and the local view at R is different. Right? Because this edge kind of gives you a common certificate for both. We apply an expander mixing lemma on this. You can think of this as F times A times G if you want. It's like going over all edges is the same as multiplying F with A times G. An expander mixing lemma will tell us that this can be upper bounded by the inner product of F with the all ones function, which is nothing but the expectation of F and the expectation of R, times the norm, which will be expectation of F square, but F is a 0, 1 function, so expectation of F is expectation of F, sort of F square is F. So I get this sort of an expression. Yeah.
The indicator of the same thing, but they just sit on the.
Yeah, they're just they're the same type of object, just on sitting on left and right. Yeah. The local view, if the local view is different, they're 1, otherwise they're 0. No, XL, not XE, XL. Sorry, my L and E looks. So yeah, so F is a function on vertices. So F is a function, and F of L is equal to 1 if there exists an E incident on L such that XE is not equal to YG. Right? So this can be written in a sort of more succinct way as X sub L is not equal to Y sub L. Okay. Yeah, sorry, my L and E looks the same. So my apologies. Okay. And let's call this product of expectations mu. So I just get that the distance is at most mu plus lambda times square root of mu. Okay. And remember, all I used was the expander mixing lemma, which I've at least for a special case, I've claimed that it's SOS. I'm using the more general case, and I can prove that with Cauchy-Schwarz after the talk if you want. Okay, so that's one inequality. The other inequality is that if you have one edge that is different, then a lot of edges should be different. Because what I see at a vertex is a code word of this little code C0. Right? So if I look at a vertex L, and if I see a difference, then I should see a difference in delta C0 fraction of the edges. So you will get that the distance should be greater than equal to delta C0 times the expectation of F of L, which is the fraction of coordinates where X and Y differ in their left views. Same for the right views. And I can take the geometric mean of these two, so I get this. And again, here, frankly speaking, I'm using the AMGM inequality, which is also sum of squares, because AMGM is just saying that okay. So I used expander mixing lemma, which is the sum of squares inequality. I used AMGM, which is the sum of squares inequality. You compare these two, you actually get a bound on the distance. So you can solve a quadratic inequality for mu and plug it back in, you'll get a bound on the distance, on the distance between X and Y. That's the proof of distance of these codes. The only thing we used were expander mixing lemma and AMGM. Both are SOS. The whole proof is a sum of squares proof. Okay, I'm cheating a little bit because I'm kind of defining these functions f, whereas what I wanted is SOS in the variables corresponding to the bits of the code, which are edges. This is SOS in these entries of this f. But f is a low degree polynomial because it's actually just depending on values of d things. So these are things which are proofs which are sum of squares of degree d polynomials. Yeah, that's it. Okay. Sorry? The load density is important. D equals constant is important. And this will be the kind of embarrassing part, what the question Ramprasad was asking actually. The conditioning will require us to kind of pick the coordinates that we need to condition if we kind of go through this kind of global correlation argument to have something like 2 to the d coordinates to condition on. So the running time of the algorithm will be something like 2 to the d divided by eta, okay, polynomial in that quantity, which is, sorry, n to that. Yeah. This is the number of levels of SOS. And it's the number, right? So it's certainly not a linear time algorithm. It's very, very far from it. Okay, but it's a polynomial time algorithm for a very stretched definition of polynomial. Okay, but it's a framework, and you kind of generically get a decoding algorithm. All we needed to verify was that this proof of distance is SOS, and that's it. We were done. Okay. There are lots of things you can do to kind of extend this. First, as I said earlier, there's nothing special about 2. You can do it for any kind of alphabet size q. Fix finite alphabet. There will be a dependence on the alphabet. It will be q to the d. So, but any constant size alphabet. There's also this nice distance amplification construction of Allen, Edmonds, and Luby, which kind of takes a code and kind of again passes it through an expander to improve its parameters, and it's used in lots of constructions. And usually, what you need is that you start from some code. You need some strong properties for that code in terms of decoding, something slightly stronger than list decoding. And you kind of get this code with nice parameters which still has list decoding. In this way, you can actually reduce it to unique decoding of the starting code. So you don't need strong properties. You can just say start with some unique decodable code, run it through the AEL construction, and then you get a nice list decodable code with optimal parameters. And you can reduce the list decoding of the new code to the unique decoding of the original code. Okay. The caveat is that the running time of the reduction is that. Okay. You can also list decode these locally testable codes, which I said are kind of fancier expander codes. So it sort of also applies there. You can also kind of apply this framework to talk of other coding constructions. So in particular, for example, a breakthrough construction of Tashma from 2017, which again is a way of improving codes. You start with something and improve it to get really good parameters. And this was a construction of so-called epsilon balance codes or optimal epsilon balance codes, where instead of epsilon balance, let's just think of a code with distance half minus epsilon. So it's a binary code. The distance can be at most half. And so it's very, very close to half. And the rate of the code or the kind of number of code words you get is kind of close to optimal. And the way this is constructed is actually by kind of taking walks on an expander graph. So what you do is you start with some other code, which is thought of as in the space of vertices of this graph. And you obtain a new code word where there is 1 bit for every walk, okay, by kind of writing down the bits of the old code word on the vertices. And when you kind of take a walk, you sum up all the bits that you see in the walk. Okay. And this is a bit corresponding to the walk. So there is 1 bit for every walk. Okay. And this is, I mean, if you think about it, it's just multiplying a matrix with the vector x, where there is 1 row in the matrix for every walk. Right? So it's just, it transforms the subspace to a subspace. Okay. And if you start with a good code, C0 with somewhat nice parameters, you get basically an optimal code with this sort of distance using this construction. I mean, I'm hiding a lot. It's not just any expander. It's actually a very cleverly chosen collection of walks on a very cleverly chosen expander, but I'll not get into that detail. Okay. Okay. And there is a recent result of Richardson and Roy, which again gives a decoding algorithm up to the Johnson bound for Tashma's code. Tashma's code did not come with any decoding algorithms, even unique decoding algorithms. And their work gives optimal list decoding algorithms up to the Johnson bound. Uh, I don't know if it's optimal. I don't know if Johnson bound is the right limit for this particular code, but in general codes, it's the right limit. Uh, and I mean, in our reduction, okay. And this is based on using a slightly earlier framework for list decoding using sum of squares developed in one of our earlier papers with Vedat Levy, Fernando, Dylan Quintana, Shashank. And we can now view it in our new framework, which we just defined in the last hour. So we can actually still view this result also as an instantiation of this proof to algorithm framework. All we need to know is that the proof of distance for Tashma's codes is sum of squares proof. Okay. And actually, Richardson Roy had an earlier paper where they explicitly gave a different distance proof for Tashma's codes using expander mixing lemmas. We already saw expander mixing lemma. It's just expander mixing lemma combined with an induction. We already saw expander mixing lemma is SOS. So this is an SOS proof. And actually, if you stare at Tashma's original distance proof, it's also SOS. So you can just kind of apply the previous framework. We have a proof of distance, which is sum of squares, and then we get a decoding algorithm. Okay. So I'll not get into this because the proof of distance, it is sum of squares, but it has a few inequalities to write down, and it's a bit complicated. Okay.
Somehow it can be written in a way where the number or the depth of the number of inequalities does not depend upon parameters like
Depth doesn't matter. So it's just as long as you're using sum of squares and inequalities, you can use any number. They all have to be bounded degree. Everything you use is bounded by the degree. So I mean, really not too much you can do. It's just like there's only so many polynomials with a degree.
that is the
Sorry?
induction that degree might be going up.
Yeah, so the degree needs to depend on the length of this walk. But the code size or the block length also depends on the length of this walk. So it's, yeah, I mean, okay, no, the degree grows worse. But yeah, I mean, it's true for even the previous algorithm. So, I mean, so far we don't know something where the degree of SOS doesn't blow up with the length of the walk that way. Yeah. Okay. We know of an algorithm which does unique decoding and some kind of list decoding, a weaker one, in almost linear time, which will be my next talk actually. But we don't know how to go to the Johnson bound using that. All right. So, I mean, yeah, I'll stop there. That's I'll not go on for too much more. There's some kind of issues to address, which is one, as I already said, SOS. It's like a first algorithm for the problem. It's not usually the last algorithm for a problem, or it should not be. So, I mean, it's a good way of knowing what is possible, but I think maybe understanding what are the kind of structures we need to analyze can give us faster algorithms. And at least the previous framework, which kind of went up to, which did unique decoding for Tashma's codes and maybe some weak kind of list decoding, can be converted into near linear time algorithms. And I'll talk about that. It would be great if all of this can be converted into near linear time algorithms, and then we would really be kind of using the kind of, or at least be comparable to the beautiful unique decoding algorithms for expander codes. I mean, right now, yeah, it's like a bit shameful, but yeah, it's it will be nice to kind of extend this to list decoding of quantum codes. There is some recent work with Tushant, who I mentioned, and Shashank. So we can decode codes from like quantum version of AEL. So like if you start with a quantum code which is unique decodable, you do AEL, you get a quantum LDPC codes which is list decodable and so on. So you can get some, and this also suggests maybe a possible way of going beyond the Johnson bound, prove a better covering lemma. So right now the covering lemma didn't use anything about the code. Maybe you can, and then if you can use a property of the code to improve the covering lemma, you'll automatically get decoding beyond the Johnson bound. Okay. I'll stop here, and maybe I'll put up a plug for TTIC in case there are any students interested in applying. And yeah, let's stop there. Uh-huh. Right. So, I mean, yeah. So, I mean, there, it's not that you are solving those levels of SOS, but you are kind of maybe saying, I only need a subset of these constraints, or I don't need everything, because, I mean, even to write down all the moments corresponding to degree k, you need time n to the k. So you can't even write down a solution in less. But what you maybe say is, okay, my algorithm doesn't need it. And I think Barak Raghvendra Stoyer and Venkat and Ali Kemal Sinha both have algorithms which kind of do this for constraint satisfaction problems. It's possible that that kind of thing can be done there. The thing which is a bit of a problem is this sort of global correlation breaking step again, which comes to, um, and yeah, so it is possible that you can do something faster than just this kind of n to the number of levels. I don't know how to do this yet, but actually I believe it's possible that you can also do near linear time. So yeah, maybe that might be more interesting.
Once you expand it to rational expression,
Yes.
those things
Not in these proofs. Yeah, so there are these so-called um, two different kinds of positive Selensards where you write something as a rational expression or sum of squares. Uh, um, yeah, here we don't need to worry about that, but yeah, I mean, it's possible for some other codes that it might show up, but yeah, here we don't need to.
here it is.
Yeah.
It's a question of can you do with lower levels. Your other
Yeah. I see.
that's related to
Uh-huh.
Is that an issue for you? Again,
Is what?
bit length.
Oh, bit length. Not in this case. I didn't talk about it, but you need to verify that the bit complexity is bounded, and so there is this kind of framework of Raghvendra and Weitz, which sort of tells you under what conditions can you solve that program. That doesn't directly work for us because they need something like you have a proof system, it should be efficient. If you're deriving a degree D conclusion, it should be doable fast. And that's actually not true for these kind of things added based on linear equations and so on. But we can just cheat. In our case, we can add whatever kind of conclusions we need in terms of linear equations as an axiom, and then the proof system is kind of trivially efficient in terms of the XOR part. So you can modify the constraints a little bit and use the framework to show that the bit length is polynomial. Oh, sorry, the time for finding the solution is, yeah, okay, I guess also the bit length, yeah, is polynomial. Doesn't apply directly, but yeah, we can sort of do a hack on top of it. Yeah. So yeah, you can tolerate more error. So maybe yes. But yeah, you have to kind of be careful about how the error in solution to the relaxation translates to the error in the code. Yeah, and then sometimes that analysis can be a bit complicated.
Oui. Yeah, I'll try to write big, but the board is not too big. So if I write big, there won't be much on the board.
Downtown for everyone.
Yeah.
Okay, so since then he's been at University of Washington, IIS, AMU. He recently moved to the Berkeley and the Simon Institute of Theory of Computing. He's won many awards for his research, including the McCart Fellowship, the Sloan Fellowship, the Presburger Award. He's also the editor-in-chief of JSCM, the preeminent journal in computer science, theoretical computer science, and has been on the editorial board for many other journals. He works on pretty much everything in theoretical computer science, approximation algorithms, hardness, lower bounds, pseudo randomness, coding theory. Today he'll be telling us about one of his most recent works.
Yeah, thank you, Anand, and thanks to all of you for coming and moving front. I know I hate to have you do that, but hopefully it'll be easier to see. Okay, so this talk is about constraint satisfaction problems. Mainly, I'm going to focus on SAT, KSAT, 3SAT. And we will be talking about a model of semi-random planted KSAT, and I'll define these. And the connection to this workshop is that really these algorithms are enabled by, very strong spectral methods. In particular here, the algorithm is SDP based, and you prove it works based on spectral sparsification results. So it's very nicely intertwined with a lot of central themes in spectral algorithms. And this is a Fox 23 paper with Juntung CA, Pravesh Kotari, and Peter Manohar. Peter and Tim are at CMU students, and Pravesh is a colleague at CMU. All right. So we've been doing a line of work on CSPs using spectral methods, and a lot of them on refutation. I'll mention that. And this one is on the planted model. So so what's CSP? Let's really, as I said, mostly start with, we'll stick to 3SAT. These results work for very general constraint types. But really all the ideas, in fact, it's really all about XOR, as I'll come to later, but let's start with 3SAT. So this is, of course, very hard in the worst case. So how hard, for example, we believe that it really takes exponential time to solve exactly if you're doing approximation algorithms by the famous result of Hastad over 2 decades ago. Which is also when I started my PhD, so correlated dates. So we know it's like 7/8 plus epsilon hard to approximate. And this is really very strong because if you have an exact 3SAT, if you have exactly 3 literals in each class, and if you pick things randomly, you would set, the expected number of constraints satisfied 7/8. So 7/8 is kind of trivial. You can do it with your eyes closed by just picking your random assignment. And Hastad's result says that's really the best you can do. And it's also hard. Yesterday it was, I think it was in Prasad's talk, he mentioned that, SAT can sometimes get easier as you have more constraints because maybe you'll find contradictions. So this remains hard even with little o of n cube clauses. And so this is a result. I mean, this is not that difficult, but by Fotakis, Lampus, and Pashkos. So I'm going to not be very, given the board and the time constraint, I won't be very comprehensive with citations. Apologies about that. So it remains. So it's pretty much whichever way you look at it, worst case SAT, there is not too much you can do about it. But we do know that you can have a PTAS when you have enough constraints. Okay, these are the line of work starting with Arora, Kargar, Karpinski, and so on. So if you have many clauses, it is easy. So the picture somehow is, maybe I'll just draw it here for the worst case. So this region is kind of hard. And once you have n cube clauses, this is like order n clauses. This is order n cube. And this region is hard. And this is easy. So you'll see in a second why I'm talking about the number of clauses and so on, because that's really very relevant in these random models of SAT. Okay, so now we're going to talk about, so that's worst case. I have nothing to really say about it. It's very hard. So let's talk about average case. Okay, and basically 3 SAT, the 3 here can be replaced by K. Everything pretty much the same story works. Of course, K equals 2 is special, but everything else is the same. So here, average case, we're going to talk about random case SAT. So how do you sample a random case SAT instance? So you're going to have each clause. So let's do 3 SAT again. So it's going to have a random 3 tuple of variables. So you can maybe pick x4, x7, x25. So you pick a random triple, and then you also pick a random literal pattern. So everything is random. So you'll maybe say x4 bar, x7 will be the same, x25. Okay, and you keep doing this for many clauses. You get so you sample. So for m clauses, so typically we'll use m for the number of clauses. So each clause IID is sampled this way, a completely random disjunction of 3 literals. Okay, so now the question is, in average case, does it become easy? So is it, so good approximate solution, can we get this? And in some sense, if you ask it this way, the question is a little bit meaningless, because when m is some greater than, let's say, 10n or something, I just put 10 for a convenient number, this implies that this instance will have no assignment which satisfies, say, 7/8 plus epsilon constraints. Okay. So because really, if you take a random assignment, that's only going to satisfy close to 7/8 in expectation, and you're sampling enough constraints that you'll be close to the expectation. Right. So really, there's in this instance, if you give me a random 3 SAT instance, well, I can just pretty much output I can find an assignment which satisfies 7/8, which I can do either by random or by some deterministically by conditional expectations, and that will be pretty much the best you can do. Because it's a random instance, there's not much you can really do. So in this sense, random is, of course, really easy. So we're actually saying it's easy, but this is not, in some sense, it's meaningless. Right? So it's not very super interesting. So what typically one talks about in these random models is 2 things. So first, I'll talk about refutation. And this was actually mentioned in Prasad Raghavendra's talk a couple of days ago. So you want to say that given a random instance, you want to certify it's unsatisfied. Okay, so I don't want to approximately solve it. If I pick a random instance, I know it's going to be unsatisfiable, highly unsatisfiable with high probability. So I would like to give a refutation algorithm. So what does that really mean? If you give me an instance psi, and here is a refutation algorithm, it's going to say either it is satisfiable or unsatisfiable. Okay, so I'm not going to worry about finding the assignment. Just say yes or no, satisfiable or not. And what are the properties I want to have? The properties I want to say is that if psi is satisfiable, R of psi should be satisfiable. So it shouldn't refute some satisfiable thing. Right? So that's a completeness property you should have. And then the other, of course, if you just want this property, I can always say satisfiable. Right? But I also want to, for a random formula, because I know it's unsatisfiable, I want to say it's unsatisfiable with high probability. So you want to say that for a random formula, the probability over the sampling of this random formula that R of psi is unsat, should be, say, 1 minus little of 1. Okay, so this is the guarantee I want. Okay, so is the question clear? So this is the refutation problem for random formula. Okay. And in principle, there is an exponential time algorithm to do this when m is even like 10n, because it's not satisfiable. The exponential time algorithm can simply test all assignments and it'll work. So the question is, when can you do this efficiently? And the surprising thing in some sense, and it's a long line of work, is that when m is here even up to n cube, your picture was very hard. But here again, note that when m is bigger, the problem gets easier because there is more chances you will find some contradiction. So the question is that what's the minimum value of m for which you can solve this efficiently? And it turns out even at n to the 1.5 constraints, this has poly times algorithms. Okay, and I guess the first citation for this is some work of Koja, Oglan, Gert, and Lanka. Again, there's a long line of work. As I said, I'm not going to be very precise with this. Feige had a bunch of works and so on. So this is for 3-sat. And of course, the same story holds for k-sat. The bound, as you might get, is that n to the k. Okay, and I will kind of hint at where this k by 2 comes shortly. Okay, it essentially kind of comes because note that for 2-sat, when k is 2, the problem itself is easy. So you can this statement holds for 2-sat also. Right. But yeah, this. What I really mean is this. I know this looks a little bit funny, but this is actually the correct thing. You want to say there is some c such that if I have more than c, and yeah. So, but yeah. So as soon as I have n to the 3/2 constraints, I can do it. Right. So, and I will be a little bit sloppy with this. Really, many of our results assume some bunch of log factors liberally. Right. So if you want, you can just put a little tilde as well. Right. So, but it is monotonic. Once you have that many constraints, you can do it. Anything above will also be easy. Right. And this is n to the k over 2. And I'll say why this comes up, because for k equals 2, you can do it at m equals order n. And essentially, you can reduce k-sat to a 2-sat instance on these many variables. Okay, that is when k is even. So this is one of these things where there's a big difference between 4-sat and 3-sat. So life is much easier for 4-sat. It was a little bit hellish for 3-sat because 3 is an odd number. It's a quirk, but it seems somehow fundamental. And this is in a couple of works, for example, Barak Moitra and Alan O'Donnell Whitmer. I believe these were around 15 and so. So this was, so do it for all k, all odd k was done later. But for k is even, it's very easy. I'll almost give you a proof late, in the talk here. Okay, so that is refutation. And that's the thing. And there is also evidence that this is okay. So maybe I'll also say, so the picture looks like this then. So at order n, it's hard. M equals order n. At order n to the k over 2, it's easy. So this is the picture for random. Okay. But actually, there is something, the picture means that it's exponentially hard under ETH. So you don't really expect that many. Well, I think below n square, at least, it's exponentially hard. But here, actually, the picture is, it's hard. But there is also an interesting trade-off that you get a 2 to the n to the delta time algorithm, interpolating linearly between delta equals 1 here and this one here. So the actual runtime is that in n to the order L time, when m is n times n over L to the k by 2 minus 1. You don't have to understand the exact thing. The point is that when L is 1, this just goes back to n to the k by 2. And when L is n, it gets to n, and it just sort of linearly interpolates between them. So you have this very nice picture that you have this sub-exponential algorithms just below this, and it becomes exponentially hard as far as we know. Of course, there are no hardness and etc. here because these are average case problems. But there are also, again, tying back to Prasad's talk, so there are also SOS gaps hinting this is best possible. So if you kind of view as sum of squares semi-definite programs as your best bet for these problems, which is reasonable because those give the best algorithms, then we have tight gaps showing that you can't do better than this. So the story here is that it's really very well understood. The refutation picture for random K-SAT is very well understood, and this extends for all CSPs as well. Okay, any questions? Yeah. Yeah, that's a good question. So this is y-axis is delta, and x-axis is the exponent from 1 to k by 2. Okay, this is n to the alpha. Okay, this is the one, you should really plot it in the log thing to show this linear thing, but the actual trade-off. I mean, one of the reasons I want to mention this is that we are able to, one of the main open questions from our work is to get a similar sub-exponential picture for the planted model, which we don't know. And I'm going to tell you what the planted model is. Okay. So this is refutation, but in a way you might say that, okay, this is fine, but you're not finding the satisfying assignment. This seems like a somewhat weird model. So we would like to have a search version. Okay, so that's the, so far I've actually not defined semi-random or planted. I've defined random CSPs, and I'll tell you what semi-random is in a second. Actually, maybe I'll actually tell you what semi-random. Actually, maybe I'll do it a little bit out of order from what I planned. So let me finish the refutation story kind of for now. So what is the semi-random model? So this is all good. So there are two drawbacks you might see here. One is that you're assuming that it's completely random CSP. And the other is that you may not like refutation. So I'll come to the next thing of finding a planted assignment. And really, it's roughly what you would think. You pick a random instance such that it has a planted satisfying assignment. And your goal is to kind of find that assignment or do something, whatever best you can do. So that's going to be the planted model. But I want to talk about semi-random model too, is that these algorithms for these random CSPs overfit to the model. So in particular, if you have a slight deviation in your random model, they may not work. Right? So, so you would really like to have some robustness for these algorithms. So you would like to say, what can you do? And ideally, of course, you should solve worst case things, but we know that's kind of not possible. So really, the semi-random means that you have a combination of average case plus adversarial choices in the instance. Okay, so here everything was random. The constraint scopes were random and the literal patterns were random. So how will you make something less random? And this is the semi-random model. And this was again introduced in works of Blum, Spencer, Feige, Killian in model of planted colorings and so on. So there is a rich history of this in variety of problems. And these go back quite old, actually. So 95, 2001. So it's a well-known model. And what does it mean in the CSP case? You can probably guess. There are two things which are random here. We can't make both of them adversarial, but we are going to make the constraints are adversarial. So I'll say the constraint scopes or constraint tuples, worst case. Okay, anything you want. And the literal patterns are. Okay, so that's the semi-random thing. So it's a blend of worst case and this. And you can also make an even less random model, which is called the smoothed model. So I'm not going to talk about that, where you can actually make the literal patterns also worst case. So genuinely worst case. And then you can go ahead and flip each literal with some tiny probability like 1%. So this is really the smoothed model in this discrete world. Okay, and many of the results extend to that, but let's stick with the semi-random for the talk. Okay. Any questions so far? And
the variables for each clause are chosen.
Completely random. Yeah. So in particular, what is the thing? You can think about this graphically. For 3SAT, you have a 3 uniform hypergraph, which tells you which tuples have constraints. That's a completely worst case hypergraph. And it has M hyperedges. But then the literals inside them are random. And once again, all this thing will be true. So for this fact, if your literals are picked randomly, it still means that the instance will be unsatisfiable with high probability. The constraints can be arbitrary because this is just a standard first moment argument, and that will hold even if just the literals are random. So I can actually ask this whole picture, which I just said, for the semi-random model as well. Okay, and that's something you can ask. And one thing we have proved, again, as I said, this follows a line of work on refutation. So maybe I will just say that this trade-off holds for semi-random. Okay, so this was done in a couple of works, one with Abascal. Sorry to write this small, but I'll tell their names. So both these papers are with Pravesh and a couple of students. One is with Jackson Abascal, where we got the polytime version of this. So we got n to the k over 2. And then another with, again, Pravesh and Peter, who's on this work as well, where we got this entire sub-exponential trade-off. Okay, so the long story short is that refutation, where you prove things to be unsatisfiable, it's very well understood, the full picture between exponential time to poly time, even in the semi-random case. Okay, so that's the picture. And again, all these things have, some of these early works were combinatorial, but pretty much the trend ever since has been to use spectral methods. Okay. And in particular, some of you asked me about this offline. So I'll just throw in the word here. So let me remove this SOS gaps business. And of course, this is best possible because even for random, we think this is the best possible by SOS gaps. So, and one key hammer in the second work with Manohar and Kotari is this class of matrices called Kikuchi matrices. I won't define them. They're not relevant for this talk at all. But really, you analyze spectra of some random Kikuchi matrices, and that serves as certificates that an instance is not satisfied. Okay, because you have to somehow prove that the instance is not satisfiable, and the proof is based on some spectral certificate. Okay, and this Kikuchi matrix method has also had some applications to bounds on locally correctable and decodable codes, because the set of constraints in defining a code, like for example, the expander code, which Madhur talked about, those are a bunch of sparse linear conditions, right? So of course, those codes are defined so that they are satisfiable. So you have something in the code, but there are certain requirements where you can write down the requirement on the code will give you a whole bunch of such equations with some structure. And you can prove a code doesn't exist by proving that that instance is not satisfied. So there is a sort of a conceptual connection to refutation for certain combinatorial problems, especially in coding theory. And that has also been quite fruitful. Okay, but that's really subject of another talk on the Kikuchi matrix method and how it has applications in a variety of things. All right, so now I will come to our main story here, which is planted models. Okay, any questions? Any other questions? Yeah. Yeah. Yeah, that should somehow only be easier, I think. Yeah, because yeah, I think that somehow should be formally easier, I think. Yeah. Because there are also problems where literal patterns simply are not even needed. For example, something say like not all equals SAT and so on. There are problems where you don't need literals. So that will be like you're sampling a random 3 uniform hypergraph and you want to certify it is not too colorable. So there you don't even really need negations. So somehow that should be much easier because there's a lot more randomness when you pick these random tuples. Yeah. Another way to view these things as some sort of you're making do with much less randomness in in these algorithms. Okay. So now let's talk about planted CSPs. So what's a planted CSP? Or KSAT. So the instance is randomly generated subject to having a hidden planted assignment. Okay, and let's call that X star. And the goal can be, okay, the most ambitious would be to find X star. Okay. So one thing, I mean, maybe I'll give just one example. Graph coloring is a nice example. So I could, for example, sample a random graph. I can plant a 3 coloring, and then I can just give some edges across this thing with some random probability. Right? And then, of course, I don't show you the planting. I just give you this graph, and I can ask you find the coloring. So this was some of the earlier things in like Blum, Spencer, and so on. So that's a planted model. So there is always a solution. So the question is, can you find it? So that is planted 3 coloring. How might you define planted, say, 3-SAT or KSAT? You can have a particular assignment. And when you pick a tuple randomly, you don't want to pick the literal pattern completely at random, right? Because you want to make sure that that one assignment is satisfiable. So you can pick it, for example, uniformly from all the 7 possibilities here. Okay. And that's one way to generate, for example, a random planted 3-SAT. So these are random. So here you just don't do a completely random thing. So here you sort of make sure that you respect X star. Okay. Yeah.
The constraints also chosen randomly?
Great. So again, here you can do 2 models: random planted CSP, semi-random planted CSP. Random planted CSP, the tuples are random. Semi-random, the constraint structure is arbitrary. And the only randomness is in the literal patterns subject to respecting X star. Okay. Now, I can define this a bit more formally, but in the interest of time, I'll just say it's a little bit subtle, this second step. And why is that? Because let's say you do this for 3-SAT, what I just said. For each clause, pick the clauses randomly or worst case, doesn't matter. For each one, you pick one of the assignments, literal patterns, 7 assignments, 7 choices of literals while respecting the planted assignment. Then if I give you enough clauses, some 100 and such clauses, because you have this bias towards this planted assignment, every variable, let's say it's 1 in the planted assignment, it will tend to appear unnegated more often than negated. So you can just look at all these things and just look at the frequency, and that will be your planted assignment. So it becomes very easy in that model. Okay. So what's exactly going on here? But the point is, you're not restricted to sample according to this uniform distribution on the 7 things. So you can actually have more, sort of quieter distributions, which will still respect X star, but will not have this sort of bias. Okay. So the literal choosing step is random. Yeah.
If you are choosing the first step randomly, the second step can't be adversarial? Or?
The second step cannot be. Yeah, that's a good question. Yeah, I mean, if you want to do that, you have to just change the distribution. But I think I don't think you can completely make it random. You do need some distribution, but it can be a point distribution. I think that's a good point. Let me think about it offline. It's related to your question as well. Yeah. So, yeah. Because, for example, here, the 3 coloring thing, there is no negation, nothing. Once I plant, the only random choice is the edge. There's no more randomness, right? So, but here I'm talking about Boolean CSPs and literals, but that's a good question. I forget exactly what happens there. Okay. So really, formally, what you will really do here is that you'll have a distribution Q supported on 0, 1 to the k minus 0 to the k. Okay. You can have any such distribution. And once you pick a clause, you will sample an assignment according to this distribution. So you'll say sample y according to Q. for each. So this is what I'm telling you, how to sample the literals inside a clause. And then the literal pattern of C will be set to Y coordinate. Again, I'm defining not. So basically, this is just some notation I'm making up, but you get the idea here is that you know that the literal pattern should be such that if I apply it to X star, I should get Y. Okay, so that's if you didn't quite follow what this was, doesn't really matter, but this is coordinate wise multiplication. Okay, so that's bad because why did I do multiplication? That's because coordinate wise flipping or so really these are nicer to do in the +1 - 1 world. And in that case, flipping is just multiplying, right? Multiplying by -1. So yeah. Oh, because you want to be 1 to the k is 0 to the k in the +1 - 1 world, and you want whatever you sample, you want this clause to the k-sat formula should be satisfiable by X star. That's so this could be uniform, for example. But if it's uniform, you get a simple algorithm, but you want an algorithm which works for all distributions. Okay.
This distribution is not allowed to depend upon which way or like.
Yeah, this distribution should be, I mean, I think you can even go a bit crazy in this, but let's say it's just universal, but you don't know this distribution. It's just some sort of quiet distribution sitting there. Okay. So this is just so that I define it somewhat formally. This level of understanding of the distribution is not too important for the rest of the talk. So
On the 2 to the
yeah,
k minus.
you want to have some support, and it should be it can be any distribution. And which is also makes sense in the semi-random thing. You're moving away from, you want to make less assumptions about the model. So you don't want to say that the literals are sampled exactly according to some Q. Okay, so the Q can unknown to the algorithm. Okay. X star is worse. X star is an arbitrary assignment. Yeah. Yeah, algorithm will work for every Q without knowing it and every X star. But exactly what the algorithm can do, I'll come to in a second. There are some limits, but yeah, so. And this is also again has tie into what Prasad talked about, but there he was sampling X star at random. That was sort of the Bayesian aspect of the CSP. Here X star is some planted assignment and you have to find it. Okay, but what can we do? So what we can do here is that for random planted CSP, and again, I'll focus on KSAT. There's a nice paper of Feldman, Perkins, Mempala, also around 15, who solve it. Again, it's all spectral methods in poly time. I think that column has become too narrow, so I think I'll just continue writing. When again, M is at least O tilde n to the k by 2. So this is for random planted. So the picture is identical to the picture for refutation. Okay. And in this case, they actually find X star, solve it. And what does solve it mean? They find X star. So again, I repeat what is happening here. You take a hidden assignment, you sample a random KSAT instance from some quiet distribution, which ensures that X star will be a satisfying assignment. Give it to the algorithm finds X star. And it works when M is at least this much. So when M is even like 10 times n, X star will be information theoretically uniquely determined because the instance is random. But the moment you get to n to the k over 2, you can find it efficiently. And there is again evidence in the form of statistical query lower bounds, etc., that this is the tight trail. Okay, so this is Feldman, Perkins, Mempala. Very nice result. So what do? We do here, probably it's easy to guess based on the title. So what our result? So we achieved the same thing for semi-random. Okay, the above in quotes because we don't and we cannot get exactly this, but I'll say what we can. And semi-random model, once again, the instance is arbitrary, X star is arbitrary. The only thing which is random is the literal pattern, which is chosen in a random manner while ensuring that X star will be a satisfying set. So what do we do achieve above? What we achieve is that we find an X that satisfies 1 minus little one of the constraints. So we don't quite find X star. We find this, but this is the best we can do, as I'll mention in a second. In the random case, really X star will be the only, if there is an optimal assignment, that will be X star. In the semi-random case, even the optimal assignment may not be X star. There might be something which is, there may be other ones which are equally good. So you cannot do that. So in particular, why can't you find X star? Because this is the worst case. Remember, the constraints are worst case. So I might give you no clause involving X1. Then how are you going to find X1 star? Right. So it is not possible. That's one issue. So no clause involves X1, let's say. So then you're not going to find X1 star. You have no information, best this. But it doesn't matter. You can still satisfy all the constraints. So that says that you really shouldn't go for finding X star. It's even information theoretically not well posed in this case. But you can try to solve all the constraints. But that also we are not doing. So why is that? That is because you can have the variable split into two parts. Here you can have n to the k over 2 constraints. And here you can have 10n constraints. Right? And there's no constraint between them. So it's essentially the union of two instances, one of which has n to the k over 2, and the other one has very few constraints. So here we believe that at this density, this problem is hard. If you go below n to the k over 2. Right? So really in this part, you can't do anything. But here you can get most of the constraints, and that's the little of one, because there are only order n constraints here. So even if you fail on all of these, it's okay. Okay, in some sense, this is the best we can do. And actually, there's even more technical sense in which what we achieve is really the most information you can find about X star. So I'll see if, depending on how the technical proof part goes, I'll come to that. So, okay, any questions so far? Yeah.
First, you mentioned this X might not have anything to do with X star, or it might not even be close to.
Yeah, it may not even be close to X star. Yeah. It might, in general, you can only find it up to some subspace, so it might differ from it in every place for all you care. So, but that's the most you can do. Yeah. All right. So now what we will do. Let's see. So about 20-ish minutes. I'll try to give some hint of what's under the engine of these things. And I talked a lot about SAT and all those things, but really under the hood in all these algorithms is really only KXOR. And in particular, noisy KXOR. Okay, so you can really reduce to this case this constraint. So I'll define this in a second. And this is pretty standard. It's not completely obvious how to do this, but this is often called a Feige's XOR trick and so on. Really, the idea here is that whatever predicate you have, so you can expand it as a multilinear, expand it in Fourier basis. And somehow in refutation, so you can write it as, or if you like polynomials, you just write it as a low degree polynomial. So, for example, for 3 SAT, you can write it, right? 1 minus x1 times 1 minus x2 times 1 minus x3 or something like that. So you get like these bunch of terms. So you can collect all these terms, you get this big polynomial, and then you can go to each homogeneous part and prove that that will have a small value in the refutation sense. In the planted case, it's a little more subtle, but you can still sort of reduce it to the XOR case. So what is the K XOR thing? The constraints really are of the form, suppose the constraint. So again, you have this K XOR instance. So so now I'm going to use some notation where the hypergraph structure is going to tell me the constraints, and there is going to be vertices and edges, and E1 to EK are the variables of edge E. And now what is the K XOR instance going to look like? It's simply going to say that XE1 times XE2 times XEK is some right-hand side, where I'm really thinking of all X. Everything is in +1 -1 world, where parity becomes multiplication. Okay, so I have a bunch of equations like this. If you like F2, this is simply saying XE1 plus XE2 plus XEK is RE over F2. But over all these algorithms work over reals and so on, so it's much more convenient to write it this way. So now what are the right-hand sides? So the right-hand sides in refutation, and once again, semi-random model, this is arbitrary. The only randomness comes, so really it's a system of linear equations. Each equation has K variables. Arbitrary one, and it's going to have a fairly large number of constraints. So you expect it to be unsatisfiable or to somehow be uniquely identifying X star, etc. So this is arbitrary. The only randomness comes in the right-hand sides. So in refutation, RE is in +1 -1 uniformly at random. Each constraint has an independent bit as right-hand side. And of course, if you set the right-hand sides randomly, you don't expect the system to have any solution. And this n to the k over 2 is exactly the point at which you can prove that. Okay. And what happens? So what about in the planted model? So in the planted model, you want the right-hand sides to kind of mostly agree, and that's where the noise also comes. The noise comes in this reduction using the Fourier coefficients, etc. So RE is going to be really agree with the left-hand side when you plug in this with probability 1 minus some eta, which is eta is a noise parameter, and it's going to be minus this with probability eta. Okay, so it's random. So it's as if you make the right-hand sides exactly equal to X star. Right? In that case, it's easy. You can solve that linear system because it has a solution. But basically, I'm making the linear system noisy, which makes it much harder to solve. But I'm making it noisy in a sort of a random way. And this, for those who have heard, this is exactly the learning parity with noise type problem. Exactly same setting. The only difference is that the equations are all sparse now. So we can hope to do something. Okay. So that's the learning model. And this is really the core engine behind all these things. So in refutation, we'll prove that such a thing is unsatisfiable with high probability when you have n to the k over 2 constraints. And for planted, we will essentially do something like this. We'll do something a little bit stronger, which is necessary for the whole reduction to work. Okay. Yeah. Yes, yeah, very good, very good. So of course, yeah, that's exactly, yeah. So again, refutation is easy, you just prove it's unsatisfiable in some sense. In planted, what you will really do is that, so let me erase, so what the best we can do is not this. So we'll find this. So this can be a goal. And this is a non-trivial goal. And if you're able to do this, then we actually need to do a little bit more than this, but that's what we do. Okay. Yes, so for the same reasons, right? So I may not even have any equation involving this in the worst case, because the constraints are worst case. And in fact, even more so, even if there is no noise, you may not be able to find X star, because when you give me a bunch of linear equations, X star is only determined up to a subspace. So if that's not a dimension 0 subspace, you cannot determine. And these constraints are arbitrary, so you cannot do it. Right. That is true the way I have presented it. But somehow when I said you can reduce to this thing, you actually need to do more in the XOR to be able to. You actually have to kind of find X star. That's how the algorithm kind of works. Except for, yeah. So it's a little, that part is technical. So I don't think I'll get to that. But that's okay. So let's talk a little bit about some technical stuff here. So I'll again be a little bit high level. Where does spectral things come in? So again, this part will not be. Let's see how far I can get with this, but I'm really going to focus. So where does this k over 2? Where on earth does that come from? Okay. And that comes from the fact that when k is 2, you can do some very nice things. So you can do m equals order n suffices. Okay. And from this, there is a very simple reduction to 2XOR. So let me actually maybe just say what that is. So if you have such an instance, you can actually, so again, let's talk about 2XOR. So why does 2XOR somehow capture the whole thing? So when k is even at least, what you can do is that you can have for each subset of the variables of size k over 2, you can have a new variable ys, right? And when you have a constraint like xc1, let me just make it k equals 4. Suppose you have some constraint like this, I can replace it by y this set times y this set. And now this is a 2XOR constraint. And the number of variables is like n to the k over 2. So like again, if you think in terms of refutation, it's very clean. So if we can refute this, which you can also do, because once you have n to the k over 2 constraints, this itself will be unsatisfiable. Even, and of course, what is the intent? The intent, of course, is that ys should be the product of xi, I in s. So that's the intent. But if you refute it even without that intent, it definitely refutes the whole thing. Okay? And that's why the n to the k over 2 comes, because it somehow becomes all about 2XOR. Now, you can only do this for even k, and it looks like a technicality, but unfortunately, it's not. You have to work much harder for the odd case. Okay. And okay, so maybe I'll also quickly say what might you do, for example, for 3XOR. So I want to just do a bunch of these things and then set the stage to just talk about 2XOR in the last part. So what you can do for 3XOR is a bit funny, but what you can actually do is that suppose you have two constraints involving some variable. Suppose you have two such constraints, you can multiply them. Right? This is the same thing as like sort of resolution or something in the XOR world. You multiply them. X1 square is 1. So now you actually get X3, X4, X7, X19 is -1. So you can basically resolve to get a 4 XOR instance. Okay, this is the high level picture. And why should you sort of expect the numbers to work out? In 3 XOR, if I have n to the 3 over 2 constraints, equations, or constraints, on an average, let's at least say things are random and so on average, each variable is going to be in root n constraints. So there are root n choose 2 or n pairs you can resolve on. So each xi will give you n such 4 XOR constraints. So this will produce n square 4 XOR equations, which is exactly the threshold for 4 XOR. Okay. Now, obviously, the picture is not as simple as this, because now one of the good things is that the scope of these equations might still be random if you're random, but certainly the right-hand side is not completely random. If you think about it, in a 4 XOR, the right-hand sides, there are n square equations, so n square bits of randomness. Here, you only have n to the 1.5 bits of randomness, so you have to make do with far less randomness. So you kind of lean on 4 XOR refutation type things, because that's when you can write a square matrix and so on. And you'll quickly see this basically corresponds to some square matrix, whereas you can't do that when in the odd case. You can do that, but a lot more technical work needs to be done because you're working with much less randomness. Okay, so this is just to give you kind of high level picture of how you handle bigger XOR. So let's now talk about just 2 XOR.
Depends on the factor, it goes from n by 2 to n square, but depends on the variable means random.
Yes, so this again, this is another issue. Yeah, so this is also, for example, the two works I said, why this was not done for semi-random before was exactly that reason. So people only did it for random, and there it works reasonably. You just have to handle this less randomness issue. But yeah, this is a lie in the other case. But yeah. yeah, the distribution of the right-hand sides is not that random. So you have far less randomness and you still have to work with that. So yeah, so that's this odd even quirk in CSPs. But now let's forget all that and just work with our favorite even number 2. So we'll just talk about 2 XOR. Okay, so how much I have about 10 minutes. So dedicate this to sort of maybe give a little bit of glimpse of where so far matrices, etc. haven't come up, but let's talk about that in a second. So in this case, it's actually 2 XOR is very nice. So you just have a graph G, V, comma, E. And let's talk about random. I'll talk about the easiest case in the interest of sort of giving you almost a full proof. So random graph, random equations, plus refutation. So this is the easiest case. So how will you do this? So again, the equations are of the form XU, XV is the right-hand side RUV, right? So you have a bunch of these equations, M equations. And let's say everything is random. And you want to prove that this is going to not be satisfied. Okay. Now you might say, okay, come on, this is ridiculous. It's a system of linear equations. Of course, I can prove it's not satisfied. Right? I mean, you don't need fancy algorithms or spectral algorithms for that. But but for these reductions, you actually have to prove they are highly unsatisfied. In fact, it will be the case that for any assignment, only about half of these equations will be satisfied. Okay. So let opt be the largest fraction of satisfiable equations. So then, if you just moments reflection, you can actually basically what happens here. Right? So if the equation is satisfied, this is 1. And if it's unsatisfied, this is -1. Right? So if satisfied, this is unsatisfied. So this is again the standard thing. You can measure opt, how much opt exceeds by 1/2. The bias of this is roughly equal up to some normalization. It's going to be 1/2m. So this quantity is 1 when you satisfy. It's -1 when you don't satisfy. So just trust me that this measures the bias of your assignment. Okay, and this is not opt. This is basically, if you maximize this over all x in +1 -1. You get this. So this is an exact equation. Maybe I got the half here wrong or something, but this is, just easy to write down. So now how do you prove that half is very close to 1/2? Opt is very close to 1/2. You want to prove that this quantity is small, right? Now, but this is where a matrix is obviously sitting. What you have is a quadratic form, right? So this can be written, just the right-hand side is something like max over x in +1 -1 to the n of x transpose, let's just call it Rx, where R is the adjacency matrix of graph G with random signed adjacency. Okay. And now how are you going to bound this? This is where spectral things come from. So this X is a vector of norm root n. So this is going to be at most n times the spectral norm of this matrix. Now this is a random matrix with about order n entries, and its spectral norm will be at most a constant, but let's say even if it's at most log n, you are in good shape because you now have n over m. So the opt -1/2 is less than or equal to n over m. Let's say, what's log factors between friends? Let's give it an extra log factor, right? So you get something like this. So the point is when m is at least O tilde of n, opt is less than or equal to half minus plus little o. So you can actually prove that things are very unsatisfied. Okay.
Value arguably if there's a 0.
Yes, yeah. So it's really a signed adjacency matrix, randomly signed adjacency matrix. Okay. So this is for completely random. Now, what will you do for semi-random? It's not that hard also. In semi-random case, you can write down an SDP, right? Instead of this, you can try to So instead, you can write down an SDP. So semi-random case, just to sort of give you a full picture that semi-random is also not hard at all for 2 XOR or even K. So you'll just say maximize Rx, inner product of X. X is a PSD matrix, and the diagonal of X is going to be all 1, or you take the diagonal matrix, that's I. Okay, so that's going to be, you can write this SDP, and you can prove that this SDP and you can prove that this is something you can compute efficiently, and you can prove that with high probability, this will also be small for a random matrix, and there you get a certificate. Okay, and note that X equals, and if you prove that this is small, you cannot have a solution, because whatever solution you can have, if you take X equals X outer product X transpose, that will have the same value. Okay, if this was not clear, don't worry about it, but this is just, you can write the SDP, and the SDP value will certify this thing. Okay, I have about 5 minutes.
So where did the constraint pattern come into that R?
So it doesn't come in at all. So in this case, the constraint is semi-random, so the constraint pattern is arbitrary.
Yes,
So the only thing which comes in is that the entries are random. Yeah, it doesn't show up in the algorithm. It shows up in the fact that this optimum is small, right? And this thing, basically what you have to use is this Grothendieck inequality to say that the gap between this optimum and this optimum is only like log n. And this optimum is small, you just prove by standard Chernoff bound and stuff, which only requires each bit to be random, not the scope to be random. Okay.
So the fully random case, why do we need the arguments to be random? Isn't it like the random?
Yeah, I don't think you need that too. Yeah, I think this is related to some other question which was asked. Yeah, so it's a random. If you take a random adjacency matrix of a random graph, it should also be small. You don't really need the signs. Okay. Okay, so let's see, what can I say in a couple of minutes? So I have to say something about planted, since that was the talk. Okay. Okay. So I'll use the last few minutes to talk a little bit about planted 2 XOR. So for planted 2 XOR, what we will do is we will exactly solve this particular SDP. Okay. So here is something which works. Solve SDP, that SDP, do random Gaussian rounding, the standard hyperplane rounding, which you know. So this is the entire algorithm. And you can prove that this will give with value which satisfies 1 minus eta minus little o of 1 of the constraints. Okay. So that's good in the 2 XOR case. But the trouble with this is that, let's think about this reduction which we did from 4 XOR to 2 XOR. So you can do the same planted thing. There is still a planted assignment, namely this Y is a planted assignment. So it will all work. So it will give you some Y which satisfies this derived 2 XOR constraint, 2 XOR system. Okay. But the trouble is that Y need not be of the form X tensor X, because that's the way, that was our intended Y. Now here you get any solution which has good value. There is no reason it has to look like this. So in particular, you won't be able to solve the original 4 XOR thing. And this is a big difference in the planted model. In the refutation model, if you refute this derived thing, you automatically refute the original thing, because this is only more permissive. But in the planted model, because it's more permissive, it allows you to find more solutions, including some spurious solutions, which don't look like these intended derived solutions. Okay, so that's sort of a big issue. So the way we get around this is that we identify some conditions on the graph which will ensure that the SDP has a unique solution, namely X star X transpose. Okay, so that's really the some of the main ideas. I'm at least happy I mentioned that. So the point is, the key thing to make all this work, and I'll finish with that in 2 minutes, is that identify condition so that condition on what? On G, so that SDP has unique optimal solution. Okay, so this is what we do, and I'll write down what that condition is, and that will at least I'll do one justice to spectral sparsification and close there. But I want to tie it back to what I said in the beginning. In the planted model, this FPV result, for example, their X star was uniquely determined and the algorithm found it. Okay. In the semi-random case, we cannot hope for that. So what we're instead going to do is that the graph G is not random, but we're going to say that if it has some pseudo-random properties, namely some sort of spectral gap, then with some sort of a weak expander, then X star will be uniquely determined. But of course, we cannot hope this need not be true for our graph. So what do? Take an arbitrary graph, then we do an expander. We throw just a small number of edges out and decompose it into expanding pieces. And then we solve the 2XOR on each of these expanding pieces. And because of this uniqueness, there is going to be some consistency across these pieces. So we are able to put everything together and get find a good assignment which satisfies all the constraints. Okay, so that's really the whole approach. So this also ties in nicely to Akash's talk yesterday on these expander decompositions. And here the very vanilla expander decomposition based on recursive Cheeger works. The 1 minus smaller of 1 comes from the fact that the edges you throw away in the decomposition, you have no idea. And in the rest, you will get 1 minus eta. These things. Yeah. And that is enough because there's a reduction, the XOR principal reduction from KSAT to XOR can take care of that. Sorry? Yeah, that will be a little off. Yeah. Yeah, in this case you won't, because but this is not an arbitrary instance. This is really arbitrary graph on any graph.
That unique is only for expanders.
Yeah, yeah. So in general, maybe I'll also say that for general 2 XOR, if your opt is 1 minus eta, you can only get 1 minus square root eta. That's the best you can do in unique games, etc. Here we are actually getting 1 minus eta, and the reason we are able to do that is that it's a random model. Okay, okay, I should stop, but maybe what is this condition? So the condition is some sort of spectral gap. So rather than, so it basically says that the spectral gap times the degree. So lambda 2 times the min degree is at least omega log n or something like this. So this is the exact condition. But more illuminating is the thing which it enables. What it really implies is the following. It basically says that if you take the Laplacian of the subgraph H of erroneous edges, okay, there are some edges which are flipped in this noisy XOR. You don't know what it is, of course, but the choice of those edges are random. Okay, so because of that, this is going to be less than or equal to half times edge. Okay, so this is really the condition, and this is very strongly reminiscent of the spectral sparsification type thing. Strictly. So another way to write it is LG minus 2LH, strictly PD. And this you can prove just using spectral sparsification tools. And it's again very easy for the K even case. For the K odd case, because we don't have completely enough randomness, we have to prove some new spectral sparsification. Okay, so I think I'll stop. So it grows faster than log. Yeah, omega of log. Yeah.
On the other side, where you have only linearly many clauses and where below the satisfiability
threshold.
So There it's still a conjecture in a survey propagation possible. So I hope that something like SOS would solve it to or close to.
Yeah, I don't know much about this, but I do know that for say not all equal 3 SAT, there are some surprising. So these things lose constant factors, even log factors, left, right, center. So pretty much anything here is not going to be useful. But I do know there are results for not all equal 3 SAT. For refutation, they kind of identify some numbers, like a 12n constraints you can refute and all those things. So maybe it's not maybe completely hopeless, but you need to get really tight control on these trace method and other things. But it's still refutation though. Yeah. Below the satisfying thing, I have not seen below. Yeah. That I have not seen any of these methods really be useful. Yeah. Yeah, Madhu.
More than one.
Oh, list planted CSP. I mean, yeah, sure.
So, I mean, yeah, I don't know how to choose the literals individually for a clause, but if you allow me some sort of global choice, then I want to choose them so that at least one of the solutions satisfies at least my test.
For each hybrid at this point.
Yeah, I haven't seen anything. You think that will make it easier or harder? When that is not completely clear. Yeah.
Model and generalized where it is there's some generalization.
So which earlier model?
Here you mentioned that okay, there is a one model and the random model, and the algorithm for that it is generalized to others.
Yeah, I mean, not that didn't generalize. I mean, they seem to really use randomness in a heavy way. A more conceptual way to maybe think about this whole line of work, right? Refutation, this semi-random, is to really inspect what randomness is needed in the algorithm, and somehow replace this with some sort of pseudo-random surrogates. So that's what we did here, right? We said that the graph has some weak expansion. So that's a pseudo-random property, and it suffices for the algorithm. So you didn't need full randomness. So somehow that has been the philosophy in pretty much all of these progress, and the exact specific pseudo-random property varies from context to context. So it's not like they didn't work, but yeah, at least they didn't visibly work.
Okay, any other questions?
Yeah.
So here instead of refuting, if we have to retrieve X star,
Okay.
can we use like self-reduction like from K to K by 2 and then?
Also for this particular thing, yeah. So in some sense, that's the thing. So you cannot do it in a black box way, because you just get an arbitrary solution for this derived 2 XOR, which may not have this nice product intended structure, right? So there is a sort of a fundamental mismatch, but the way we get around that is to say that there's some structure which forces this instance to only have this solution up to some sign, and that allows us to get these solutions.
So that was for refutation, right?
Yeah.
So if you have to retrieve X
No. So this is for refutation. You have no problem. Once you refute this derived instance, you refute the original one, because that can only have more solutions. So if you prove that it doesn't have any solutions, you're done. This issue only comes up in the planted model, the search model.
K to K by 2.
No, K to 2 in one stop. Of course, here in this case, K by 2 and 2 are equal. So it's a bit confusing. But in general, I think it got erased. The way you get, yeah, so you actually make a variable for each K over 2 variable. So you still reduce directly to 2 XOR. Yeah.
Y's have K by 2 variables.
No, the equations are still just 2 XOR equations. There are n to the K over 2 Y's. So if you have, for example, 6 here, it will still be 2 XOR, and the Y is intended to be the product of 3 of the variables. But the solution you get need not have that property.
So once you get an assignment for Y, it will be like Y1, Y2, Y3 equal to C minus
1. No, it's still Y1, Y2 it's 2 sets. YS, YT is the
constraints are like these.
Yeah.
But once you get an assignment for these n to the K.
Correct.
Every particular assignment will be like Y1, Y2, Y3 equal to.
No, I mean, I don't know what you mean. You will get
X1, X2, X3 equal to. So.
Oh, yeah, that's right. Yeah. But that may not have any solution. Yeah.
You have to split K by 2.
Right. Yeah. You're right, but the problem is that may not have any solution. That Y need not have that sort of product structure. So in general, in this case, the Y is an n-cube dimensional vector. There is no need it has to be the tensor product of x tensor x tensor x. And somehow we have to force it with this property.
Okay, let's thank Venkat again. We have lunch outside and we'll meet again at 2 p.m.
Splitting into Ys and not working out. Can you try to use higher level SOS, etc.? Because that will come in with the tensor structure built in.
Yeah, that's a
But
good
then
point.
need better rounding.
Yeah, the trouble is that for these linear equations, SOS, yeah, I mean, it could, because I mean, ultimately our algorithm is SDP. It's
Yeah,
just leveled
I
to.
mean, it's very similar to what Madhur will talk.
Yeah.
This is the main reason why we can't do near linear time work in our case.
Actually, one open question I didn't mention, which is that, see, this one for each piece is solves the SDP separately. So related to your question is that can you write in a higher order SOS, which will solve all these things in one swoop?
Right.
Because we are doing this, each piece, we have to write the SDP, we round it, and so.
That's right. Go ahead.
For the SDP summary and the Gaussian rounding, is it similar to the flavor of how KMS do it?
No, this is just random hyperplane rounding, just Gormans-Williamson.
Okay.
Yeah, just really that.
That's precisely the regularity issue.
Yeah. In this
No, not yet. Right.
Oh, hello? Okay. So, all right, let's settle in, everybody. So, like I was asked to introduce the speaker because I made slides yesterday. So, we're very glad to have Professor Chiranjeev give this talk. So, we swapped sessions. Chiranjeev's slide leaves at 7:10. So, yeah, I mean, that's why this swap is being done. So, Chiranjeev is a professor at IISc. He did his PhD more than 2 decades ago. And let me tell you a little bit about what this talk is going to be about. So I hope, yeah. So I had slides. Right. All right. So what is this talk going to be about? So imagine a news article, this one. So this news article says that Sachin Tendulkar was ill and he was thrown in a hospital or something for COVID-19. All right, so you might be interested in understanding that, hey, what is this news article about? Is it about a cricketer? Is it about healthcare? Or is it about religion, right? Sachin is God. So what this talk will tell you is that it enables algorithms that help you uncover the topical structure of a given document. So you can uncover what a given document is about, what topics is it about, right? So for example, 50% is about cricket, 30% is about healthcare, and 10% about religion, or 20% about religion, something like that, right? And so you will learn how to do this with spectral methods. And yeah, that's all I have to say. Thank you, Professor Cherry.
So good afternoon, everyone. As you already heard, should I go on? Yeah. So good afternoon, everyone. As you already heard, did my PhD 2 decades ago. So obviously I'm Jurassic now in this age. Yeah. So what I would like to thank Anand and the co-organizers for inviting me. So I work in machine learning. So today I did not ask him to put up that slide on what I'm going to do about Sachin Tendulkar and all that. But let me see what justice I can do. And so what I thought was, initially I was supposed to talk yesterday, but due to some confusion, and it's mainly because of my fault, I could not make it. I apologize. And I thank the organizers for accommodating me. But initially, the talk was planned for just before lunch. And the cardinal rule is just before lunch, don't do math. So, and now this after lunch also is a bad idea. So I hopefully that way the slide tone would be good. And just before I just came in and I saw a very nice Blackboard talk on good things, So my talk wouldn't be of that kind. Okay. Just to so that, and if you fall asleep, I don't know, I'll try to entertain you. Okay. So having said that, So, so I think for this audience, I would believe the sentence, what's happening? Is there? I have no idea. What? Is came or not? Is that fine? You want to? What should I do? Duplicate. Okay. So now there's another challenge. Presenter notes. Okay. 1 minute. Where it go? Yeah. So what does it want me to do?
Yeah, so duplicate. Duplicate on the map. So his resolution is very high, that's why it's famous speaker.
You change resolution.
It's coming there. No, it's flickering, it's going green, then.
Okay. So again, this is this workspace.
Maybe we can lower the resolution.
If you want.
Yeah, and try. What are you asking to duplicate this one? Is it not being duplicated right now?
What should I do?
Can I, do you mind I try?
Yeah, go ahead. Sorry on this.
What possibility is you can just join on Zoom and share screen? That will get projected here. No? I mean, the issue is
But then we need to start Zoom here and everything.
would you have Zoom?
I think there is Zoom, I guess.
Yeah, so then why not just connect to that?
Link.
No, you can just get the meeting ID and password.
Can you share the Zoom link on?
Yeah. There should be Zoom somewhere.
Just do command space and Zoom.
Just see if this helps. Advanced. That's already right away.
Oh, resolution is list. Yeah.
No, I don't think the problem is the connector. No?
I don't think it's been working for the past. No, this is a very high resolution display. That's
Retina display.
Yeah.
So very good.
Yeah.
Now let's see how it go. This is let me just finish the slides. So this is
you need to duplicate the screen and
yeah, this is come back now.
Now I have to go see there and do.
Okay.
Mirroring current. Mirroring current. Display. What happens?
I have no. We have different connector work. I have a different connector. I'm not sure. No, it's not a PDF. It's basically that's the keynote. So now 1 minute.
You're connected to the network here.
Yeah, you see this? I have this.
Yeah, you can just join.
You can join.
So where is it? So here's the Zoom. Yeah, can you just type in here?
So
Join a meeting. Yes.
966 7269 7269 7140 7140. Passcode 910. Join.
Join and then last. I think the passcode will last.
Tell me the passcode. 910 396 110 396.
Okay. Join. Join.
And now you can share the screen like
Yeah.
a normal.
Yeah. Then now they're also join with computer audio. No. Got it?
You can just share the screen.
So where is the share screen now?
No, one second.
Mute. Okay, now share, where is the share screen now?
Yeah.
Where is it?
It should be in more.
More, right?
Share screen.
Share screen. Okay, here it is.
No,
No, I'm muted.
no, it's muted here.
Okay. So
You can
play,
make it full screen.
play in full play slideshow. It should be fine, right?
How do you do the presentation?
It's another problem. Another problem. There is the zoom. See, then play in window. And play slideshow. Again, this will work.
Play slideshow. Play slideshow.
But still doesn't. It's not. See,
Oh.
your screen sharing is paused. Oof, stop share. Yeah. Escape. Why is this? 1 minute. So now what do I do?
In Zoom, you need to share the screen.
Zoom we shared already, right? Okay, Zoom more.
Share screen.
Share screen. Then this is the screen, right?
Maybe the entire this thing, not the window. But
okay, so now let me just go back. So what do I do now? Desktop.
Yeah, share desktop.
Share desktop. Okay.
Yeah, share
Desktop.
Yeah. Yeah,
Now
now you can go full screen.
Now let us say, now where is it?
There's a play button.
Yeah, play full slideshow. Finally. Yeah. Okay. Sorry, this was not part of the talk. Okay, so sorry for the confusion. Okay, so I think what I was saying was that probably the first 3 lines, first 3 words on this, maybe new to some of you or most of you. I would like to walk you through that. But before I go into this topic, I thought I'll present one interesting idea, which we did, and I thought here machine learning and classical algorithms can play a big role, and which I came across from my own experience. So spectral methods, of course, this workshop is here. Algorithms have played a huge role. But in machine learning, the way I was exposed to spectral methods was when I started playing with graphs. So that's where spectral methods has played a role. And to illustrate this point, I would like to make this interesting. Unmoving, yeah? Okay. Yeah. Now, so here's an interesting connection we made some time back when I was visiting Devdutt Dubashi. So on this thing on Lovász theta function, a very classical tool in algorithms, support vector machines, which is a very useful tool in machine learning. And a very interesting connection. And so the way we're playing with graphs and finding large graphs is of huge commercial interest. For example, I've given you some references. See, these are all e-commerce companies trying to figure out who your customers are and things like that. Of course, if that's money there, but forget money, even there are lots of other fundamental sciences where graphs can play a big role, for example, in biology. So there's something called coherent networks. I will introduce that problem a little bit, the graph theoretic aspect of it. So some of you may have known this problem. That is that, suppose I give you a G-n-half graph. What is a G-n-half graph? There's a graph on n vertices. You pick any pair of vertices, toss a coin. With fair coin, if it puts up head, you put an edge. That's G-n-half graph, right? Now on the graph, what we do is I pick k, some k, 5, 6, whatever. Now what I do is I look at the subgraph induced by those k vertices. Now some of them may have edges, some of them may not have edges. Now what you do is wherever there's no edges, you just put an edge there. What you've done, you've planted a clique there. You give me back that graph and say, okay, it's a G-n-half graph. I have planted a clique of size k. You tell me this information. Can you find out which k? So that's the planted clique problem, right? So most of you know this. So now the interesting thing is, see, by random chance, there will be a clique, right? And that clique size is something like 2 log n by random chance. But more than that, probably that is the clique we have planted. And there's very low probability of a clique of size more than that emerging, right? So that is the idea. Now, what is happening here? What happened? I didn't know.
I think your screen just unshared or something.
Screen unshared. Share screen, yeah. Desktop on top, please. Hopefully you come back. Yeah. Okay. So now, probably this community know better, but the best that I know, it's little old, but I think still holds, that if you can find a clique of size root n or more, there exist polynomial time algorithms. Now beneath root n, okay, since the open problem, by open problem means is there a polynomial algorithm? It's open problem. Because there's a gap is between root n and log n. This is something we done. Okay, so now, fine. Now, what's happening? I'm sorry. Yeah. So, yeah. So this related problem, which is that coordinate networks problem. Now here, suppose I give you a collection of graphs. The vertex set, the vertices remain same. The vertex set remains same. But the edge set is different. Okay. Now I ask you, is there a subset, a set of vertices, subgraph, which is common? Now this is of great interest to a lot of people. Biology is one example. Even in here, for example, in this room, if we say we start putting edges based on our food tastes, based on our movie tastes, based on our book reading tastes, right? I get different subgraphs, but is there something common? Now these are of great practical importance. So currently most of them, you can look up this better. I think the reference is a little old. I'm sure this is of great interest there, but usually the thing is people do enumerative approaches. That is that they try to look for all possible subgraphs, and hence it doesn't scale that well. For example, a graph of size 60, right? In 4 or 5 graphs, it will take roughly 17 hours. So these kind of things, obviously, more needs to be done, right? So now, here, we made an interesting connection to SVMs, and we'll talk about that. So here is an optimization problem. So K is an n cross n matrix, and assume there is some data given here, xi, xj, and you define a function K on this, and Kij is that matrix entry. Now the function Kxi, xj, is such that the K matrix on this n is the number of data points is positive semi-definite, right? Now, given so that's called the kernel matrix. So given a kernel matrix, what you do is you solve that problem, optimization problem. It's a quadratic, it's a maximization problem, though it's a concave function because K is PD, a PSD, right? So you can maximize it easily. Okay, there are good algorithms to solve this. So this is in a nutshell called the SVM internal problem, but SVM has other things. Let's forget all that. So this is output an alpha for you. Alpha is a vector, the size is n, right? And that you can do other things like classification, things like that. Again, I see something. Okay. Now, the interesting thing is I can solve this in n square, open source software, and are very powerful things. And of course, now it's just a little dated because of deep networks, but they don't like me. I didn't touch it. Yeah, this is better actually. Yeah. I don't know what's happening.
Yeah, I think the Wi-Fi is getting disconnected. That's what is happening.
Wi-Fi is getting disconnected. I see. Now I see. Let me see if this helps. Sorry, this.
Put a hotspot and then maybe you can connect with that.
Kind of that?
Yeah.
Yeah. Oh. So hotspot. Say do ROM.
You can go to other networks,
Other networks. GRV.
Type in the
Please. Yeah. No, there is a Zoom. Zoom is here. No, Zoom is here. That one. Join a meeting again. I'll do.
Disconnected.
Yeah. So then the password is what you need. No, this is there. You need the password, please.
Join the meeting.
Join the meeting, right? This is just admin. This is what's happening? Is it the
No, it's maybe the network is not powerful enough.
unable to connect? Join a meeting. Okay. Is there a
Yeah, that's fine. You can join. You can join.
join? Now see.
We have animation.
Yeah. That is the thing. That is the thing. The keynote. Anyway, so yeah. It's 1 minute.
488 988.
488
Sorry. 910396.
910
396.
396. No. Okay. Join. Hopefully this time. Verifying passcode. Join with computer audio. We can mute it, I guess. More. Share screen. No. Desktop. I thought didn't I mute? There are two or both.
Above you can go. And
See, the two things are open, right?
from your laptop, I think you could do audio.
Okay. That's fine.
Yeah.
Okay. So let's see what this shows up.
You just need to
Show up. Okay. Play. Full slideshow. There's a delay.
It's not.
Okay. Play slideshow. Okay. Sorry. It's getting, yeah. So anyway, so that's the SVM problem and all that, right? So now the other interesting thing is, another thing you want to remember is the following. Now, how to choose the kernel matrix? So that's also a lot of study. Now, one way to do that is, in the previous slide, we had this omega k function, right? So that is, you give a k, you solve the optimization problem, omega k comes out as a number, as a function on k, if I choose to look at it. Now, people ask this question, can I find the right kernel? Okay, so one formulation was this: suppose you have a library of kernels. Let's say there are a capital M number of kernels, and I want to find a linear combination of them. That's one way of choosing a kernel from a library, right? So what can I do? Okay, you minimize that objective function where omega k of beta is another kernel, right? With the condition that k beta must be PSD. Now, moment you see this, now currently we know this kind of problems are solved by so-called semi-definite programs. Okay. Now, semi-definite program is a great news, but very bad news for machine learning. N cube, bad news. N square, tolerable. N log n, yes, that's practical. That's the scope. You want big data, right? So now, though this is a SDP problem, that's one we'll propose. But today we know better because of the structure of the problem. We can solve it by a first order method, which essentially maybe few calls to an SVM solver, which is like n square. And that's the state of that. Just remember this, right? This is called multiple kernel learning, right? This is the background. And now let's come back to the famous theta function, which you know very well. So theta function was an amazing discovery by Laszlo Lovász. Now it is sandwiched between the largest click size versus the chromatic number of the complement graph. And theta g is a polynomial time computable thing, which is often computed through a semi-definite programs. Fine. Now you have planted clique, SVMs, where are you going? Now the interesting thing is we discovered a very interesting connection. Connection is the theta function. It has many definitions. If you look at the huge definitions, so you can pose it in many ways. One of the interesting definitions was we could find is that you can pose it as if minimizing a kernel as SVM over a certain family of kernels. And so what are the family of kernels? It says that Kij is equal to 0 if ij is not a part of an edge set. If there's no edges, Kij is 0. And where there is an edge, you can put any values of k you want, but the k matrix has to be positive semi-definite. Okay, so this is a very interesting connection. And omega k, as you know, all this, right? Now, why am I presenting this? Now, often I see when I see theta function computation, I often see that they're running SVM, they're running SDPs. Now we in machine learning community has figured out algorithms for these kind of things. So that's another connection. I have not seen exploited though, so I thought I'll just present this. But more to the point that now this also gives me, suppose you want to find a largest independent set, right? Theta g computation, great, but it is something like n to the power 6. But now, if I can now because the previous thing, omega k is what? If I know k, it is like n square. So now, you know, if I suppose I know k, it is like linear in the edge. N is number of vertices. So k is n is like number of edges, right? Linear in data. So in fact, there is a very famous k you can easily get, which is almost free. If A is the adjacency matrix of the graph and rho is the minimum eigenvalue or more, then this matrix is PD. It respects all the family, the definitions which you wrote before. And this is sometimes called labeling, because that's what Lovász initially called it, orthogonal labeling. So in that honor, we're using this term LS labeling, right? Now, using spectral methods, right? So rho is basically your eigenvalue, right? Now, let's come back to the planted clique problem. So Feige and Krautgamer, you know, they showed that, you know, in adversarials, in a semi-random setup, you know, there are many results on that, but the long story short is that the theta function of the complement of the planted clique is equal to exactly the clique size. That's one thing. And from, you know, by the computation of that, you can also recover the clique, the planted clique. That was the result they had. Actually, they did it on the complement graph, so they recovered an independent set of the same size. So that means they'll give you the subgraph. Okay. But the essence of their algorithm is that theta g bar is equal to k. Right. But to compute this now is n cube, right? N to the power 6, right? But of course, k has to be large enough, like c root n. Now here is our result, that the rho we talked about, using random matrix theory, you can see that rho can be pinned down to something like root n plus k by 2, right? And omega k is roughly 1 by 1 plus t times, you know, theta g. And t is something like 2t root n. So what happens as t becomes large? You see, this becomes a very accurate description. And from that, you can actually tease out the planted clique from the solution of this algorithm, right? This doesn't tell you the algorithm yet, right? But as t becomes larger and larger and larger, you know, this becomes the omega k will exactly equal to theta g. And as I said, I already gave a hint that if you can get to that, you can also get to the graph. And in this case, just solving the SVM, right? I mean, so that's sort of the interesting thing, right? Now this other problem which you talked about is finding a common subgraph, right? Now, you can exactly pose it like this, like an MKL problem, where Km is the orthogonal labeling for the mth graph. So there are a capital M number of graphs. For each, we do the orthogonal labeling for the matrix of Km, and you have a linear combination of them. Now, you have to, goal is to find out delta M's, right? And some of the delta M equal to 1. I mean, probably I will talk about why is equal to 1. But essentially, the thing is that I can solve this problem very efficiently using the algorithm I told you about. And then what you do is you return the subgraph for its alpha is greater than some t. T is a threshold, right? Now, this recovers, this is an heuristic, but we can probably show that it will indeed, if not the highest density subgraph, common subgraph, but it will actually recover for you a very dense subgraphs, which are common to them. And now when you run code on this crochet is the enumerative method, right? And see, we can do it in seconds, and that is in hours. So this is a power. So I've not seen this interplay happening more. That's why I thought I'll just present this idea to you. But anyway, so we'll talk more about this if there's interest. But let's get back to the agenda of the day. So it's a nice blackboard. So I didn't know if blackboard talks were allowed. I would have done a blackboard talk. So I thought instead of that, I just cut the slides and I'm using chalkboard fonts. So do with it. So what we'll do is, as we said, I'm not sure we can do justice to the story you said, Sachin Tendulkar and all that, but we'll talk about what are topic models. I'll give a brief survey of the field, and then we talk about an SVD-based algorithm, and that's for the spectral methods, what I know of. For me, I don't know much about this, but SVD is what we can do about it, and talk about some recent developments if there is time. But I think I've already overshot my time, but Akash, please tell me when to stop. I think already a lot of time has been wasted. Thank you. Yeah, but I really feel sorry about this. Okay, so now let's get to this. What are topic models, right? Okay, so now just to keep you awake. So here's the question: what is common to Xenotortoise? You know who the person is? Look up Wikipedia. Greek, somebody Greek, yes. Casanova. Oh. And then something more, right? Mao Zedong, J. Edgar Hoover is all colorful characters, historical things, right? What is common to them? Many things may be common, I don't know. Many things are uncommon as well. But what is interesting is this one. They all worked in a library. Right? And Casanova, I'm not sure, is a fictional character, I guess. But all things somewhere they go to the library, right? So we're talking about library here, right? So now, so for me, information retrieval is a very important thing. And today's web world, especially big data world, internet, runs on this, right? So what is so now in a library, right? I mean, a definition you can look up, but essentially look at this. So what does a librarian do or used to do? You have information need. I want to learn more about this. I want to know all the temples in India. I want to know what are the food habits of, I don't know, some region. What do? Go to the library, repository of knowledge. And what do? You tell the librarian, I want to know this. Which book should I read? Oh, give me a book. Now imagine librarian's job. Now suppose the books are like this. How hard is it going to be? Now, instead of that, the books are like this. That's why people develop indices, right? How do you index these things? This looks quite trivial and all this, but this is probably one of the most important tasks. Otherwise, you won't be able to find information, right? So now, so now here in the, why is this interesting? Now in this web world, I have unstructured, all of us are writing whatever we want on a website, whatever fonts, what languages, all that, right? Unstructured text. Now, can you develop indices? If you don't have indices, search engine is not going to run. So how do you do this, right? And now the last one, so okay, we know a lot of natural language processing. We can use some of that. But unfortunately, all these grammar-based things cannot scale to the sizes of the internet. the traditional grammar-based methodologies, right, will not scale problem at hand, right? So here comes topic models. So the question posed was, okay, can you discover themes in document collections, right? As I said, is it sports document or is it suppose I know these documents are about sports or these documents are about literature, things like that. If I can discover those themes, then I can, use them to index and sort of things, right? And this is one of those, and those of you who are exposed to machine learning, and you probably have seen some of these applications roaming around, ImageNet, things like that. What is the input to that? Input to that is I have a picture. Oh, this is a picture of a dog, picture of a cat. You take those data set and then you train on these things, right? This is called supervised learning. Now here there's no supervision. Imagine you're supposed to do, and Google, for example, there's a room full of engineers who are doing indexing documents in languages they don't know even. So I don't have the option of training this. There's no supervision involved, right? So now this is an example of what is known as unsupervised learning. So now, let's try to delve a little deep on this. So what are topics? Now imagine there's a document which says, this first five letters, right? First five things: run, inning, hit, season, game, right? This is something about sport. You didn't ask what the noun, verb, all that. Didn't ask any of these things, right? Suppose this thing called computer software system, and the last thing, right? It's something on computers. See, the things you are marked in blue is actually what you relate to as a topic. But the theme is then, if I see this collection of words, that means they're expressing something, right? Now imagine doing these things. Now that means if I can find co-occurring entities, I don't have to know the language. I know that's the theme, right? So now I'll show you examples on this, that how this is one piece of technology, I think, which can break the English language barrier for this country. I mean, and other places as well. I'll show you some examples after we'll go there. So now that's being this set of topics, right? Now the question is, how do I find such topics, right? How do you define such things? How do you find such things given a document corpus, right? So now here's a quick survey of the field. But before that, it'd be good to, at least you should have one matrix here, right? And you had this troubling equation. So let's have one matrix after lunch. So let's assume this is a document collection. So what we do is we put each document, and put it in a matrix in a column. And the rows of the matrix is the words in your vocabulary. Okay. So what I do is I take a document, I throw away all the structure, noun, verb, I'll throw everything away. And I just count the number of words. Maybe you can normalize it, right? And so I get a big document vector, and the number of rows is basically the number of words in your vocabulary which you use, right? So you can imagine this document is going to be a very sparse document. Sorry, sparse matrix columns, right? And now each now if there is a corpus has n documents, so number of columns in the matrix A would be n, and D is number of words in vocabulary, right? So this is so now just take this A matrix now and say do whatever you want on this. Fine. So the first thing that we thought about this was 1970s. What does information need now? I want to build a machine where you query, just like a librarian, you get a query, you set a query and say to tell you similar documents. So now at that point, they build this interesting thing that, okay, the query is also a vector like this. Now, if AJ transpose Q is high, right? AJ is the jth column, right? So that, you can use the following encoding that AI is equal to 1 if what I is present, what I is the ith word in the vocabulary, right? Now, AJ transpose Q is high, that means the keywords are getting matched, right? You said that if you tell me query Q, I will show you document J, right? So this was the state of the art in 1970s. This was 1975, come out of Cornell, interesting things, powerful system. Okay, so but as document collection got richer and richer, people found many problems. For example, cricket, right? India cricket means a sport. But I can tell you there's a large part of the globe, and I've been there, where cricket is an insect. The word bank can mean many things, right? So this keyword spotting is not good enough for this, right? So automobile and a car, for example, is just a rank opposite thing. Two words which mean the same thing. Okay, so many other, see, keyword spotting has this problem, keyword searching, right? So we need something more, right? So then came this very interesting idea in 1990, I believe, where I said, okay, so what you do is do not use just the raw matrix A. What you can do is you do an SVD decomposition of it. Okay, and then you use this M matrix to do things, right? So basically now M will factorize in D into R, right? And now this you know very well. This is SVD decomposition of it, and R is a number of non-zero singular values. So maybe you can write A as AJ equal to MD into SJ, where SJ is the jth column, right? And now what you do is you use SJ as your. So basically, you're projecting the data onto the columns of M, right? And then you use SJ, so take query vector also, and then you again project it in the columns of A, and then you use similarity on that. So they changed it a lot, and this immediately solved those problems what we saw, synonym polynomial, all these other problems, right? Fascinating. And they also gave a name for this. They said that maybe this is encoding semantics, and this is known as latent semantic indexing. And that was state of the art for a long time, and so it was working well. And then, so the next question came as that, why is it working well? Can you give a model for this? So now, then came a very powerful analysis, 2000. It took almost a decade, and then see, Papadimitru and other colleagues first came up with this notion of idea called what is called a topic. So it said topic is not, so now think like this, they said that look, they have to make some assumptions to understand why LSI works well. One of the assumptions is as follows. Think like this, that each document is maybe instantiation of draws from a probability distribution. And a topic is nothing but a probability distribution over words. Okay. And they also thought about this, that the corpus is pure. By that, what I meant was that each document has only one topic. So the Akash's question, whether it is healthcare, whether it is cricket, or whether it's something else, is it a mix of them? That doesn't still fall in this purview. Each document is only one topic, pure corpus. Okay. Now, under that assumption, a few more assumptions. So, so that if the topic is also a special kind, that, for example, what you saw in the beginning, right? Run, inning, hit, season, game. Right? I see predominantly these words occurring in the document. These are called primary words. That is, the large part of the probability mass is on those things. Right? Under those assumptions, I'll not go to separable corpus, but this is a little more technical. They could show the following, that if the two documents have the same topics, right, then you see that the dot product between AKs are quite high. If they're different topics, they're very low under all these assumptions. So this somewhat explained LSI, under these assumptions, right? Now, as usual, he already gave a good example. We have ours. So do you know what Jackson Pollock is? He's a very famous artist. Okay. Now, this is a very famous blog. I don't know how many of you track this. I track this. So you see, this document, how will you classify? Is it about computer science? Is it about machine learning? Is it about paintings? So this kind of documents, right, or the example which you showed, this will fail. Why? Because LSI says that, to understand when LSI works well, you need, each document can be of only one topic. This is multiple topics. What do I do? So that changed the game. People have been looking at this, but so they said that maybe we should do something differently. That means we must have models that are flexible enough to allow for multiple topics. So how do we do that now? So then we said, okay, so basically let's decide that each topic comes from a mixture of topics. So what's a mixture now? Mixture, when I talk about mixture, it is more like a probabilistic mixture distribution. And now what you do is select a topic along that mixture, and then and then you have a compound topic, and from the compound topic you draw words. Okay. So in other words, the idea is, see, it's an animation, right? So assume that, for example, M1, M2, M3 are your topic vectors. Okay, these are vectors. Now what I do is I put some weights. Yeah, I put some weights on it, 0.6, 0.3, 0.1, and 0.3. Right? Then you get a compound topic here. Right? Now from this topic you draw your document. MID draws, right? So now if it was a pure mixture, then I should only be either seeing M1 or M2 or M3, not this. These are sometimes called add mixtures. Now, the algorithms community, has done a fantastic research. For example, K-means clustering. This is an example of pure clustering, right? The add mixture changes the game significantly, where the cluster weights are also random. Now that part, probably more of you should get involved in it, So yeah, so topic model is the first thing. Departure is the add mixture, and now so there is a graphical model description of it, but I think after lunch and after this fiasco with this thing, it's not good to just get slide the picture. So essentially, as we said, we can think about it like each document is drawn from a mixture of probability distribution. Let's call it theta. Now each topic is distribution over words that we already have learned it, and now so now each topic assignment, z from theta is then a word sampled from a corresponding topic variable beta z. So in other words, so first thing is, how do I now put on the weights? I need to have some structure on it, right? So we'll put Dirichlet structure, and that gave the name of latent Dirichlet allocation, LDA model. It has a very scary set of equations. So the idea is that once you know the words, W is what you will see. W is set of documents. This is what I have, right? From that, I need to figure out this document is about sports or politics or whatever. I figure out theta now from this. Also need to know which words came from which topic, Z. Now, given W, figuring this out essentially is, you can very well imagine, is NP hard. What do we do? Right. So essentially, things are nothing much can be done. Machine learning community has borrowing from statistics, and they did MCMC algorithms. And there's also this very dirty method called variational inference. And these things works very well. But that's the state of the art. Now, and it's quite powerful even. For example, these things, so for example, here's a document. Again, David has very nice tutorials on his website. For example, this is borrowed from one of them. See, this is a document. See, so the first topic is gene, DNA, genetic, and things like that. Second is life. So all you can see, the actual code is actually marking out which topic, which word is from which topic, etc. Right? And this gives you a lot of explanation of a scientific document. And this all came out from this MCMC algorithms on that, right? So now, as we said, I earlier said, right? So now this is so powerful that you need to know co-occurring words, right? Now we can extend it easily. This is some of our results, right? Now, if you can say that, okay, the problem is this, right? Now, let us say I give you Bangla news. do whatever you want. Can you tell me what is the corresponding English news? Or the reverse? So Bangla news with a translation. Can you index them both? So here's an example. So now these are all co-occurring topics. So this is a very minor change to the probabilistic machinery one can do. Minor in the sense that I mean it's quite straightforward to do. Anyway, so this has a lot of implication in research class languages, but that's beside the not the topic of the day. Now let's come back to some of these mathematical machinery. So Akash, how much do you have time? 20 minutes, huh? A lot. Thank you. Thank you once more. Yeah. So now, so here now, so the idea is now, can we be a little bit more precise about these things, right? So one of the questions, so if you just look at the data generation model, what is the model now? I have capital M is a topic matrix. Each column is a topic. What is the topic? Word distribution of words. So how many rows it has? Number of words in a vocabulary. And what are the columns? Number of topics. The D cross R, which I wrote down before, right? So it's like K topics. The triangle which I drew, the 3 topics there, right? Now what you do is first select a topic weight. And this, so W is a random variable, you draw from some distribution. Example which you give is Dirichlet distribution. You can draw whatever you want, right? And now from this, you'll get a compound topic, P. W is a vector, right? Who sums to 1 is like a PMF. So P is a new topic distribution. Now you draw small m number of words from that P. That's your document. Okay. Now what you've done is you've given me back those documents and I've formed the A matrix from it. So the challenge is from A, find M. That's a challenge. That's a learning problem. And now, okay. So statistical approach, use maximum likelihood. Right? Now there are many challenges. First of all, computing that likelihood itself is difficult, NP hard. So you saw some scary equations, right? On top of that, maximizing M star is also another difficult problem. So both this problem seems to be if you do a maximum likelihood approach, you're already, it's like a doomed problem, right? And so people have done few things. As you said, existing things are mainly study-specific distributions. And so most of these methods, what has a very weak finite sample guarantee. That is, they'll say, oh, maybe this will work well if you have infinite number of, n is infinite number of documents, right? Now that is not really something very useful for us, right? Now, so here's a question one would like to ask, the following, right? Suppose you knew that A was generated from some M matrix, the process we just described, right? Do whatever you want, run a favorite algorithm, algo, on A, you come out with M hat. Guarantee that M minus M hat in some norm, whatever, is less than epsilon, right? So here, the main learning which you came across is that the best fit approach, the maximum likelihood approach, is a bad idea. It's doomed from the start. Rather, let's take a promise-based approach. There's a promise of an M, right? And then can you pose a problem like this, right? And there you want to ask this following question that, can you tell me, now what is the smallest value of n to recover M from A in that sense? Okay, this is the setup now. So this was, so this approach was pioneered by Sanjeev Arora's group in 2012, right? So what they made the following assumption, they call it separability, right? So they say that, in a topic T, there is at least one word which only occurs in that topic and no other words. Something like, I don't know, maybe batsman. Batsman will never occur in cooking, in politics, right? So that word occurs very high probability, right? These are called separability assumptions, right? So under that, give some polynomial time algorithms, for this. So here, so that's why I said m minus m hat. Here is this, here is this result. So S is the number of sample complexity, if you will. So I like to draw your attention to two things. One is K. K is for number of topics, and another is P0. What is P0? That the word batsman occurs only. What is the weight of that word? Right? P0 is that. I want to draw your attention to the denominator. What is the denominator? P0 to the power 6. This is the result, right? And where is it?
Last line.
A is the minimum expected weight of a so that is that, so like over the corpus, that topic at least occurs that many times over the corpus, right? It's since that it's still an expectation. See, you have a sample, right? But I think that's not the point. I'd rather draw your attention to P0. Right? So what is P0? P0 is the weight of the word batsman, for example, right? And comes 0.6. Like P0, put P0 to 0.1. What happens? Right? Okay. Now, okay. I'm sorry again. Now, so I would like to draw your attention to the title. See, because you're fitting multiple topics, right? And the algorithm, he said that, and LSI was one topic, right? SVD, going beyond SVD. Let's go beyond SVD. SVD will not work. Okay. So now, yeah. So now let's look at SVD. And he talked about a very interesting examples. The talk is recorded. I can't share that. We can talk about it. Ravi and me are talking, and so Ravi is a little bit, yes, SVD, we can do things with SVD. And I can't say what he said, but so let's see. So what is it we can do, right? So remember the following things, right? You have to go beyond SVD because multiple topics, number one. Number two, you have something like P0 to the power 6, all that, right? Okay. But it takes nothing away from him. He was the Aurora's group and all that. They are the ones who first conceived the problem which I posed it. They are the ones actually gave us the road, right? And we are building on top of that. It's amazing breakthrough which they've done. So yeah. So now the thing, as I said, right? So it's a sample size, and for example, instead of asking the word batsman to occur with probability 0.1, maybe can we do the following? Can we ask a group of words to be occurring with that probability? Maybe is that so? See, that also ties into the initial description of LSI, catchwords, a group of words occurring, right? So try to catch that notion. So we made that assumption. So we'll do that. So most importantly, we made the following assumption, right? Now, if you look into this setup here, the SVD, LSI, what did it say? Each document is only one topic. Now let's say, how about making some more assumptions here? One assumption we make is the following. Let us say a document can have multiple topics, but primarily the document is about some theme which is very dominant. So Sachin Tendulkar, sports person, Sachin Tendulkar, COVID-19, that means healthcare is the dominant topic there. Right? Can you make that assumption? As you can see, then comes closer to this our LSI structure, right? Yeah, I will not go over that algebraic definition of it. So another thing, as I said, catchword, right? Catchword, maybe the group of words has high weight, as opposed to saying one word has high weight. They're called catchwords, under that same spirit, right? So now, okay, we all can welcome to make assumptions, but does it play out? Yes, it does. Actually, experiments actually show that these assumptions are valid to a large extent on various corpora, right? And so where does the algorithm go now? So algorithm is as simple as this. So now so think like this, right? If the topics are really dominant, it basically becomes what? Molecular side, right? You're going to basically have only one topic. So what you have to now do is you take the A matrix. There is some magic here in how we don't apply SVD directly on it, but you just threshold it and then apply SVD on it. And then you roughly recover the dominant topics in each, you recover the map between dominant topics and the individual documents. And from that, you estimate M hat, right? So, of course, a lot of things I'm hiding here. So essentially, we would like to draw your attention to now look at P0 and P0's dependence now. This becomes P0 square, right? So basically, yes, SVD will definitely not work as is, but under this assumption, and after this some thresholding, we could even make SVD work for that, and that's what the thing is. So as I said, after lunch, proving things is not a good idea. So we didn't talk about the proofs, but it is really something very interesting. This can happen. I think more can happen going forward. So this is what we thought was SVD-based approach, right? Now, if you want to really know more about this, as you can see, it is like if you plot the data matrix versus these words, the raw matrix looks like this, but after you thresholding is done in a very clever way, though. It's not as simple as that. It cleans up some of this, the cross entries in most of the. So these are like catchwords, and so if you can only get those catchwords correctly, your SVD has enough signal to partition. The eigenvectors will tell you the dominant topics and so on and so forth. Yeah. Anyway, so now the last part. I mean, obviously, since the numbers are there, I think it works well. So now last part is I want to talk about some later developments, right? Now this is a very interesting model and probably requires more study. And what we are currently have come up with this interesting idea called latent K polytope. So where we can see high dimensional convex geometry is can be used to understand topic models. So yeah, let's come back to our favorite picture. So what is the latent K polytope? Now forget topic models now. Let's make it a pure geometry problem. So now what you do is you generate a point in the convex hull of that. Basically, now you know what that is. That is topics, right? Now drawing words from a topic. So if you plot them, what are you going to see? So maybe another word which may or may not lie in the convex hull is a draw, right? So essentially, the idea is this: that PI is the topic, and AI is the observation. So the way I can view this is that I have these green points now, and you have to give me what? The pink colored points. And how do you define the green points now? So the green points can be thought about like this, right? So maybe this diagram is useful here. Yeah. So sorry again. So first you generate a point in the convex hull, then you give a small perturbation to it. The perturbation may keep the point inside the hull or outside it, right? And now you expose me the perturbed points, and you're asking me to find the corners, right? This is a pure geometry problem now, right? So this is called latent K polytope. Why latent? Because I don't see the polytope per se, right? And what we found is in literature, algorithms community have studied the following. They've studied points, given points from a convex body, recover the body. That they have studied well. And now here, but here's a nuance is different in two ways. Most of the studies actually can recover the large part of the body. But here what do you want? We want the corners. That's all I want, right? So that's a little bit hard. number one. Number two is that the points are perturbed. The points may not lie on the body. That makes it extra, the additional difficulty, right? So now that's why this a standard convex hull of, so what's the big deal? You take convex hull of the green points. That's not going to work. It will have a large intersection of the volume of the body, but will still the M1, M2, M3 may be out of it, right? So this is one of those things here, right? Yeah, this is what we talked about. This is exactly the current setting. So those of you interested, I think this is a very fast. I don't see too much work on this, but a lot can be done here. So convex set estimation, yeah, convex set estimation. We can look that up. So this is the probably few other works are like this. We are trying to learn convex bodies from data like this. But our point is that, as you now see, that the green colored points, which you call A, from that, can you find out the polytope? By the polytope, you mean find out the vertices, extreme points, right? So that's your topic model. And so now we can clean up some of these things. And under three assumptions, there's an algorithm we can learn now. So one of the assumption is, first assumption is the topic should be extreme points should be very far apart. Otherwise, if they're very close, I can't do much. There's enough separation. That's a reasonable assumption to make, I believe. Now, the perturbation. Of course, the idea is that, okay, the real challenge is to learn perturbations which are very, very large, right? But still some structure is needed. So under that structure, that A minus P in an infinity norm, the average perturbation, if you characterize it like this, right? So that's the perturbation. And then, just like our dominant topics, right? We also make the following assumption that at least few points from the A matrix lie very close to each of the individual vertices. This is called proximate point assumption. So under these three assumptions, we can find an M hat which is pretty close. Yeah. So that's one of the results which came out in Soda. Yeah. Anyway, so I think I'll stop here. So thanks again for this opportunity, and apologies again for the mess I created. And right. So thank you. Happy to have any questions if you have. Right. Yeah. Yeah. Are there any?
There are no questions, then let's have the speaker again.
Right. Sure. Right. Okay. Listen T. Yeah, I'll do that. Huh?
So let's start. Our next speaker is Madhur, who will be continuing on a slightly different topic. We all the decadal introductions are already done, so I'll
I'm sorry. All right. Thanks again for sticking around for the second talk. I apologize to some of the experts. You might have seen some version of this talk earlier. It's on a slightly older result, but thought it might make a nice complement to the talk in the morning where we were trying to decode codes using sum of squares or semi-definite programs, and we got some algorithms which go all the way up to the Johnson bound, or in some sense, at least for a generic code, give optimal list decoding radius. But the caveat is that they are, although they are polynomial time, the exponent is not great. And here we'll talk about algorithms using a different route, slightly different technique. They are related, and I'll point out some connections. With at least so far, I don't know how to get to Johnson bound or the optimal decoding radius, somewhat weaker in terms of what they can achieve, but the running time is n log n. So yeah, it's a machine level, sort of machine learning level of running time, as Chiranjeev said. Okay. So although, yeah, don't ask me about the constants in front, but so we'll again talk of codes, and this time, as opposed to the morning, I'm going to, sorry, it might flicker a bit, but I'm going to talk about unbalanced bipartite graphs, and the codes we'll talk of, I'll call direct sum codes. And I kind of briefly mentioned Tashma's code in the morning, this epsilon balance code. These are sort of maybe a slightly more general way of thinking about these constructions. What we are going to do is take a code word and make a new code word out of it using this bipartite graph. So let's say you have X, which has n bits. We write them on the left on these blue vertices. And every green vertex has few neighbors, let's say 3. So we are just going to write down the sum of these 3. And the sum is modulo F2. Everything is in F2. So we're just going to write down the sum of these 3 bits on this vertex corresponding to Y. Okay. And in general, we'll have a full bipartite graph, not necessarily balanced again. So the number of green vertices is larger, as is indicated by the picture. And at every vertex, we have a sum of few positions from the left. Okay. And this is called a direct sum operation on codes. It's an operation which is kind of parameterized by what this graph is in the middle. And in general, we'll think of this graph as given by W, which is a subset of K tuples. Okay. Will it be better if I use a different connector? I don't know. I'm using my own, which I used in the morning, but I don't know if that will. We can try. So just give me the HDMI. Okay, let's see if that's more stable. I don't need the charger. It's fine. Maybe not. This seems worse. Okay, I can just switch back to the one I used in the morning. No, it's worked fine in the morning. So like, okay. Yeah, that's a good idea. Okay, I think this HDMI cable is a bit finicky. Oh, no. I can hold it. It's, I think this might. I can adjust it, don't worry. So, okay, so I guess it's a memory test. How well can you remember the pictures on the slide, and then they go away after a while. Okay, so we'll think of this W as a subset of the set of K tuples. And so these are ordered K tuples, and that just means that if I have a K tuple which is I1, I2, I3, let's say K is 3, then I have this tuple which is 3 elements of this index set of size n, let's say I1, I2, I3, just means that there is a vertex here called I1, I2, I3, where I sum these 3 things. Okay, so it's just a hypergraph. I'm just going to think of it as an ordered hypergraph. It will be clear in a minute why ordered is kind of more convenient, but this is just a subset of K tuples with an order on them. And we define a direct sum operation parameterized by this W with just one element on the right for every element, sort of one bit on the right for every element of W, where we have summed the K things appearing inside W. And as we also said in the morning, you can just think of this as matrix vector multiplication. So X is a vector on n positions. A sub W is a matrix with one row for every element in W, which has exactly K non-zero entries, the ones corresponding to the elements in the tuple. And you sum those K things, you get one entry of AW times X, and then you go over all the rows, you get this entire green vector. So that's just to say that this is a linear transformation. If X belong to some linear space, then AW times X also defines the linear space. So if we started with C0, which is a linear code, then C is also a linear code. Okay? And I'll stick with linear codes. I'm sorry? The generator matrix is a product of the generator matrix for C0 times A. Yeah, exactly. Okay. And as I claimed in the morning, and we'll see again, that the epsilon balance code construction of Tashma is a special case of this construction. And we'll talk about how to decode these constructions, this time thinking of them as constraint satisfaction problems. You can already see that this looks a little bit like the 3 XOR problem that Venkat talked of, and it is. And then we'll actually use this connection in our algorithm this time. Okay. Any questions? So this is the kind of object we'll work with. Yeah, let me know if there's anything unclear in the definition. Because like there was the previous construction, which is direct product, where you write down x1 and write down x2 and write down x3. And so like here, because you're taking sum modulo f2, it's direct sum. It's yeah. And direct product, direct sum are both used for kind of hardness amplification, pseudo-randomness amplification, etc. Okay. And now the question is, like, depending on this W, you get very different kind of codes here. So what kind of Ws give you some interesting properties or maybe good codes, or sort of how do different Ws behave? So let's see a few examples. Okay. First, let's just look at a W, which is everything. Okay. So this green side is kind of humongous in comparison to this blue side. It's of size n to the k. And now, instead of thinking of this X as having bits in 0 or 1, let's think of it as having entries in -1 or -1. Again, the same sort of embedding we were working with in the morning, and then Venkat used in his talk. So we'll think of -1 to the xi as an embedding. And the sum of xi's corresponds to the product of -1 to the xi's. And so if I think of for an arbitrary kind of element on this green side obtained in, according to this construction, what is the bias, which is again the number of ones minus the number of -1s, the same sort of thing we worked in the morning. It's this, right? We go over all tuples. So we go over all vertices here, I1 to Ik. We look at what is the -1 to the y subscripted with those elements. Okay. But this y is just the sum of the corresponding xi's. So -1 to the y is just the product of the corresponding xi's. And because we have w equals everything, we are going over all values of I1 to Ik uniformly at random, which means it's just the expectation over I whole to the k. So what this means is that if this kind of blue string had bias epsilon0, this green one has bias epsilon, which is epsilon0 to the k. Okay. And so in that sense, it's kind of amplified this bias. And if you remember, this bias was kind of related to the distance of the code. The distance was delta, the bias was 1 minus 2 delta. So the smaller this bias is, the larger the distance is. And so we want to make it as small as possible. And this, in some sense, is the best possible, that we actually go from epsilon 0 to epsilon 0 to the k. It's bad because this is humongous. And if you want to think of this as a code, the number of bits in the code has grown a lot. And so we want to do it more efficiently. And actually, it turns out that you can do the same thing if you just pick W as a bunch of random k tuples. And in fact, some n over epsilon square random k tuples will work. By Chernoff bound, you can show that the sort of you'll basically have the same property, except you'll have sort of a random collection which will achieve this. So and then so that's a great improvement over this n to the k. So now we can work with subsets which are of size n over epsilon square, and that in some sense gives us a very good code. We get something with bias epsilon, where epsilon was taken to be epsilon 0 to the k. Epsilon 0, you can just think of some arbitrary fixed constant, let's say 0.1. And bias epsilon means distance half minus epsilon, just kind of. And so you get a code with distance half minus epsilon. And the number of tuples you have is n over epsilon square. So the rate of the code, which is kind of what is the dimension of the space in which, like corresponding to the code versus the ambient dimension, is pretty good. It's actually epsilon square, right? Because you have n over epsilon square ambient dimension. And in some term are real, they're coming from here. So and the problem with taking things at random is that these are great codes in terms of properties. Random codes are in general pretty hard to decode, and so we don't have any idea how to do this, like what to do algorithmically. And also, a lot of the times we are not interested in the code itself, but we want to use the code to construct something else, etc. And so we want explicit constructions. And a nice suggestion of Rosenman-Wigderson kind of said that, okay, you can take this W. First, let's take it to be the edges of an expander graph. So just think of k equals 2. And you just kind of sum two things for every green vertex, which are just think of each on the right-hand side vertices as an edge, and the left-hand side things as vertices in a graph. So you just sum the two endpoints of an edge. That will already actually give you somewhat of a good bias amplification. And if you choose the degree of the graph right, you can get bias epsilon on the right with n over epsilon to the 4 vertices in this green set. And then you can also just consider walks of length k in an expander. It doesn't really improve this epsilon to the 4. This was analyzed by Tashma. But he kind of built on it, and as I said in the morning, kind of gave a carefully curated collection of expander walks, which actually does much better. It gives them something like the random collection, and which is nearly optimal. Yeah, please. Yeah, epsilon naught is 1/3. Sure. Arbitrarily small epsilon. Yeah, so we have some parameter epsilon, and we want to get to that. Yes, absolutely. Thanks. Okay. So, okay. And so this construction was the first explicit construction to get close to what the threshold is for random. And I mean, again, this collection of walks requires some work to describe because it's also a specially constructed expander. But it's of this flavor, and we'll develop an algorithm using this structure and some relatively kind of weak properties of what this graph has. So we'll not need to know a lot about the explicit constructions. Okay, but these are examples. Again, as in the morning, the question is, can we decode these codes? And I claimed already that the SOS-based methods we discussed can give a decoding of these codes up to the Johnson bound. And for distance half minus epsilon, let's say, So the Johnson bound is actually pretty close to half also if you have distance close to half. And so in some sense, these codes are pretty good algorithmically, except that we would like fast algorithms. And then so let's see what else can we do. And then there are some other techniques which I want to kind of highlight in this one. Yeah. Okay, so now I want to think of decoding these codes as solving a constraint satisfaction problem. And what do I mean by that? So suppose we did this construction for every y, I1, I2, I3, we kind of properly wrote down the sum of the three things, xi1 plus xi2 plus xi3. And then I kind of tried to send it to you, but there were some errors, and let's say delta fraction of errors. And what you received was y tilde. And y and y tilde don't quite match. There's some kind of mismatch in about delta fraction of positions. And so there is an underlying x, but what you see is not always the value of xi1 plus xi2 plus xi3. Sometimes it is, but in at least delta fraction of the places, or about delta fraction of the places, it's not. Okay. So the question is to find an underlying x which kind of matches what you see, the y tilde you see, as much as possible. Okay. So that just means that we want to, let's say, search over all x in this code C0 and minimize the kind of mismatch between y tilde and AW times x, which would have been this. Okay. So this is the question of finding maybe the closest code word. Okay. Any questions? All right. And instead of a min, let's think of a max. So instead of saying, let's minimize the number of positions in which they are unequal, let's say, let's maximize the number of positions in which they are equal. It's the same thing. And now it's really a constraint. It looks like a constraint satisfaction problem. I want to find x such that these right-hand sides given by y tilde are kind of satisfied as an XOR of xi1 plus xi2 plus xi3 as much as possible. Okay. So it's an instance of 3 XOR. And but it's an instance of 3 XOR which is not necessarily perfectly satisfiable. It's because there is some error from y. If we actually received y, this would have been a perfectly satisfiable instance. We would have used Gaussian elimination and so on. And as Venkat said, if you have a noisy instance, then it's not always easy to solve this problem. So, but I claim that if we can even solve this problem up to a certain error, then we can actually recover the starting x which you gave. And let me sort of say this for unique decoding, although you can also do this in a list decoding sense, and we'll actually give list decoding algorithms. But the important point is that this matrix A, which we kind of multiplied, or this direct sum operation we did, amplifies distance or reduces bias, right? So if two things were kind of somewhat far before you multiplied them with A, then they're really, really far after you did that. And in contrapositive, if some things are kind of somewhat close, even after you multiply them with A, then they must have been really close to begin with. Otherwise, they would have ended up quite far, right? And this is not just for X, which is in the underlying code Z0. Importantly, we are using that this distance amplification happens for all vectors X. Okay. And so suppose you started with this AW times X, we got Y tilde. I found some other solution. I found some X tilde, which again kind of satisfies at least 1 minus delta, like fraction of the equation, so it's delta far. Then AW times X tilde and AW times X are no more than 2 delta apart by triangle inequality. And if I kind of set up my parameters right, I should be able to say that X tilde and X are quite close. Again, they're close enough that I can do unique decoding in this base code. So I'll try to reduce the question of decoding this code to decoding the original code by approximately solving this constraint satisfaction problem. Okay. So, okay. And now we just have an instance of 3 XOR. We can forget about codes. Now we'll just try to solve 3 XOR or maybe K XOR. Okay. Any questions? Yeah. Y is a code. Y is actually just sort of a linear function of X. Y is just A times X, right? It's a. I mean, that is what we are trying to do. So we are trying to decode Y tilde. And the question is, like, I'm trying to design actually an algorithm for decoding Y tilde using this constraint satisfaction. I mean, if there is another algorithm, then sure, we can use that anyway. But for Tashma's codes, I didn't know of an algorithm. And so this is an attempt to design one. It's yeah, but it is a code. And so it's possible that there are other ways to design algorithms directly. This is just one approach to designing. So this in particular for direct sum codes, I can design an algorithm by going through constraint satisfaction.
So first decode the Y tilde to code word Y on just the.
Yeah. No, but I mean, that's all you need to do, really. I mean, this X is, you don't need it. I mean, and also, if you found Y, you can find X because this matrix AW should be non-singular. So, or like, yeah, so it should, yeah, should have an inverse. Yeah, whatever that is called. Yeah. Okay, yeah. So you should be, once you find Y, you should be able to find X. This, yeah. Okay. And of course, yeah, if you find X, you found Y. So, okay, good. All right. So we'll attempt to kind of solve this problem of decoding Y tilde to Y by going through this CSP just because of the structure of this direct sum. And yeah, of course, there can be other approaches. And for example, the SOS approach we saw doesn't go through this CSP route. Actually, it's inspired by this, but kind of now we can state it in a way just about distance proofs. But that has a sort of a drawback of runtime. Okay. So let's talk a little bit about CSPs. And actually, Venkat already did a fairly thorough intro, so I don't need to. But I mean, in general, a 2 CSP you can think of as constraints, sort of where every constraint is between a pair of variables, and we can restrict ourselves to XOR. So 2 XOR, which Venkat discussed, 3 CSPs, and then in general, you can think of K CSPs, where we have, let's say, n Boolean variables, m constraint. The goal is to satisfy as many as possible. And yeah, again, we can stick to XOR for the talk. So for 2 CSPs, we know how to solve them approximately. So it's in general, a 2 CSP is also hard to solve exactly. But if I give you a max cut instance, then in general, you can do some non-trivial approximation, something like Gomans-Williamson. But actually, if I give you kind of a 2 CSP on an expanding constraint graph or some kind of slightly weaker notion of expanding graph, you can solve them using SOS hierarchies. And then these are sort of the root of the methods we saw in the morning. There is actually another approach to solve these CSPs, which is so-called regularity lemmas, which are structural statements about the graph themselves. So they kind of write the graph in a simpler way, sort of represent it in different ways, such that kind of optimization of problems over the graph becomes easy, and you can just kind of search some finite dimensional space. And this is the approach we'll take for this talk. We'll kind of try to go through regularity lemmas. But the first issue is we don't have a graph. We have a hypergraph. Okay. So the question is, are KCSPs easy on expanding hypergraphs? So you have some hypergraph, and well, I mean, I don't know. It depends on what an expanding hypergraph is. We haven't defined it yet, right? And as Prahlad said yesterday, there's quite a few definitions of expanding hypergraphs, and not necessarily all of them equivalent. It's so a sparse random instance is, one can think of as expanding, but it's not necessarily easy. In fact, sparse random instances are pretty hard. And as we saw you can sort of, it might even take exponential time to solve sparse random instances, although you would think of random as expanding. You should. Yeah. Never seen an academically curious dog that sort of that academically curious. Okay. All right. Yeah, no, let's go over it again. Right. So I was trying to say what's a good notion of an expanding hypergraph. Okay. And I said one way could be to mimic, like in random graphs, we said like a random graph is a good expander. And so anything that kind of is pseudo-random in the sense it mimics a random graph should be a good notion. Right. And as Prahlad also mentioned, that's not a great parallel for hypergraphs. Sparse random hypergraphs are not good models for high dimensional expanders and also for our notion of expanding hypergraphs. In particular, sparse random instances of CSPs are actually hard, whereas we want some notion which would make things easy. So it doesn't quite suffice for us. On the other hand, dense instances, not random, just dense instances are easy. And again, Venkat said there is a PTAS. And so we would like kind of expanding to be something more like dense rather than sparse random hypergraphs. Okay. And there is this notion of link expansion, which Prahlad mentioned, or also called local spectral expansion, which defines some sort of structured pseudo-randomness. I'll work with a weaker notion, which I'll call splittability, which is implied by local spectral expansion, so it's weaker, and it suffices for our purposes. So it does give us SOS-based algorithms for decoding these codes, sort of for list decoding, etc. And today we'll talk about a regularity-based algorithm also using this notion of splittability. Okay. So, yeah. Yeah. No, that's not going to be true, and that's not necessarily required. So, in fact, for graphs, there are regularity lemmas for dense subgraphs of expander graphs. So they don't have to be dense in the absolute sense. They just have to be dense inside a pseudo-random graph. And in fact, that's the kind of model we will get here also. And so we'll see that, yeah, this splittability property will be sufficient to actually prove regularity lemmas. We don't really need density. Okay. Yeah, but the intuition is right that we want to define pseudo-randomness or expansion to mimic properties of dense instances so that we can prove the same sort of structural properties as in dense instances. But we won't actually need density for that. Something with just some weaker property will suffice. Okay. All right, good. Okay, so again, if there's kind of one definition I want you to remember, it's splittability. It's just sort of an independent notion of what is an expanding hypergraph, and it captures a lot of the things we are interested in. So let me kind of take a moment to spell out this definition. And I should say that this is equivalent to an earlier definition studied by Mosel in context of higher order correlation between random variables, but we can think of it combinatorially for now. So remember, we had W, which was a subset of n to the k, or an ordered collection of k tuples. Okay? And this is where the order will be useful. So let's define W with an interval a to b as kind of a subtuple of W with kind of indices between a and b. So if W has, let's say, k, if an index has k elements, I1 to ik, and then I look at a equals 2 and b equals 4, I'm just going to look at every tuple and write down the I2, I3, I4 appearing in that tuple and forget about all the other stuff. Okay, so I'm just going to write down 3 coordinates out of these k for every tuple inside W. Okay. And I'm going to assume that the instance is kind of, in some sense, highly regular, that if you look at WAB, the size of it just depends on the difference between B minus A. You can still do this otherwise, it's just that you have to talk about measures, etc., the kind Prahlad was talking about. But these kind of regular instances actually do occur in our cases if you just want splittability. So it's okay to just kind of assume this, and I'll show you an example of this in a minute. Okay. And then we can think of this matrix where rows are indexed by first L entries of a tuple, and columns are indexed by the set of the last k minus L entries appearing in any tuples. And you put a 1, if when you put these two subtuples together, they actually form a valid k tuple, okay, which appears in my collection somewhere. So it's a bipartite graph. You can just think of it I mean, it's a different bipartite graph than the one I drew earlier, but it's also bipartite, it's also unbalanced. And these are the kind of first L indices of any tuple appearing. These are the last k minus L indices, and I draw an edge between them if the kind of concatenation is actually a valid k tuple. And we'll say this collection W is splittable if this bipartite graph is expanding, okay, or its second singular value is less than tau, same as in the morning. And we will do this for all values of L. So L can go between 1 to k minus 1. So there are actually k minus 1 bipartite graphs. If all of them are simultaneously expanding, then we will say that W is a splittable collection. Okay. So it's just bipartite expansion of k minus 1 bipartite graphs. It's slightly different from link expansion, which is expansion of something like order n, possibly order n, but smaller graphs. And these are k minus 1 larger graphs. Okay. So first, there are examples of this. There are the collections which do give us splittable tuples. So for k equals 2, this is just expanding bipartite graph, just regular old graphs. As I already said, these spectral high-dimensional expanders or link expanders are splittable. It takes a little bit of a proof, and there are kind of two different proofs which appear in these papers with slightly better parameters actually in this one. Also, walks on expander graphs give us a splittable collection. So if you think of, let's say, a length 3 walk, so you kind of, when you take a length 3 walk, you encounter 4 vertices. You write down, let's say, this matrix with kind of 2 vertices here, 2 here. And these are sort of 2 tuples which appear as kind of the first 2 coordinates in some 4 tuple. So they have to be an edge, because something which is a non-edge cannot appear as a sort of subtuple of anything. Similarly here. So these rows and columns are just indexed by edges. And between I1, I2, and I3, I4, there is an edge, or you get 1 if I1, I2, I3, I4 is a valid walk. And it's a valid walk if and only if I2, I3 is an edge. So you can see that this matrix actually is just a tensor of the adjacency matrix of the graph with an all ones matrix of D cross D after a little bit of work. And so it's actually second singular value is the same as that of the graph. Because the all ones matrix has the singular value 1 after normalization. So walks on expander graphs give us a splittable collection. So does this kind of slightly more specialized collection of walks in Tashma. So all of these are just examples of splittable hypergraphs. And we'll be able to use just this kind of weak property to obtain algorithms. So now we don't really need to remember too much about expanding hypergraphs. We can just capture this property and then work with it. Okay. Any questions? Yeah. Dense hypergraphs are also splittable. Yeah. So, okay. There's a bit of a catch. So here I'm defining splittability as saying the second eigenvalue is small. In dense instances, it might not be that the second eigenvalue is small, but maybe the 10th one is small, or so there's some threshold after which. And I mean, everything we are going to say would work for that, except that here I'm taking it to be more conveniently just the second eigenvalue. Yeah. I mean, okay, it's defined for second eigenvalue there. I think maybe the rth eigenvalue should also work, but yeah, I'll have to check that to think back. Okay, so now let's come to regularity, what it is, how does it give us algorithms for constraint satisfaction problems, and so on. So before talking about hypergraphs, about this kind of fancy splittable hypergraphs, etc., let's just talk of graphs. Okay, and this is a very nice result of Alan Fries and Ravi Kannan, which gives a structural approximation of dense graphs, and that's, I think, where what you were referring to. And for a dense graphs, it kind of says that for any graph and for any epsilon greater than 0, you can identify a collection of subsets S1 to SR and T1 to TR, which gives you a way of kind of approximating your graph G. And what do I mean by approximating? In the sense it gives you a way of counting edges between any set S and any set T. And the way it does is that, okay, you just need to know the intersection of S with each of the SJs, T with each of the TJs, and then, yeah, this sort of approximation comes with some coefficient C1 to CR such that you can take this linear sum. And it's actually going to be close to the number of edges between S and T for all S and T. So the important part is the quantification, that this S1 to SR, T1 to TR depends on the graph G, depend on epsilon, but does not depend on S and T. Right? So it's one approximation which works for all S and T. Okay. And the error, again, that's where density comes in. The error is epsilon n square, so it's kind of meaningless if the total number of edges in the graph is less than epsilon n square. And so this is a good statement when you have a dense graph. So you can choose your epsilon to be smaller than the density, but otherwise it doesn't quite work. I'm sorry? No, I don't, because otherwise the statement is trivial, so it's just true. Yeah, I mean, I wouldn't apply it, but yeah, I mean, it's still true. Okay, so you can just think of there's some complete bipartite graph between S1, T1, S2, T2, and so on, and somehow G can be written as a linear combination of these complete. Linear combination doesn't make sense because G is a combinatorial object. Really, the adjacency matrix of G can be written as a linear combination of the adjacency matrices of these, but the picture is nice. Okay, any questions? So that's the so-called weak regularity lemma for Fries and Kannan. I mean, not because the lemma is weak, it's just that the notion of regularity it kind of works with is called weak regularity. And it actually implies the so-called kind of strong regularity lemma, or like Samredhi's regularity lemma. You can actually, so the lemma is actually pretty strong. It's just that it talks about weak regularity. All right. So let's use this to get an algorithm. Let me get an algorithm for, let's say, max cut, okay, for dense instances. And so we'll get a pitas out of this. And so what is max cut? We want to, well, partition the set of vertices into two parts, maximizing the number of edges going between them. Okay. And we already have a good way of counting the number of edges going between two parts, let's say S and S complement, that up to some small error epsilon n square, it's going to be equal to this expression which we got from regularity. Okay. So let's just try to maximize this expression rather than this one. And this one is kind of cleaner because all I need to know is for each for the S that I'm considering in my maximization problem, I just need to know its intersection with S1, S2, and so on. And again, similarly, the intersection of S complement with T1, T2, and so on. Okay. And I mean, this might still not be easy to figure out because S1 and S2 might overlap in some weird ways, etc. But let's actually look at the kind of partition generated by S1 to SR, T1 to TR. So let's write down all the sets, like write down the Venn diagram, see how things intersect. I mean, this is also called the sigma algebra generated by these, but yeah. So, I mean, just let's write down all intersection patterns. Okay. And now within every piece, which kind of maybe is in S1, S5, and S13, and T3 and T5, sort of there'll be some piece which exactly has this sort of intersection pattern, let's say. I can figure out the intersection of S with that piece, and also the sort of the intersection of S complement, which is whatever remains. Okay, and I don't need to know the actual intersection. I just need to know this number, the size of the intersection. And I don't even need to know the size of this intersection precisely, only up to an error of, let's say, epsilon n, or maybe epsilon cube n if I want to be a little more conservative, right? So I just need to like for every piece in this kind of intersection pattern, I just need to guess for an S what is the size of the intersection of S with that piece of the partition. Okay, and I mean any guess is fine, because once I like these pieces are non-overlapping, they're disjoint pieces. So there is an S which has exactly that kind of intersection sizes once I sort of make a guess. Right? So the number of pieces in this partition is 2 to the R or maybe 4 to the R, where R was the number of these SJs. And here I said R is like order 1 over epsilon square. So in time 2 to the 1 over epsilon square, I can enumerate kind of a guess for each of these pieces. And once I enumerate over all of them, I will be able to maximize this quantity, which up to an epsilon error is the maximum value of the max cut. Okay. And in fact, I can even find the cut, because this S and S complement, I can realize these intersections. Sorry? It's all relative error, but again, epsilon n square is kind of absolute. So, I mean, I can, and the number of pieces is bounded, so I can even work with absolute error. Okay. So this is an algorithm. It's just a very simple algorithm. I just kind of enumerate the intersection sizes within every piece and just check everything. Okay. And the only non-trivial part is to find these subsets S1 to SR, T1 to TR, which is to basically make this weak regularity algorithmic. This is known. In fact, it can be done in sort of linear time. So that gives you up to this extra constant in front, sort of a relatively nice algorithm. Okay. And also a very kind of conceptually simple algorithm. You just kind of have this collection of pieces, you just enumerate and check. All right, any questions? Okay, so now we're going to develop an analog of this lemma, but for our splittable hypergraphs. But I'm going to kind of massage the statement a little bit, write it in terms of functions, etc., so that it's kind of easier to work with when I talk of hypergraphs. Okay, so let me first write down the same statement we saw for regularity, which is that there exists S1 to SR, T1 to TR, such that for any S and T, the number of edges between S and T, which is nothing but 1 S transpose times the adjacency matrix times 1 sub T. I'm not normalizing the matrices right now. These are just kind of vanilla adjacency matrices with zeros and ones. Minus this linear combination of matrices, which is kind of 1 Sj times 1 Tj transpose. If you look at this quadratic form, it's going to give us exactly the term that appears as an approximation in regularity lemma, which is the S intersection Sj and T intersection Tj. Okay. And we know that this is less than equal to T squared. And maybe we can write it in a slightly further simplified way by just thinking of this matrix, which is A minus this kind of outer product of these rank 1 matrices. And we are saying that A is well approximated by this linear combination of outer products. So the difference of the two has small inner product with any kind of 1s, 1t transpose. And we are going to think of A as a function, this time from the set n square to 0, 1. Each of these 1 sj's as a function from the set n to 0, 1. Okay. And so we have a function on n square things, like a 0, 1 function, and we are approximating it by a sort of sum of functions, which are just kind of tensor products of functions on n indices. Okay. And okay, I mean, this epsilon square became epsilon because I took the inner product the way I did in the morning with respect to expectation measured, so that I don't have to write the normalization. And this is can be written as a more general statement, and this statement itself has quite a few applications. This regularity lemma actually can be used to kind of simplify kind of large part of the proof of the Green-Tau theorem for progressions in primes. You can say that if some structure can be approximated by some other structure, then you can transfer to this simpler approximation. And so, sorry. So that right now, yes. But in some sense, in this statement, it's hidden because the inner product is allowed to be with respect to whatever measure you want. But yes, if I instantiate this with respect to the measure which is uniform on n square tuples, then it's with respect to densities. Okay. But I want to think of this version for a minute because we can actually prove this one in generality, and then kind of switch to splittable collections. How much time do we have, by the way? So, sorry. Okay. I mean, okay, yeah, let me know if I need to kind of wrap up, but yeah. Okay. So, in this statement, in this version, kind of statement looks a little cleaner to write. So we have some function g, okay, and we have some family of functions script f, which is of this form 1s tensor 1t and so on. And we want to say that for all functions on this family, for all function f in this family, which will be of the form 1s tensor 1t, we want an approximation of g. We want something which kind of behaves as well as g when I take the inner product with respect to f. And the lemma says that I can actually take functions from the same family. These fj's are actually the same kind of functions. These are just 1sj tensor 1tj. So if I have g, I want to approximate it with respect to some function class f. I can take a bunch of functions from that same class f and build an approximation for g. That's all it says. And in fact, this thing is true in more generality. It's sort of not just for graphs. And let me use it to give sort of an answer to your earlier question about density. So you can actually use this to prove a regularity lemma for dense subgraphs of expander graphs. Okay. And this is the statement I'll now be interested in. So I want to kind of have the same sort of statement that given a g, which is now from this w, which maybe is an expander, it's an indicator of an expander. And instead of just taking it to be 0, 1, I'll allow you arbitrary functions which take values between -1 and 1. Again, it's a good expander. And now I want to say that if I want to approximate g with respect to this function class f, the function class is the same. Okay. I can build an approximation, this time with error, which is relative to the number of edges. Okay. So now I don't need density. If the graph has very few edges, this error will go down. Okay. And as long as this collection w is an expander. So this w is not a subgraph of an expander. G is a subgraph of an expander. Okay? Because think of g as labeling edges of w by 0 and 1. Okay? And as long as it sort of has more than epsilon times w edges, you will get a good approximation. Okay, so we'll prove this in a minute, but let me first just kind of say how to generalize this to regular this regular splittable collections, etc. Is this statement okay? So it's just the same regularity statement, just with a better error term, so that it behaves well with even with sparse graphs. Okay, so you can prove this statement, and in fact, you can prove more general statements, all using the same kind of idea, which we'll mention in a minute. But let's just say what it will look like with respect to splittable collections this time. So now, instead of graphs, we have hypergraphs. Same setup, we have w, which is a subset of n to the k instead of w subset of n square. And it is now splittable instead of eigenvalue bounds. And we'll need the splittability parameter to be suitably strong. Okay. So, and now we will take this class of functions instead of tensor of two things, which were of this form 1s tensor 1 sub t. I'm just going to allow tensor of f1, f2, and so on up to k. Okay. Just because we are working with k uniform hypergraphs. So, okay. And again, I'm going to work with arbitrary functions taking, let's say, values -1, 1 instead of 0, 1. It's a bit simpler. And the theorem is, or like the statement is exactly the same. For every G, there exists an H, which can be constructed by just combining a bunch of these functions themselves, okay, such that G approximates, so H approximates T with respect to this function class. Okay. And again, we can prove it so that the error kind of scales correctly. Everyone okay with this statement? I claim if we have this statement, we are done. We can solve CSPs. So let's solve CSPs. So remember, we were trying to solve 3 XOR. 3 XOR instance looks like this, where this I1, I2, I3 belong to my some splittable collection W. Okay. And let me kind of construct a G by just kind of taking the right-hand sides, which are zeros and ones, and just embedding them in real space as before. Okay. So now I have a G. And my regularity lemma tells me that if I have a G and all I care about is its kind of inner product with functions from this restricted class, I can use an approximation of G, which is built in terms of the same kind of functions. Okay. So what are the kind of functions, or what are we trying to optimize? So let's think of an assignment, which is some values of X and sort of to each Xi1. So an assignment is just something in F2 to the N. You can think of it as a function from N to -1, 1 by doing exactly what we were doing in the morning. Just kind of at ith point, I write down -1 to the alpha I. This constraint is satisfied if and only if G I1, I2, I3 times F alpha of I1, F alpha of I2 times F alpha of I3 is 1, right? Or rather this, yeah, I mean, this expression is 1, which is equivalent to saying that this product is 1. Okay. So I can study, instead of kind of maximizing the number of satisfied constraint, I can study maximizing the inner product of G with functions of this form, F alpha tensor F alpha tensor F alpha, right? Because I'm writing at I1, I2, I3, I'm writing F alpha of I1 times F alpha of I2 times F alpha of I3. This is what is called the tensor. Right? So, so I'm going to search over all functions now, F alpha, the maximum over such functions inner product G. And this is the kind of stuff regularity was designed to handle, right? So we are trying to study the inner product of G with such functions. Then regularity will tell you that study the inner product of H with such functions, where H is actually built out of such functions, right? So you can construct a regularity approximation for G. So let's write down that regularity approximation. Let's say that has Fj1, Fj2, Fj3, or a bunch of J's. And because these are tensors, you can write them in terms of individual inner products. And now we are in the same situation as before. Earlier we said kind of the object we are searching for, the size of the cut, only depends on the intersection of this S with each of the Sj's. Now, the object we are searching for, the best assignment or the value attained by the best assignment, only depends on the inner product of F alpha with each of the Fj's. Okay. And so we just need to know these numbers. Okay. Again, we do exactly the same. Each of the Fj's kind of gives us a 1 - 1 labeling of the N space. We can look at the partition generated by them, by all of these Fj's. And within each partition, just guess how many ones and how many -1s occur, or how much agreement is there between F alpha and sort of Fj restricted to this partition piece. Okay. And we go over all densities. That gives us the maximum value of the CSP. And in fact, again, we can, as before, actually find a good F alpha out of this, right? So that gives us an algorithm. So that's our decoding algorithm. That's all we wanted to do with CSPs. The catch is that we need an algorithmic version of the splittable regularity lemma. And this is actually doable in order n log n time. You need to solve an SDP to find this approximation, but it's an SDP which you can solve fast using primal dual methods. Okay. And once you have regularity, you can get an approximation of the CSP. Once you have an approximation of the CSP, you can get decoding. Right? Because we saw if you are kind of close to a solution of the CSP, then you're close to a valid X. So that's a decoding algorithm. And in fact, regularity automatically does some sort of enumeration. We kind of search over all possible things. So this automatically does list decoding. But it doesn't quite go up to something like half minus root epsilon or half minus it sort of goes up to half minus eta, where eta is this kind of a function of epsilon. So it's a somewhat weaker. For sufficiently small epsilon, this will still be close to half, but it's not Johnson bound. Okay, but it has running time and log n. Right. So that's all about the algorithm. 2 minutes, 3 minutes. Sorry. Okay, let me kind of just restate this kind of like mention again the statement that we had for regularity in a more broad way, and I'll kind of just quickly say the proof of this, which is more abstractly what we were trying to say is that you have some function g. Let's say from some abstract space to -1, 1, you have some class of functions from the same space, and you have some probability measure, and you want to kind of build an approximation for g which fools all functions from this class, and hopefully something simple. G can be very complicated, messy to deal with, and so on. And the lemma says in general that there exists an H which is just a linear combination of a bunch of functions from the same class. And the proof is actually shorter than the statement and everything else. It's gradient descent. Okay, so you start with, so what you're trying to do is just kind of minimize a convex function. I'll mention that function in a second. But you start with H as 0. If there is a function in this class which distinguishes G from its approximation H sub t, then add that function to your approximator. Sorry? Perceptron, yeah. And you can prove that the L2 norm decreases as a result of this. So it can't keep going down forever because G in this definition had L2 norm at most 1. So you'll stop in 1 over epsilon square steps. And that's it. I mean, so this is the regularity lemma. You can kind of apply it in these various settings. There are some, like the technical part of the paper is actually just making this algorithmic for splittable hypergraphs. That I will not get into. But if you just want to think of this as convex optimization, I can just mention that this is solving the problem. This is a linear function in H. This is a supremum of linear functions. It's a convex function. And you're just trying to minimize this convex function. And if it's piecewise linear, so at every point, the derivative will be one of these FTs. You just move in that direction. You apply gradient descent. That's the proof. Okay. I'll stop here. A few open questions. As I said, it would be great to extend this to going all the way up to the Johnson bound, and where we can do this by SOS methods. It will be great to also be able to work with something weaker than splittability. And there are some notions defined by Blanc and Doron. And a last question which I want to mention is that somehow here we are trying to get additive approximations to CSPs. If you can satisfy 0.9 fraction, we are trying to satisfy 0.9 minus epsilon. But really, what we want is an advantage over half. So we're working with max cut or sort of max 3 XOR, where we can satisfy, let's say, half plus delta fraction, and we want to satisfy half plus delta prime. So we want to just approximate this advantage over half. In some multiplicative approximations, some relatively weak multiplicative approximation is fine. In some sense, we are solving the wrong problem with this additive approximation. And maybe that's one thing that kind of limits how far these regularity methods can go. It would be good if we have a technique for this actual multiplicative approximation problem. And I don't know one, but yeah, it will be great. So, okay, I'll stop here. Yeah. No, it's not. And that's a very good question. So, in fact, implementing this gradient descent algorithmically, this is the hard part. And for our case, we do it through a semi-definite program, but that's actually the tricky part in it. You can't always do it. For these kind of regularity type decompositions, there is a way to approximately solve this inner max through a problem called cut norm, or the sort of a semi-definite program for something called Grothendieck's inequality. But in general, yeah, this is not an easy problem. In fact, that's the key to the algorithmic part. I'm sorry?
Searching the vector.
Searching a vector to update in the direction of, or finding kind of a violation, a counter example to sort of the approximation.
they are integrated in this and so for example, if I have max cut instance with that value close to 1.5, are you like saying that you're trying to find multiplicative approximations in that way?
Yeah, so okay, for max cut, I should say that this is known. So this is a problem called max cut gain. So if your max cut instance has value half plus epsilon, can you find a cut sort of which cuts at least half plus epsilon prime fraction of the edges, where epsilon prime is maybe somewhat smaller than epsilon, but not too small. And there is a result of Cote and O'Donnell, which kind of gives half plus omega of epsilon over log 1 over epsilon. But without any assumptions. So you don't need expansion. You don't need anything about the graph. This is just true for all graphs. Okay, and it's also tight. You can't do better than this. I mean, I think they proved UG hardness, but now with the 2 to 1, it's actually NP hard to do better than this. But I don't know of an analog of this for, let's say, 3 XOR or 4 XOR, where this general result is impossible because a random 4 XOR instance, we don't even know how to, like, it's no more than half plus epsilon satisfiable, but it's hard to even say it's kind of not perfectly satisfiable. So we can't hope for that strong a result. But maybe we can have a weaker dependence on the splittability parameter or this kind of approximation parameters, which right now we need a fairly strong dependence because we are trying to solve a stronger problem, which is additive approximation.
So let's start with the final talk for the workshop. So Prahlad will be talking about lifting testability using high-dimensional expanders.
So mic on? Yeah, good. Thanks. Thanks everybody for staying on till the last talk. This will be sort of an application of HDXs towards testability. This is based on joint works with Gautam Dijkstein, Irit Dinur, Pranal Kumar, Nagaran Zevi, Ramprasad Saptarishi, and Madhu Sudan. So, three different words, one of which I gave a sort of a tutorial in the yesterday, HDXs, but the other words called liftability, lifting, testability. Yeah, there's a lag between my one. So let's first take time to sort of introduce each of the characters in our talk. So even before that, I need some preliminaries to define what these concepts are. So I need some basic primer on error correcting codes and expanders and expander mixing lemma, some of which the second thing I mentioned in yesterday's talk, but let's quickly go over that again. So a quick there's a lag between. There's a quick primer on error correcting code. So what is an error correcting code? So we'll be working over some alphabet set, say sigma. Typically, it's the Boolean alphabet, but it could be anything. The most common example we'll be seeing in the talk is when it's actually some finite field SQ. It is inside. Is that? Okay, thanks. Okay. So there was that. So so we're dealing with some finite set sigma, typically 0, 1, but for the typical examples we'll see in this talk is when sigma is actually a finite field, and an error correcting code is just an arbitrary subset of sigma to the n with certain special properties. So, and these properties are typically described by two parameters of the code, which we'll refer to as the rate and the distance. What is the rate? Rate is defined to be log of size of c by n. This is typically the amount of information per each symbol of the code word. And the other more interesting, this one is distance. This is the sort of for any pair of distinct code words, you ask what's the minimum Hamming distance between them. And so we'll refer to this the minimum Hamming distance as delta n, and delta will be referred to as the distance. And in general, we are interested in codes for which, or rather a family of codes as n grows larger and larger, in which the rate is constant, delta is constant. These are two fixed constants, and we want to construct codes. In fact, it's still an open problem. What's the best trade-off between R and delta that we can achieve for, say, the Boolean alphabet? But we'll be interested in such one, and actually in a couple of slides, we'll see one construction of codes which will achieve a constant R and constant delta for a growing family of this one shortly. Okay, this is a second preliminaries. This is what we already seen. These are expander graphs, which are well corrected. The primary thing about expander graphs which we'll use is the spectral notion of expansion. That is a second eigenvalue. We'll be dealing with graphs. The graph, we'll be talking of a graph being a lambda spectral expander. We talked about this a fair amount yesterday, in which we have a family of graphs of possibly a family of graphs of increasing sizes, but possibly constant degree or a fixed degree, in which the second eigenvalue is at most a fixed constant, bounded away from 1. And one thing which we also mentioned in yesterday's talk was, once you have these expander graphs satisfy a very nice property, which we call the expander mixing lemma. I just flashed it in yesterday's tutorial, but let's go over it a little carefully because we'll be using this quite a lot in the later part of the talk today. So what does it say? Suppose the expander mixing lemma sort of says the expander graph, though it's possibly a very sparse graph, it has only order n edges, it behaves very much like a random graph. In what sense?
In what sense? So let's take any two functions f and g on the set of vertices. For simplicity, you can think of these as indicator sets of two arbitrary subsets of vertices. And then let's look at this quantity, mu f times mu g. This is the mean of the function f and the mean of the function g. Now this is what, so you now pick two vertices at random, completely at random, ignore the edge structure of the graph, pick them at random. This will be the this will be what the expected value of f mu times gb if you had picked the two vertices at random. But instead of that, if you pick it according to the edge distribution, pick a random edge and do this, this is the expected value of the product you would see. And what the expander mixing lemma says that the difference between these two quantities is fairly small if the second eigenvalue of the graph is small. So it sort of says the graph mixes well. Sense? We'll use this amount. Okay. So given that, we can now talk about what three properties which I was talking about. The first, what do I mean by lifting? And this is sort of best instantiated by an explicit construction in some context. So we talked about this. I'll give the example of Sipser-Spielmann codes. So notice we wanted to find out, and the very thing I said, it's non-trivial to construct codes with constant rate, constant distance. In fact, the best trade-off is not known. Let's try to construct a family of codes which have constant rate and constant distance. What we'll show is that if you have a family of expander graphs, then you could use that family of expander graphs to actually construct a family of codes which have constant rate and constant distance. And how do you do this? You start off with some base code on a constant size block length, say capital D, with some rate R0 and distance delta naught. This is constant size, so you can possibly brute force search and lay your hands on such a code. Find the best code over block length D. Now suppose you have a spectral expander G on n nodes, and think of n as a very large number. D is a fixed constant. It's a lambda spectral expander, and the degree of this graph is bounded. It's D regular. Then Sipser-Spielmann says that you can somehow combine these two to get a larger code, a much larger code. The block length of this code is n, whose rate is 2r0 minus 1, and distance is delta naught minus lambda. So as long as delta naught is larger than lambda, you get constant rate, constant distance codes for a large family of codes. Let me quickly tell you what this construction is. So this is a Sipser-Spielmann construction. It's a beautiful construction. Can you people see what I'm writing, or should I use white? There it is. Yes. Is that better? The Sipser-Spielmann construction. So suppose you're given this graph G. It's D regular. We are going to so each vertex has degree D. I'm going to construct this new code, which is based on the graph G and the base code C0. Its block length is, I should have written, its block length is M, which M is a number of vertices. It's block length. And what is it? It's going to be the set of all code words on sigma to the M. You're going to put a symbol on each edge. CE1, CE2, this one, sigma to the M, such that for every vertex, if you look at the restriction of this code word to the neighborhood of that vertex, if you just look at what it sees in its neighborhood, this should belong to the base code. Any such word, such that if locally around every vertex, what you see should be part of the code C0. All such code words, all such words that have this property are members of this code word. A priori, it's unclear whether there's any code that satisfies this property, but you can show actually the code has distance 2r0 minus 1. So if r0 was less than half, this does have positive rate. And not only that, this code actually has distance. And lambda is the second eigenvalue. Lambda is the second eigenvalue. The smaller the second, And what do I mean lifting here? So these expander graphs are sort of taking the base code's distance. The base code has some distance delta naught, and it's lifting this property of distance, sort of local distance, to a global distance. It's getting a whole family of codes which have distance. So we want similar properties. Expanders have this nice thing, properties that they take some local property and lift it to a global property. It's taking some local property. The code word has distance over here. And because the graph is an expander, the new bigger code word also has some distance. So it's taking some local property and lifting it up to a global property. And we'll see, this is what I mean by lifting, at least informally. And we'll see this in the context of testability. Yeah. No, this is a non-bipartite graph. And by the way, the proof of the rate is actually trivial. It's just dimension counting. The proof of the distance just follows from the expander mixing lemma that I flashed previously. You just use the expander list. For linear codes, yes. Every code that I'm going to consider will be linear. So, yeah. Okay. Next is testability. Now we have these codes. I would like to ask some other property is, given a purported code word, can I check whether it's a member of the code or not? This is something what Akash was talking about. So we're going to have a tester which potentially probes. So think of W1 to Wn as a potential code word. We don't know if it's a code word or not. And you have a tester which is going to look at this code word and tell you whether it's a code word or not. The only constraint, if it of course gets to see the whole thing, if you're working with linear codes, you can check it whether it's this one, but you get to see only few locations based on your random points, and you still need to say whether it's a code word or not. And such testers, we do have such testers. This is no, there's lag between here. So when do you say that such a thing is a tester? When a word is a code word, the tester should give say 1, accept with probability 1. And if the code is the word is say far from the code, say in Hamming metric delta far, then it should say accept only with probability say at most 2/3 or some such thing. So 2/3 is an arbitrary constant. We can fix it to be any fixed constant. So we want to design such testers. And the crucial thing is we want to make the query complexity of the tester as small as possible, typically a constant. So the question is going to be number of edges. I messed that. Number of edges. Sigma to the m. Sigma to the m. Yeah. The code is sitting on the previous slide. I had got that wrong. Okay. Yeah. So what we would like to ask is, do there exist codes which have good rate, preferably constant rate, constant distance, constant fractional distance, or linear distance if you measure it, this one, and testable with constant number of queries? This is an interesting question we can ask. And we just saw that expanders where you could use expanders in constructing codes with the first 2 properties. Now, what I want to know is, can I use expanders to construct codes with all 3 properties? And not surprisingly, such things can be done. There have been this one, and actually that's a wrong citation. HDXs can be used to obtain the 3rd property. And what the talk is going to be talking about is how can HDXs potentially be used to do this. This HDXs is in quotes, and the reason why it's in quotes, I'll come to that shortly. And just if this one, almost all testable codes that we have constructed so far are examples of such cases. There's an underlying HDX or a HDX in quotes by which the testability has been proven. This is starting from the very first Hadamard codes, the proof due to Blum, Luby, Rubenfeld. There's an underlying HDX structure using which the testability of this code has been proven. The Reed-Muller codes, their testability was also proven very similarly using some properties of some underlying HDX underneath it. And more recently, there was this breakthrough work of Dinur, Evra, Livni, Lubotsky, Moses, and Kalachev and Pantelev, who answered the question which I had asked in the previous slide, that whether they exist constant query, constant rate, constant distance codes, and they use some sort of HDX property to actually construct such codes. And the HDXs they used are actually what are called square complexes. These are, and the reason I put it in quotes is these are not HDXs the way I defined HDX in the tutorial, but slightly different HDXs. So let's see what are these type of different HDXs. I'm going to use the word HDX in a very liberal sense. That is, and I'll tell you, so next few minutes we'll spend on what do I mean by HDXs in this sort of very loose sense of the word. So let's recall HDXs from what we had done last time. From the tutorial, we had this sort of, we had a K-uniform hypergraph out of which we built a layered graph. The set of K sets, set of K-1 set, triangles, edges, vertices, and this ones. And we had this notion of it said that if you take any hyperedge in between and you looked at its corresponding link, the underlying graph beneath it should be an expander of its own right. So this was the link expander. Let's work with this definition. We'll change this definition to various things. So what does this tell you? That if you look at this layered graph, which I'm going to, so that's if a layered graph. What is this? If you take it any one face point of view and you look at the corresponding link this way, the underlying graph beneath this should be an expander graph for every circle point. Now, because this was down closed, it also has the other property. So suppose this was some K set. This was some hyperedge E with vertices V1, V2, Vk. Now you restrict your attention to only those things which are contained in E. Now, because this is down closed, this down-thing shadow will be the complete complex on the vertices V1 to Vk. And therefore, those things will also, everything out there will be a good expander on its own right. So I'm going to use HDX in this loose sense. That is, we're in general going to have a layered graph, which is possibly inclusion graphs general, in which various substructures have various expansion properties. And our prime example of such this one is what I'm going to call the affine Grassmannian HDX, which is not a HDX by what I had defined last time, but it has this property. So what is the affine Grassmannian? Yeah. Which property? So I have just now, I haven't generalized anything so far. I'm just going to talk. I want to say HDX, I'm going to use it very loosely for various substructures of it that have expansion. Each time I quote a theorem, I'll say exactly which substructures I want to be expanders and stuff. So right now I'm just using it. I'm going to use it very loosely for any layered graph in which various substructures, the substructure which we talked yesterday in the link HDX is for any hyperedge. If you look at its link, the graph underneath it had to be an expander. That was one. We could talk of various other substructures also meaning to have an expansion property. And I'm going to use HDX as a generic term. My co-authors will not be happy with this, but I'm going to go ahead and use this term generically for referring to any such structures. Each time I state a theorem, I'll state it formally, because we'll have a specific HDX in mind when I state it. Okay. So one particular object I'm going to call is the affine Grassmannian. It's fairly complicated words for something quite simple. So we're going to deal with some vector space. So F is a finite field, and we are working in m dimensions. And the layers here are now going to correspond to very natural objects. We're going to look at all points in the finite field. So this is exactly F to the m. Then we're going to put all possible lines in this, all possible planes, and so on up to, you go up to some fixed dimension. All possible k-dimensional affine subspaces. Okay. And the edges between them you put are the natural inclusion edges. If a particular line, if a particular k prime affine subspace is contained in the k affine subspace above it, you put an edge between them. And if you look at this, actually this graph almost every I'm not going to define what structures, any substructures that you think of it has going to have extremely good expansion property. For example, take any one line and just look at what it sees above it. Look at all planes that contain this line, all cubes that contain this one. If you notice that that particular bipartite graph will be a very good expander. This will just follow from pairwise independence, and this will be a very good expander. So in general, at least for a large part of this talk, we'll be talking only about the Grassmannian. If I have time, I'll talk about the square complexes, which I don't think the rate at which I'm going, I will have. But we're going to talk about this particular thing, which is the Grassmannian complex. And in particular, we'll only be dealing with a 3-layered structure. So actually, I erase all, in which we just have points, lines, and planes. So we have a point here, we have a line here, and a plane here. Yeah. Firstly, the way I defined HDXs were simplicial complexes. These are not down-closed. So it doesn't technically fit in the way I defined this once. So you had to define something, you had to define layered graphs and other things. So, but here I would just want to say that take any point and look at all the lines that contain it and all the planes that contain it. If you look at just that part of the graph, that will be a good bipartite expander. Take a particular plane and look at the lines that are contained in that plane and points contained in that plane. If you just restrict to that particular bipartite graph, that will be a good expander graph. In fact, each of these will be isomorphic to some other Grassmannian on a different dimension. So somebody pointed this out yesterday, where the complete complex, various links would look like complete complexes of smaller size sets. The same thing is going to happen over here. Okay, we'll deal with this. So this is the sort of HDX. HDX I'll be mostly dealing with for the talk today. And the code sitting on this, which I will work with, is the Reed-Muller code. So what is the Reed-Muller code? Once again, there's this vector space Fm, there's an ambient dimension M, there's a degree D. Think of the degree D as large but smaller than the size of the field, so that we can apply Schwarzschild, D over Q. And what is the Reed-Muller code over this? It's basically take every polynomial of degree at most D, M-variate polynomial of degree at most D in this space, and evaluate it on all points in the space. This is the Reed-Muller code. It's this evaluation vector these evaluation vectors are the Reed-Muller code words. And this collection of it is what I'm going to call the Reed-Muller code. The rate of it can be just read off the definition. The distance follows from Schwarzschild. The distance is at most D over Q. What we'll be actually interested is not these two quantities, but this is not a constant rate, constant distance code. But what we'll be interested right now is can I show testability of this code? So notice, what is this code again? So you have this m-dimensional space, Fm, and you are given a function as a table of values on this. And you want to check, is this function actually a Reed-Muller code word? Is it an evaluation of a Reed-Muller word? Is it the evaluation of a low degree polynomial on this entire space? What's a natural tester for? What's a tester that one can study? Natural tester for doing this? Because I want to check if this object is actually a Reed-Muller code word. This is a linear code word over the field F. A very natural tester is the following tester. Just pick an arbitrary line in the space, read the function only on points in this line, and check if the restriction of the function on this line is actually a univariate polynomial. The restriction of a multivariate polynomial of total degree at most D on a line will be a univariate polynomial. You just want to check this restriction. If it is a univariate polynomial, you accept of degree D, univariate polynomial of degree D. And clearly one direction is true. If the given function was indeed the evaluation of a multivariate polynomial of degree at most D, then the restriction to every line will be a evaluation of some univariate polynomial of degree at most D. Now, question I'm going to ask is the converse. If for most lines you actually do see the restriction of a univariate polynomial, is the global object the restriction of a multivariate low degree polynomial? So this is the tester we just now talked. We want to ask how good is this as a tester. So the query here, notice the function is q power m. The total size of the table is q power m. The number of queries is just q queries. So it's just the number of points on the line. So therefore, if m is large enough, this is for any m. This is actually for any m. This is sublinear in the size of the whole space. For m being 2 onwards, it's sublinear, and a larger m is, it's even, you're reading very, very small number. It's not constant, but you're reading very small number of things and able to check that this one. Are we able to check? So I want to ask the converse question. That is, is this tester a good tester? And in fact, this tester actually forms the basis for, it's one of the most basic objects. It forms the basis for the PCP theorem, which was proved 3 decades ago. Yeah. Spoiled the word decade for me. Okay. So what do these sort of theorems prove? This, by the way, this tester was proposed by Rubenfeld-Sudan, and the current statement of the theorem is due to Friedel-Sudan, which builds on the result of Polishek and Spielmann. It says the following. It says there's some fixed delta naught and a constant c, says that as long as the field is large enough compared to the degree, so this is just for some Schwarzschild sort of statement to hold, then the following holds for any function f. If the function, when restricted an arbitrary line, if the expected agreement to, when I mean P1D, I mean univariate polynomials of degree at most d, when restricted to a line, if it agrees with some univariate polynomial and the agreement is at least 1 minus delta, and this 1 minus delta is, so think of delta as some 0.01 or something. So the expected on a random line, you see agreement say 99%. It agrees with a line on 99%. You want to ask how good is the global agreement with degree m polynomials. So this is sort of a local agreement. It's agreement of just the restriction of the function on a line to univariate polynomials. What you want is the global agreement, the agreement of the function with m variate polynomials. Because just based on local agreement, can you say something on global agreement? And this theorem, what basically says, indeed you can. You can, if there's a global agreement is at least, say, 99%, it says expected local agreement is at least 99%, expected global agreement will be 98%. That's what it says. And this is called in the low error because it reads very high agreement. It works only when delta naught is for agreements which are when 1 minus delta is smaller than delta naught. There's a corresponding theorem which was also known, version of it, which was proved for the high error, that is, the agreement is really, really low, and you still can say something. So it says that as suppose there is for all functions f degree functions f, all fields f degree d and epsilon naught, as where epsilon naught is some large enough parameter in the Frey ratio d over f, the following holds for any function. If the expected local agreement is at least epsilon, then the global agreement is epsilon minus epsilon naught. So you at least, so even if you agree with the lines, on a random line you agree on 1%. For a random line you agree on 1% of the time. Then globally you agree 1% minus epsilon naught with a global polynomial. A statement of this type was proved in 97 due to Aurora and Sudan with slightly deteriorated parameters. The primary improvement we get recently is improving the range of epsilon naught, how small epsilon naught range, and primarily the ratio between d and f is the difference between. Otherwise, the theorem as stated is due to Aurora and Sudan from 97. It's some fixed constant. It's a fixed constant, 38 or 40 or some fixed constant. Okay. One hopes that the constant will be 2 or so, but right now the proof yields a large constant. Yeah. Okay. Why am I flashing all this? I want to say, how do you prove? So how does one prove the statement? For instance, how did we go about proving this theorem? How did we go about proving this theorem? So right now, look at it. It is a statement for, it's a statement for function in m variates. The way we went about actually proving this is we first proved it for functions just on m equals 2. That is not an arbitrary line, but actually the bivariate version of this. That is, you're just given a plane f square equals f. You're given a table of values like this. You pick a random line and you check that you do exactly the same test. We proved the theorem for the bivariate case. And then we sort of lifted it to arbitrary m using properties of the Grassmannian. And that's basically what I'm going to sort of talk about. So this work actually involves two parts, both our work as well as previous Aurora Sudhan work. They will prove a base theorem for some constant m and then lift it this one. So this, what I'm talking is these HDXs let you do this. You prove testability for some constant size, a small sized object, then you can lift it to a much larger size object using the expansion properties of some underlying structure. Here it will be the Grassmannian HDX. Yes. So if you recall, there was a Moshkovitz-Raz theorem which gets a de-randomized thing. That's, you can, the proof will just uses expansion. So if the object, sparse object had this one, it will lift. Yeah. So this sort of proof will just tell you if you had a sparse version of Grassmannian, the same low degree test theorem will just go through. Only thing is you need to make sure that the base case also holds for the sparse version. Then then this lifting is just oblivious. It just works. It just needs a spectral gap of the underlying objects all to be the same. And if you look at the proof of Moshkovitz-Raz, this is essentially what they'd show. Okay. Okay. So what I plan to do this one. So what the whole point of doing all this Reed-Muller was just to say that this was an important proof in gradient. We used the properties of the Grassmannian. So we proved something for just a small sized object, a bivariate object, just for this plane, which just looks like a line in a plane is just quadratically smaller. And we proved the test for this. And we are able to lift it for arbitrary m with hardly any loss of parameters. And this happens because this underlying object, we'll talk about this underlying object when the ambient dimension is Fm. This will have good spectral properties in various senses of the word. And you're going to use that to do this lifting. So, by the way, the main technical part of this, all these papers happens to be typically the second bullet, not the third bullet. But because this talk I'm talking about HDXs, I will focus only on the third bullet, which is and assume the result is true for the bivariate case. So we'll assume the result is true for the plane and show how to lift it for m dimension. Any questions so far? No. So the way the proof goes now, tau deteriorates in both places. Yes, heavily in both places. Yeah. At least the proof as written, as I know of it now. There have been proofs. For example, there have been proofs in which if you don't work with lines, if you work with cubes instead, then we know how to make the tau to be equal to 1. This is work due. So it started off with work from Amai, Irit, Inbal, and more recently Dor Minzer, and who's the other? Zhang. Yeah. So they managed to get it. But if the thing was not a line but a cube. And once again, the reason they're able to get is the corresponding HDXs they work here have better expansion. The spectral gaps are better when you work with cubes than with lines. There's a theorem due to Ras-Safra which is on planes. Yes. Okay. So what we will do now is won't have time to go do exactly the full. Painful. So I won't be able to do the full-fledged lifting for the high error region, which is our main this one. What I'll instead show is for the low error version. It's about sort of the baby case of it. The low error version, I'll show how to lift it from here to here. And one of the reasons I want to do the proof, actually in its entirety, I'll have time to do the proof in its entirety, is because it will show you where in this thing I'll actually use the expansion of various substructures of this object. I will actually explicitly use them. It's a baby case of this. We're going to prove it only for the low error version. So in particular, we're going to assume this theorem, the low error version of the theorem for m equals 2. So I'm assuming the bivariate thing, the low error curve, and I'm going to prove the arbitrary m variate version. We'll more or less give a full proof of how to go from the low error theorem for m equal to 2 to the low error theorem for arbitrary m. The questions on this. And I'm going to use the fact that this structure has expansion over here. Question? Okay. Let's see. So what do we have? So I want to prove the higher error version. Jump too much. So we want to prove I'm given a function f of this form, and I know that the expected agreement of f restricted to L on this is larger than 1 minus delta. From this, I want to show that there is one global polynomial with which f agrees. So in other words, I'm given a table of values like this. So the table of values in particular specifies for every single plane over here, it does give me this one. And because the expected agreement on lines is large, if I take a particular plane, if there are several good lines in that plane also for which the expected agreement is large. So in particular, the bivariate version of the theorem. So we are given the function is evaluated on this space. The bivariate theorem says that for every pi here, if I just look at the portion of the graphs under pi, then actually for that particular thing, if the expected agreement is large enough, the bivariate theorem will say for this pi, I possibly have a low degree polynomial, but only restricted to this plane. Then for another pi, I have another low degree polynomial, this one, another pi. But these are all different low degree polynomials. I need to be able to stitch them together to get a global, these are low degree bivariate polynomials. I need to be able to stitch them together to get a global m-variate polynomial. And we'll show how to do this using these properties of the HDX. Questions so far? So that's where we are. I've given an arbitrary function f, which is of this type. Let me make it a little bit for every line L. Let's define the best fit univariate degree D polynomial. If multiple of them exist, just pick one arbitrarily. This is the best fit univariate degree D polynomial. So for every line L, we take the best fit. Therefore, this delta was adjusted. So delta is actually the probability that f of x is not equal to TFD L for a at the point x for a random choice of x and L that contains x. Yeah, I have about another 20 minutes or yeah. So let's define this as delta f. We want to show that if delta f is smaller than what? If delta f is smaller than 2 delta naught, then there exists a global polynomial Q in PMD such that the agreement of f with Q is at least 1 minus 4 delta. That's what we want to prove. Questions on this? That's like I exactly written out the conclusion of the final result I want to prove. This is exactly if delta f is smaller than 2 delta naught, then I want to show there exists a global polynomial Q that satisfies this. Notice we only have something happening at a very local level. We have it for every plane. I need to stitch it to get a global m-variate object. So how am I going to lay my hands on some global m-variate object? So we want to correct this function. There's a so we'll define a natural correct, the self-correction of f. So we're going to define f correction, which is a function from fm to f. And we'll define it in a very natural fashion. For every point x in the space, we look at all the lines that go through this point look at what all the best fit polynomials predict and choose the most popular value. So this is f core of x is the plurality, the most popular value, that's the plurality of L's that contain x of PFD L of x. Is that clear? If there's more than one, this one just break ties arbitrarily. So we'll define it this way. And I'll want to claim that this, ideally it will be great if I can show that this corrected function is close to f and the corrected function itself is a low degree polynomial, then we would be done. We won't be able to show that in one step. What we'll show is the following. We'll show the following two claims. Claim 1, which actually is fairly trivial and I will skip the proof, is f and the f corrected are actually pretty close to each other. This is at most 2 delta f. F and f corrected will be pretty close to that. Just follows because f passes the low degree test reasonably well. F and the best fit line agree with probability at least 1 minus delta. Therefore, this is good. This is where it's almost, you just write down the statement of this, you will get this. So I'm going to skip it. Huh? Which one? That delta and delta f are the same thing. This is delta f. That's delta f is defined to be this, which is exactly, this is not equal to, that's agreement here. Okay. Claim 2, which is the more interesting, this one, what we'll show is, so we'll show that f corrected passes the low degree test with even better probability than this. So if you look at delta f core, which is, I plug in f core instead of f in that statement, then it is smaller than delta f by 2. It passes it. Its rejection probability is less by a factor of, it falls by a factor of at least 2. Why is this good enough? You can now keep correcting the function repeatedly. You can start with f, correct it to f core, then keep correcting. It's going to become closer and closer. Rejection probability is going to become smaller and smaller. This cannot continue infinitely because the number of these probabilities are discrete quantities. So eventually it's going to hit. No, this is true for any function f. I'm going to define this for any function f. So this I'll prove only for, this is if delta f is smaller than delta naught or something. Anything close enough, then it will go, is going to go. It's not delta, no, it is. It's possibly delta f smaller than 2 delta naught or something. Yeah. Is that what I have there? That's what I have there. And q is larger than some poly in 1 over delta naught. Delta naught is a fixed constant. This is what claim 2 will show. Notice if I prove claim 1 and claim 2, I am done because this will show that the corrected function becomes closer and closer to a polynomial. Eventually, it has to become a polynomial. This process cannot continue. And each time, the distance between f and f core is 2 delta f. This number is also shrinking. So eventually, it will be 4 delta f. It will be just even 1. So that's, we'll forget the theorem if I prove claim 2. So what I will try to do, convince in the next sort of 10 minutes is the HDX property can be used to prove claim 2. Okay. So are you with me or any questions so far? Yeah. F core, yes. So f is some arbitrary function which passes the low degree test with reasonable probability. Now I'm given this low degree test, given this function f, I'm going to define the best fit line. For every line, I'm going to define the best fit polynomial, which is choose the univariate polynomial that agrees the most. That's PFDL. F core, how am I finding it out? For any point x, we look at all the lines that pass through the point x, look at what all the best fit lines say about this point, choose the most popular value. So each of these low degree polynomials evaluate to something at this point x, because these lines choose to tell what it say and choose the most popular value among all of the lines. That's why it's called the correction of f. That is possibly one line, on one line it's wrong, but other lines possibly give it correctly, so it corrects the value. That's why it's called the self-correction of x. So I'm going to correct it this way. So from F, we are moving to an F core. Huh? No, F core is a function on the whole space. And so F core is a function on the whole space. This is an arbitrary function. This is an arbitrary function. What we'll eventually show is if you do this process repeatedly, eventually you're going to collapse to a low degree polynomial. That's what we're going to show. Questions? Okay. So what we need to show, what does this claim suggest? It says that F core is going to pass the low degree test with even better probability than F. So if F rejects with 2% of the time, F core is going to reject only 1% of the time. And then next, once you apply a correction on F core again, that's going to reject only 0.5% of the time, and so on. And this cannot go on arbitrarily small because this is a discrete space. Eventually, it has to become 0. Okay, so how do I? So I want to prove is. Well, we want to prove is the following fact. Delta F core is less than delta F by 2. Let's recall what delta F core means. Delta F core is the probability that you choose a random point and a random line containing that point, that F core of X is not equal to the best fit polynomial for F core at the point X. That's how delta F was defined. And now we're writing delta F for delta F core. This is the best fit polynomial according to F core. Certainly, this is a quantity less than or equal to if I choose the best fit for F, if even that pass, that is only going to reject with even worse probability. This is certainly an inequality because PF core DL is the best fit for F core. This is for best fit for F. That's only going to make this even worse, this rejection probability. Now, look at this. This is the best fit line. This is what the best fit line, this is the best fit line of F. This is what the best fit line of F tells at the point X with the most popular value of this. It's not hard to see this is at most pick X, pick 2 lines L and L prime. So in the space, you pick X, you pick a line L, you pick another line L prime and ask what do the 2 best fit lines what do both the best fit lines say at the point X? This is just stating that the most popular value versus the collision probability. So what we want to show is, to show delta F core is less than delta F by 2. Well, I'm claiming it suffices to show this quantity is less than delta F by 2. And what is this experiment? Let's recall this experiment. Let's pick a random point, pick 2 lines through this point, and check if the 2 lines agree at this particular thing. So the nice thing about the way we have done it is, we wanted to talk about a global object. Now, the random experiment deals only with point and 2 lines through that point. This is restricted to a plane on which we have the bivariate sort of test. So we'll use properties of bivariate test to tell something about why this probability is small. And then this will conclude this, it will complete the proof for us. So once again, what's the experiment that we want? What's the thing that we want to prove? We're going to have to do this random experiment. We're going to pick a point X in the space. Basically this, we're going to pick a point X. We're going to pick 2 lines L and L prime to this. and then ask look at the best fit polynomial for this line L prime, the best fit polynomial for this line L, and ask if they agree at this point X. Now, if you have X, L, and L prime, there's exactly one plane. Assuming L and L prime are not the same, which happens with very high probability, there's exactly one plane that contains these three. So this picture is something like this. You have a plane with experiment is equivalent way of doing this experiment is pick a plane pi, pick two lines on the plane L and L prime and a point X. Or equivalently in this Grassmannian, what's happening is you're picking a point pi, you're picking a plane pi in this layer. You're picking two lines which are both contained in pi in this layer, and then looking at their intersection X. So this picture is that in the Grassmannian, this is this picture. Okay. And what we want to show is the following. Probability that PFD L, the best fit polynomial on the line L, the probability that it disagrees with the best fit polynomial on the line L prime, both of these disagree at the point X. We want to show the probability happens with probability at most delta F by 2. That's exactly what we want to show. This is this event. This is a random event. Pi X, pi L, L prime, X are picked randomly, and we want to show that after having picked that, this happens with small probability. Huh? Yeah. So this 4 tuple is picked randomly. So yeah, once you pick these three, pi is defined once. Yeah, I'm talking about the randomness defined in picking up this 4 tuple. Okay. I want to write down a couple of bad. So I want to write down some events for which this. No, so we have this plane. So all I want to show is if in this plane, the low degree test, the function had passed the low degree for most lines, if F agrees with the low degree test, then the bivariate version of the thing says there is a polynomial over here. And suppose that polynomial actually agreed with the best fit polynomial for both these, then because both the best fit polynomials are agreeing with the global bivariate polynomial, they have to agree with each other. We want to say that this event is going to happen most of the time. Most of the time, for most planes, we will see a bivariate polynomial that explains the function f. And not only will that bivariate polynomial explain the function f, it will actually be the best fit for this line, best fit for this line. Hence, it's going to actually agree on x. And we want to say, we'll write out a bunch of bad events which cause this thing not to happen. So what are the bad events? So these are a list of bad events. So E1 is the first bad event. So we defined, I had this delta F, which I defined delta F. Delta F was this quantity, probability X, L, and X. F of X not equal to PFD L of X. We'll define delta F pi, which is the same quantity, but restricted to the line lying in the plane. You pick a random point in this plane and do the same logic. Just focus your attention on this one. Now you could ask, the first bad event is globally the low degree test passes with high probability, but possibly this is a bad plane. That is delta F pi is larger than delta naught. Notice that if E1 doesn't happen, if E1 does not happen, there is a bivariate polynomial Q pi such that delta F and delta F restricted to pi and q pi is less than or equal to 2 delta f pi. This is the where I'm using the bivariate low degree test. If the E1 does not happen, then this happens. But that's what exactly the bivariate low degree test tells you. E2 is going to be, so in other words, f pi and q pi agree with each other. That's you picking on a random plane. Now you're picking a random line in the plane. What's the probability that this random line disagrees with q pi? And this is just the probability that E1 does not happen and delta f restricted to the line L and q pi restricted to the line L, say, are more than 4 delta naught from each other. And a similar statement for E3 for line. These are some bad events I have listed. Now, if none of these bad events happen, it should be clear that these two things will be equal to each other. Because if the first bad event does not happen, then there's a bivariate polynomial on this plane. And then it also says that bivariate polynomial agrees with the FL on a large fraction of points. Therefore, the best fit has to be that bivariate polynomial, Schwarz-Zippel. On this line, same thing on this line, therefore this happens. So if these three events happen with low probability, then this event happens with, then this equality happens with very high probability. So it suffices for us to show that each of these say happen. So what I'm going to say, it suffices. So it suffices to show. So the probability of each of these bad events, any EI is at most, say, delta F by 6. Then the total bad event just union bond is it. But this is now, just look at it. This is just, these are just sampling properties. You know that delta F pi. So let's look at this quantity, delta. Where did I define delta F? It should be clear from this definition that delta F is just the expected value of delta F pi. Therefore, if the planes sample the lines well, then this event should happen. The probability that this event happens should be very low. That will be your delta F by 2. Similarly here, now that if event E1 does not happen, these two agree with each other a lot. If they agree, what's the probability that on a random line these two don't happen? That's just the expansion properties of a plane over here. So this is once again a sampling property. This will also happen. So the fact the probabilities that E1 is low, E2 is low are just properties of some underlying bipartite graphs having good sampling properties. And basically using the sampling properties of the appropriate this ones, we'll get sampling, or the fact that the above is proved. And that basically completes this one. So I'm going to use this structure, show that the plane sample the lines well. For a particular plane, the lines here sample the points here well. You'll use these properties over and over again to actually prove that each of these events happen with very low probability. It's not, by the way, it's typically you show that low probability is a polynomial is low in the spectral gap. Here we'll need it even smaller. We want it to be delta F, which can go very close to 0, but the expander mixing lemma actually gives you this. If you, all of these things are just proved by running the EML on the appropriate bipartite graphs. You will get these sort of statements. And this sort of gives you the baby version of moving from the bivariate case to the M-variate case. And the higher thing also uses this, but it uses even more substructures to have good expansion properties. So yeah, and I knew I could not do this. What the Dinur et al. Result do for construct constant queries is they construct another sort of 3-layered object like this, which they call the square complex. They take a basic testing result. That's like over here we showed the bivariate is. We showed that there's a basic small size testing result, which we then lift to a large testing thing. They showed that tensor product testing can be lifted to their case. That's the proof of theirs. It's a more involved proof, but it's basically the same idea. It shows if an underlying structure, three-layered structure has lot of several substructures have expansion properties, then you can lift testing from a small thing to a large one. Stop with this. Basically, we use lifting using these HDXs, which are various sort of layered graphs, in which various substructures have nice expansion properties. We use this to lift testability on a small object to a large object. I more or less gave a full proof for Reed-Muller testing from m equals 2 to arbitrary m. I'll stop with this. Thank you. Yeah, Venkat. No. So this step uses planes and lines. This step uses for every plane. Now that you're in a plane, the lines and the points. So it uses both those. Huh? Yeah, there's only these three. This one. So this one uses this. This pair is a good. This one and this one. This one uses for every. So you prove it on a plane by plane basis. For every plane, if you have this property, the lines in that plane sample the points well. So yeah, so this is what I said. You now the corrected function the rejection probability for the corrected function is delta f by 2. Now you correct again, becomes delta f by 4. This cannot go on because this is only a finite space. So eventually, at some point, the corrected function will become a polynomial, but each time the gap is geometrically decreasing. Therefore, yeah. This is basically the idea. This proof, at least the baby case of it, which I proved right now, is there in Friedel-Sudan, but not for this HDX. Their HDX is points, lines, and they have some weird surface over here. This is a cleaner version of their proof. And so we use the Grassmannian, affine Grassmannian in our paper. So this proof, but essentially all elements, what I said for the baby case right now is in Friedel-Sudan, but they have a different three-layered object. This is points, lines, and surfaces which are defined. These are these sort of tensor-like surfaces which are defined in the Rubenfeld-Sudan paper. So this is essence what they actually prove. We prove it for the more natural Grassmannian, which we then extend to even the higher regime. Yeah.